Welcome to Simplilearn's YouTube channel. Picture this. Mountains of data, thousands, even millions of rows, and only few minutes to extract insights from it. Sounds overwhelming, right? Now imagine that you have a superpower that helps you surf through the entire dataset in few minutes or even seconds and answer to complex business questions almost instantly and uncovers insights that can actually drive decisions. That's the power of SQL. That's the backbone of every database and data-driven organization in the world. In this course, we will take you through the journey from the basics of SQL to the advanced queries, analytical functions, subqueries, real-time scenarios, and a lot more. You will learn how to explore data, identify trends, and solve business problems like a seasoned professional. By the end, you won't just write SQL queries. You will think like a true data analyst. If you are excited to transform the raw data into actionable insights, hit that subscribe button and ring the bell icon so that you never miss any updates from our end. That said, you might have already guessed that this video is going to be a little longer. So to follow us, it's better you download all the datasets, and the link to that is in the description box below so that you can follow along with us in this learning journey. Also, just that you know, if you want to upskill yourself and master data science and data analytics skills and land in your dream job, then you must explore Simplilearn's cohort of various data science and data analytics programs. Simplilearn offers a wide range of master's, certifications, and postgraduate programs in collaboration with some of the world's leading universities like Purdue, IIT Guwahati, and many more. Through our courses, you will gain knowledge and work-ready expertise in skills like Python, Tableau, Power BI, SQL, generative AI, and over a dozen others. That's not all. You also get the opportunity to work on multiple projects led by industry experts working in top-tier data and product companies. After completing these courses, thousands of learners have transitioned into a data science or a data analytics role as a fresher or moved on to a higher paying job and profile. If you are passionate about taking your first step in building a successful career in this domain, then make sure to check out the link in the pinned comment and description box below to find a data science and data analytics program that fits your experience and areas of interest. Now, without further delay, let's get started with the agenda for today's session. In today's video, we will walk you through SQL fundamentals. So let's go through the agenda in step-by-step fashion. First module, you will be learning about the introduction to SQL and database basics. Chapter 2 will be about the basic SQL queries. Chapter 3 will be about understanding data types and operators. Chapter 4 will be about inserting, updating, and deleting data. Chapter 5 will be about mastering SQL joins. And 6 will be about grouping and aggregating data. 7 will be about subqueries and nested queries. Chapter 8 will be about data modeling and relationships. 9 will be about indexing and performance tuning. 10 will be about views, functions, and stored procedures. Chapter 11 will be about transactions and error handling. 12 will be about real-world SQL projects. 13 will be about SQL for data analytics. And 14 will be about integrating SQL with Python. And 15 will be about SQL interview questions and answers and some certification preparation tips and tricks. And 16 will be our last module or chapter. This will be about final project and wrap up. And last but not the least, this final project is to test your learnings. So I hope I made myself clear with the agenda. Now let's get started with a small quiz on SQL. And your question is, which SQL statement is used to extract data from a database? So your options are select, extract, open, get. Please do let us know your answers in the comment section below. And with that, let's get started. Now we enter the module 1. So the module 1 will be about the introduction to SQL and database basics. So what is SQL is our first question, and why is it important? So today, SQL in simple terms, or let's expand as structured query language, is the standard language used to store, manage, and retrieve data from relational databases. In very simple terms, SQL acts as a communication layer between humans and databases. Instead of manually browsing data through files or spreadsheets, SQL allows us to ask precise questions to the large data systems and receive accurate answers almost instantly. You can think of SQL as the grammar of data, because just like grammar helps us form meaningful sentences, SQL helps us form meaningful data queries. So through SQL, we instruct databases to perform critical operations such as searching for specific information, updating existing records, inserting new data into the entries, deleting or removing outdated data, and organizing information using tables, views, and schemas. Without SQL, interacting with structured data at a scale would be slow, manual, and completely error-prone sometimes. Now, why is it important? SQL turns raw data storage into an intelligent, queryable system that businesses completely rely on. Now, you might be wondering why SQL still dominates in 2026 despite hundreds of new technologies and tools and frameworks emerging every single year. So, the answer is SQL continues to dominate the data ecosystem in 2026 and in future because this is not by accident. Because SQL solves a fundamental problem: reliable access to structured business data, universal adoption. Every major organization, whether it's Google, Amazon, Meta, banks, hospitals, or e-commerce platforms, they rely on SQL-powered databases at their core. Even modern cloud-native systems ultimately store their most critical data in relational databases using SQL, and they also query that data using SQL. Next is standardized language. SQL allows ANSI standards, which means once you learn SQL, the same knowledge applies to MySQL, PostgreSQL, SQL Server, Oracle, Snowflake, BigQuery, Redshift, and many others. This portability makes SQL a career-safe skill that remains relevant across tools and companies. Next is essential for analytics and AI pipelines. In analytics and AI workflows, SQL is often the very first step. Before any dashboard, machine learning model, or AI system is built, SQL is used to extract clean, structured, and reliable data. In many ways, SQL is the foundation layer for data-driven intelligence. After that, we have high performance with massive data. Modern SQL engines are highly optimized and can process millions or even billions of rows of data in just mere seconds. Features like indexing, query optimization, and parallel execution make SQL extremely efficient for large-scale data operations. Now, the next question is, where do you see SQL in real life? Although users rarely see SQL directly, it silently powers many everyday systems we interact with. Whether you book a flight, withdraw some cash from ATM, place an online order, or check your bank statement, SQL queries are running behind the scenes. SQL also supports food delivery applications, telecom recharge history, hospital records, and customer support systems. Each of these systems rely on fast, accurate retrieval of structured data, which SQL excels at. A useful real-life analogy is to think of SQL as a remote control for business data. Successful learners who master SQL gain the ability to instantly switch to exact channel of information they need, whether it's sales data, customer retention, or customer records or transactional history, without delay or dependency on others. So the next one is types of databases. So we have two types: relational databases or RDBMS and non-relational ones. Let's get started with RDBMS. A relational database stores data in tables made up of rows and columns, similar to Excel spreadsheets, but with far more structure, rules, and reliability. Each table represents a specific entity, and relationships between tables are clearly defined. Relational databases enforce consistency through constraints and relationships, ensuring that data remains accurate and reliable even as systems scale. They follow ACID, or popularly known as asset properties, which guarantee transaction safety, making them ideal for business critical operations. Since relational databases are SQL based, they allow precise querying and strong validation and predictable behavior. Most popular examples include MySQL, PostgreSQL, SQL Server, Oracle, and MariaDB, all of which are widely used in enterprise systems. Now let's discuss the second type, which is non-relational databases, or simply known as NoSQL. Non-relational databases, commonly known as NoSQL databases, store data in formats designed for flexibility, scalability, and speed rather than strict structure. Instead of fixed tables, they often use JSON documents, key value pairs, columns, or graphs. These databases are designed to handle large volumes of semi-structured or unstructured data, and are commonly used in microservices, IoT platforms, real-time applications, and distributed systems. Some of the popular examples include MongoDB for document storage, Redis for key value access, Cassandra for column-based storage, and Neo4j for graph-based relationships. NoSQL systems trade strict consistency for flexibility and scalability in many use cases. Now, in the next stage, let's discuss the basic fundamental differences between relational and non-relational database systems. So, relational versus non-relational analytical comparison. Relational databases focus on structured data, predefined schemas, and strong consistency. They are ideal for transactional systems, reporting, and business logic where accuracy is critical. SQL serves as a powerful and standardized query language in this ecosystem. Non-relational databases, on the other hand, prioritize flexibility, horizontal scaling, and high-speed access. They allow schema changes without downtime and are better suited for rapidly evolving data models. A strong analogy is to think of RDBMS as a well-organized library where every book has a catalog number and fixed location. NoSQL is more like a creative studio where items can be placed freely based on immediate needs without any rigid structure. So, what is RDBMS? A relational database management system is specialized software designed to store structured data and manage relationships between different data entities. It acts as an engine that processes SQL commands and ensures data remains consistent and secure. An RDBMS is responsible for enforcing rules, managing user access, and handling backups, recovering from failures, and even ensuring that multiple users can work with the same data simultaneously without any conflicts. In short, the RDBMS is the backbone that makes SQL reliable, scalable, and safe for enterprise use. Tables represent real-world entities such as customers, products, or orders. Each table focuses on a single concept, keeping data organized and easy to manage. Next is columns. Columns define the attributes of an entity such as name, email, or city. Each column has a specific data type and rule set that governs what value it can store. Rows. Rows represent individual records within the table. Each row captures a complete instance of an entity, such as a single customer or transaction. Next is the primary key. Primary key uniquely identifies each row in a table, ensuring no duplicates exist and enabling efficient data retrieval. Foreign keys create relationships between tables by linking related records, helping maintain consistency across the database. Next is indexes. Indexes function like a book index, allowing the database to locate data quickly without scanning every row. Followed by that, we have constraints. Constraints enforce data quality rules such as not null, unique, and check. These rules help preventing invalid data entry entering into the system. Now, the next stage is why RDBMS is the industry standard. RDBMS systems are highly reliable and trusted for business operations that cannot afford data errors. They enforce data integrity, support normalization, and handle complex transaction workflows efficiently. Because of these strengths, companies use RDBMS platforms for mission critical applications like billing systems, HRMS, ERP solutions, inventory management, and logistic platforms. When accuracy, consistency, and reliability matter, RDBMS remains the preferred choice. Now comes the next stage where we will learn the installation and setting up SQL environment. So now we have come to a stage where we will install MySQL into the system. Now it's really simple. All you need to do is just type down MySQL Workbench on your browser, and then you'll be redirected to this particular page. Use the first link, MySQL Workbench, or you can also go with the download option. And here you have the download now option, right? So you can click on this and your installation file or the setup file will be downloaded for you. And you just have to run that particular file. It's a simple installation procedure. But if you have any queries, don't worry. I'll also drop a link to this particular tutorial on how to install and run MySQL Workbench. For now, we have already installed MySQL. So let me run that. So this is my database, which is SLP database. So you can see on the right hand corner of my screen, we have an option that says the position of all the prompts and all the sections of this particular workbench. So I'll go with the first option where I can see all the databases I have and the tables I have, right? So right now we are in the table that we earlier created for interview questions and answers. So this will be in the down the line. So let's go to any of the databases. I would like to go with this particular one, sample dataset. So I'll be using the SLP database. So we can test our SQL database in this way. You can start by selecting any of the databases. Don't worry, in the upcoming section or at the upcoming module, I'll explain you how to load the data, how to create table, how to insert the values into your table, and all those fundamental things. So first, for the beginning section, to test our SQL installation, we'll do this. So before you get into anything, you just need to select the database where you have the data. So you can do that by simple command which says use the database name. This is the font. So let's say use and database name. And you need to have a semicolon, right? So you can also see why I'm using specific format. I'm using, let me expand my screen. I'm using all caps for the keywords. In SQL, we have keywords and also the user defined words, right? So the keywords are something which carry a functionality. So here, if you see, we have a select, from, where, not in, right? These are keywords. They have specific functionality. And whatever the things you see in a black color, which have, case sensitivity in lowercase or sentence case, those are the ones which I define. So tomorrow, if my query gets a little more complex, so down the line, we will be learning subqueries and advanced querying functions where we should be at a stage where we should identify our own code. If you follow or some mixed kind of way to write your queries, then you might fall into a confusion understanding what is what. Is it a keyword, or is it a word that I define, or is it the name of the column, or anything, the name of the table which I define? So to avoid such confusions, we will follow this standard. If ever there is a keyword, just keep it in all caps. And if ever there is a column name or a table name, then you can keep it in mixed case or low case as per your requirements. So product ID, this particular name is a column name, so that I identify it as a column name, I'm using mixed case there. So it has a caps thing, and then the all small letters in that way. So basically, you need to select a database name and explain MySQL workbench that I'm going to dive into this particular database, which is SLP. And you can see I have complete access here. So if I expand this particular section, you can see SQL gave me a green to go, and then I can also check what are the tables present in my database. So for that, you will be using show tables, control enter, and these are the tables which I have: bonus, book collection, book order, clone, consolidated student information, employee details, etc. So now, if I want to understand employee details, what I'll do is copy this row, copy field, and then I'll simply write down a select statement, right? We will also understand what exactly does select from, and every aspect, every syntax of the statements in the upcoming module. For now, we are just testing the condition of the installation that we have done. So for that, so I'll be writing down select. So you can see when I type, you can see some auto suggestions, but don't take any auto suggestions. Follow a strict format for yourself. So select star, which means all the columns. So maybe I'll be having 5 columns, 6 columns in this particular data set or data table. When I indicate star, automatically MySQL Workbench will understand that user wants to query or extract all the columns from the table. If I dedicatedly provide, let's try that as well. So from, and remember the field that we copied, just paste it and remove the single quotes. And at the end, yeah, without semicolon, your query will run. But to follow a strict syntax, we need to enter semicolon. Now, let's hit enter to find out the entries in our data set. So we have 5 columns. You can see we have employee ID, employee name, age, department, and salary. So now, let's say I just want the employee name and their department. In that case, what I can do is quickly copy this and paste it somewhere here. And instead of star, I will write the dedicated column name, EMP name, comma. If your intention is to extract specific columns, then you need to specify them and separate them using a comma. Now I want employee name and department, so I'll write EMP name column, comma, separated, both are separated by comma, and department, right? So let me run this and I'll have, okay, there was some error. Copy field name and I'll paste it here. Yeah, I think that was a small spelling mistake, not to worry. Enter. There you go. So we have John Doe and all the other employees, Jane Smith and Michael Johnson, and their specific departments. Now let us understand something a little more detailed. Let's say the user wants to extract specific employees from IT department. How do we do that? We do that by adding a where clause. So these are clauses, don't worry. We're just testing it out. In the upcoming module, we will be going deep diving into each and every part of this. So where our department is IT. So since this is a character data type, it will be inside quotes. So IT semicolon. Remove the semicolon and everything is good to go. Enter. And we will have the details of all the employees who are in IT department. So this is how a basic query on a MySQL Workbench works. Now we have a briefing on the understandability and working functionalities of the MySQL Workbench. Proceeding ahead, we have the choice of SQL engine for learning purposes. So MySQL and PostgreSQL both are excellent choices. MySQL is known for simplicity and ease of use, making it ideal for beginners and web applications. On the other hand, PostgreSQL offers more advanced features and widely used in analytics and data engineering roles. Both databases are open sources, stable and production ready, making them perfect environments for learning SQL fundamentals. Now we have common installation issues and fixes. Beginners often face issues like port conflicts, authentication mismatches, or missing environment values. So these will be the common issues that you might be facing during the installation process. Don't worry, we will be linking the complete installation and setup video in the description box below. You can go through that and it will have all the mistakes and all the possibilities of creating mistakes and all the permutations and combinations of the problems that you might be facing in real-time installation. It's a completely detailed tutorial, so it might take a lot of time of this particular session. So for that purposes, we have created a dedicated tutorial for installation. So we will be linking that. Now, why these issues come? Because you might be having Jupyter Notebook or any other platform that deals with databases like MySQL as well. So you might have to dedicatedly create a port for their access. So if there is a port conflict or any kind of authentication mismatch, you might face these. So you have that all covered in that session. Understanding these errors early prevents frustration and builds troubleshooting confidence. Addressing problems such as 3306, which is a port number conflict, or PG admin setup, which is for PostgreSQL failures, helps learners become self-sufficient and comfortable with database tools. Now let's go through best practices for beginners. So some of the best practices are, you should learn always to create a dedicated practice database to avoid accidental data loss. Using meaningful table name and column names improve readability and long-term understanding. Backing up data before experiments and maintaining a personal SQL notes file helps reinforce learning and builds good habits from the start. And that brings us to the end of module 1, and next will be the module 2. So now we have entered module number 2. So this module number 2 gives us a brief introduction to the basic commands in SQL. So this is all about how to create a table, how to insert data into a table, and then when you start querying, how do you query, right? For a basic example, you have select. So select in SQL means you're trying to explain the SQL workbench that you want to select something from a table that you just created. So there might be many number of tables. For this sample execution, we're going to create 5 tables and you must specify which table are you focusing on, right? So for that, you might have to give SQL table name along with the select statement. And then what do you want to select? You want to select a specific column or all the columns available. So there are again specific ways to select the columns again. If you want any particular column from the table, you need to specify the column name. Or if you want to extract all the tables, then you don't have to write all the column names. You just write an asterisk and then all the values will be extracted for you. And if you want to filter out, let's say there is a condition where you want to filter out all the employee details where department is equals to HR, then you will go ahead with one filter query, which is where, right? That particular where is a clause in SQL. So this can help you understand how simple SQL is. It's just a verbal language. You talk to your database and you'll get the queries. It's as simple as that, right? This is what makes SQL so exciting, so resilient, so reliable, and so relevant to the current IT standards and industry standards wherever data is related to it. So now without further delay, let's start by creating a simple table, right? So now you can see on my screen, we might have to use the database first. I have already created a database on the name interview, and this particular database will be used by us in upcoming modules, maybe 2 or 3 times for interview questions and answers and joins. And for now, we are just working on the basic terms of creating and filtering data and extracting data insights. So I'll be using this particular dataset. And if you want to create a new dataset, it's really simple. You go to File, and here you create a new model, and then you add the names to your model and all those things. Or you can also go ahead with this particular option, create a new schema, and then you name your schema as sample schema test now, and then you can choose a default location and all those default things for yourself, and then apply. And then you create a schema if you want, apply, and finish. For now, I don't want to create this one, so I'll just close it. And once you create the schema, everything is straightforward, like we are going ahead with now. So once you create a database, you need to remember the database schema name. So now I've created this particular interview schema. So to begin with adding any of the tables or adding any of the data entries, I need to specify the database I'm using. So you can see on the left hand side, we have a lot of data schemas. We have car dealership, credit card data, interview, sample stop, right? This is the one sample schema test that we recently created, right? You can drop this schema, drop now. So we have removed it. That's the way you delete a schema if you want. Okay, let's take it as a learning step in case if in future if you wanted to delete any schema. So now I want to get the access to interview schema, or the one which I created already. So how do I get access to it? Again, SQL is really simple. You just need to write down use schema name, which is interview. Done. Semicolon. Now SQL understands, yeah, user wants me to use this particular schema on the name interview. So let me expand this so that you can see it better. I hope the code is visible clearer. So now you can select the entire query and use this particular flash logo to execute, or the best way I use is hold control and press enter. That is the best way, or a shortcut to select the database. Now comes the next step where you want to create a database. So again, let me tell you this. So we have linked this particular code document in the description box below. You can open up the code document and follow along with us so that you have a better learning experience. And I've also saved this particular code documentation on a notepad for quick access. But before going with the quick access, let us manually type the table names and enter the data or the insert commands so that we have a decent understanding. Let's go back. So the first table that we will be creating is departments. Now you can see this particular double code, right? If you have programming background, then you might have something called naming conventions or tagging or quoting, right? It will not be executed in real time, but it will act as a note or a sticky note that you leave on your code, so any of your fellow developer understands what's happening here. So I'm using these double hyphens here as a quote so that my fellow developer will understand. That I'm creating a data table which is named as depart. So the simple command for this is create. So you want to create something, so you just write create. What do you want to create? I want to create a table, right? So you can see that whenever we write something, we are using, or I'm using, a separate naming convention. right? So here you can see I used uppercase for the keyword use. So anything which is getting highlighted as in a blue color is a keyword. A keyword has a dedicated meaning and it cannot be used for normal purposes. It can be used only for SQL purposes only, to make SQL understand what is your step or what is your intention. So use uppercase for all the keywords and use mixed case or sentence case or lowercase preferably for your names, right? For the table names, for the column names, for the row entries, or anything which is from your end. Basically, anything which you are giving, the users which you are giving to SQL should be in lowercase so that you can differentiate. For now, we are just trying to write 2 or 3 lines of code, 2 or 3 lines of query. That is easily understandable. But in future, you will be writing subqueries, you will be writing joins, and a lot of more complicated queries where at least you'll be writing 10 to 12 lines of code. In that particular scenario, you must be capable to understand which is a keyword and which is a user defined word or a name or a column name, right? So a metadata basically. So that's the naming convention you should be following. So understand what's the difference between a keyword and what's actually the name that you have given to your column name or a table name, which is basically user defined. So you can take it in programming terms, which is user defined, which is internal implicit design, right? Implicit function. So I want to create a table. So write create table. And what's the table name? So my table name is departments. So this is my table name. So what do I have inside my table is my next question. So inside my table, I want to have a couple of columns. Let's say 2 columns, department name and department ID. So for that, I need to write down dpt ID and data type is integer. I want to provide integer data type for it. So basically, before we continue, let me tell you something. So whenever you want to add columns, you need to add column name. Okay, let me comment this. Column name along with its data type. So this is a set. So whenever you try to enter a column name, you should follow this particular approach where SQL understands this is a, it's a combination. It's an entity which is made of 2 things: name of the column and what's its data type, right? So this is the naming convention that you should be following. So I want department ID as the first column and the next column is department name, right? So for this particular department name, I want to go ahead with varchar, and varchar is also another data type. And for that data type, you can allocate number of locations to save that particular department name. So for a basic request, I think I'd like to go with 50 character spaces, and that should be good enough for writing my department names. And then you can close the command and write a semicolon to end the query. So your query will run without a semicolon, but for safer programming practices, consider it as a protocol so that you or any other developer who is reading your commands will understand that it is the position where this particular query ends. So use a semicolon for that. This is pretty good, but remember, we might have to work on joins in the future modules. So joins is nothing different from the VLOOKUPs or the relationships or the data modules that you have seen on Power BI, Excel, etc. Basically, you're combining 2 or 3 different tables together. Let's say you are ordering something from your online websites, and for getting that particular product to your location, you're providing your address, phone number, and all the details, right? So in a similar way, when you want to access data from a different table, you might have to establish connection between them. So to establish a connection between the 2 tables, you might want something called as a primary key and a foreign key. So primary key and a foreign key act as phone numbers or an address location, or basically something which establishes a relationship between them. So now this particular thing you need to understand. A primary table in one table is the one which connects with the same primary key in another table. But in the other table, it is termed as a foreign key. In my table, department ID would be the primary key. It will be unique and it will not be null. And this particular department ID can also be another table. It can also be unique, it can also be not null, and it will not be empty. But in that particular table, it will be termed as foreign key. The same primary key in a different table is termed as foreign key, but the same primary key in the dedicated table is termed as a primary key. So now I want to term my department ID as the primary key in my table. For that, you just need to write one more sentence here, not even a sentence, one more word. You just need to specify primary key, and that's done. So primary key and done. Now what happens is SQL will understand you want to create a table and the table name is departments, and you have one department ID column, two department name column, and the data type for department ID is integer and the data type for department name is varchar, and you have provided 50 spaces or 50 data spaces or addresses for you naming your department name, right? And out of which department ID is the primary key. So these are the details that you have given to your SQL workbench, and you should be ready to create a new table. So now let's head back to the notepad where we had created the code. This is the one. So create table departments ID is equals to int primary key, department name is varchar, 50 locations, and semicolon. So only difference is there are some indentations done. So what is an indentation? Just like any other programming, you also provide dedicated spaces, new lines, so that the fellow developer understands where is what. So this is the indentation we have followed here. We are creating a new table, departments, and the first column is department ID. It is an integer data type and it's considered as the primary key. The next column is department name. Its data type is varchar, which is a character data type. We have provided 50 spaces, and then end of the command. Right? Now comes the insert command. Now, again, similar to table creation, inserting data into a table is also simple and easy. So all you need to do is specify the operation that you want to do. It is insert. I want to insert data, but into which table? So I want to insert into table which is departments that we recently created. You can simply copy and paste the departments table name here. And what are the department columns you have? So I have two columns there. I'll take department ID and department name. And now these are the values I want to insert. What are the values? So again, comma separated values. The first is ID, so you don't have to write any quotes. But the second one is varchar, so character data types must be specified in single quotes. So this is the first entry, comma separated values. The second one is number 2, comma, single quotes, and what's the next one? Maybe engineering, and again a comma separate. And third team could be finance, separate by comma. Fourth team can be marketing. So I don't have any further rows here. So what I can do is I can close this particular indentation. And write a semicolon to explain the end of this particular query. So now, similarly, you can just execute this and add the values. So let's head back to the notepad. So here you go. So this is a similar approach what we have mentioned here on my MySQL workbench. You can follow this indentation so that you are clearer. And you can just simply run the query. I'll use Control Enter, and these values are entered into your table. Now I want to extract what are the values that I have entered into my table, or I want to just cross verify if I have entered all the values or if the values that I have given are properly inserted or not. So for that, you want to select. So as we discussed, there are multiple ways to extract data. You can just specify the column names from which table. The table is departments. Or you can specify dedicated column names. Let's say I want to only extract the department name or department ID. You can also do that. Or another approach for the same code is this one. You don't have to specifically mention the column names. You can just write down an asterisk and it will still execute the same. So let's try all these 4 commands. You have your data here. And the same works for this one as well. Now, let's say I want to select only a dedicated column. So these are your department IDs and dedicated department names. This is your department name. And now, if we drill down further, let's say I want to extract the details for only HR team. So this is where the where clause comes into the picture. So extract or select department name where. So this is basic fundamental queries that I'm really writing right now so that you understand how it actually works in the background. So you understand the workflow of it. So where department ID is equals to, let's run this, department ID 4. So 4 is marketing. So department ID is equals to 4. So what happens is SQL selects the department name column altogether. The entire department column is selected. First, it will go to the departments table itself. It has 2 columns. One is department ID and a department name. You can see it right here, right? So this particular entire table is selected by SQL. And then it reads what are the columns I need to select. So we are dedicatedly specifying just one column, which is department name. This particular column will be selected in the second phase. The third phase is where it applies the filter for department ID. Now, again, it goes to department ID and it checks individual department numbers. So it will go for the department ID where it matches with number 4 and then adjacent to it is marketing, right? This is what we are trying to extract. SQL has understood this and it will give us the marketing team name. So this is how the query works in the background. Now that we have a basic understanding of how the fundamental keywords in SQL, which are select, from, where, filtering things, right? Basically how to create a table, how to insert values inside a table, and how to query them. Now we will proceed and add a few more tables onto our MySQL workbench so that we can get continued with further queries like some aggregate functions like average, sum, etc. So let's not waste much time. Let's go back to the query window where we have all the table details and copy them and simply write them. So let me copy the entire 3, 4, 5 tables and paste it on the SQL workbench here. I'll minimize this a little so that we have a better view. There you go. So this is our second table, which is employees table. Now, before we create the table, let me explain you a few things. So we have about 5 tables. One is departments, second is employees, third one is users, fourth one is orders, and fifth one is sales. In the terms of data analytics, in the terms of business analytics, we deem these tables as 2 parts. The first one is fact tables and the second one is dimension tables. So what are fact tables and dimension tables? We will deep dive into these in the next upcoming modules. So basically, it's nothing but relationships between the tables. So there will be one table which is related to all other tables in the database, right? So in this particular scenario, the employees table is a fact table and employee is the one which works in your company. Let's say you have an online store and you have a list of employees, and these employees are the ones which receive orders from the users and they fetch your inventory, pack that order and send it to the users, right? So employee table is the fact table which is related to the orders table, which is related to the users table, which is related to the inventory table, which is related to the department table, right? It connects to all the tables. And on the other hand, the dimension tables, these are related to your fact table based on one foreign key. right? You will be having employee ID, right? This particular employee ID will be the primary key of your data table, and somewhere or the other, the employee table will dedicatedly have a department value, department ID, right? It will have the order values, the order ID, it will have the sales ID, right? All these entries will be in the fact table, and all these entries will be the primary keys of all the dimension values, right? The dimension tables. These values will connect to the fact tables. So it will be a little confusing now, but when we enter into the data modeling module, there you will have a clearer understanding. For now, let's understand one thing. You just have different types of tables. One is fact table, one is dimension table. Fact table is really important because fact table acts as the mother of all the other tables, and all the other tables are connected to fact table. If you delete the fact table, then there is no way you're going to perform the analytics in future, right? It is like the root. Just understand that basic thing. Now let's continue with table creation. So now let's head back to table number 2, which is our fact table here, or let me tag it as the fact table for reference. Now the same pattern again. We want to create a table. So create command, table command, provide a name to your table, which is employee. And here we have 1, 2, 3, 4, 5, 6 columns. We have employee ID, we have employee name, we have salary, we have department ID, on which date was he or she hired, and the department ID, right? So here we are dedicatedly specifying that department ID is a foreign key which relates this particular fact table to the departments table, and we are referencing this, right? So references is the keyword which helps SQL identify that you are trying to connect this particular employee data with the department data, right? So we have about 5 columns here: employee ID, name, salary, department ID, and hire date. And if you are trying to get this connected with another dimension table, then this particular command where it says we are trying to use department ID as a foreign key, which happens to be the primary key of a dimension table, which is the table name, departments, and in that particular table name, the column name is department ID. It is named as department ID. So please go to the departments table, refer to the department ID column, and then match the entries of department ID from employees table to the department table. So this is how it works. Now let's click the flash logo, or I'll go with my shortcut Control Enter, and we have successfully created the employees table. And similar to the previous approach, you need to specify the keyword insert. I want to perform an insert operation, and I want to insert these elements into is another keyword, and you need to provide the table name, which is employee. And now what are the columns I have in my table? I have employee ID, I have employee name, I have salary, I have department ID, and hire date. So based on the column names, I need to specify the data entries as well. So you cannot mix and match. You are specifically providing the order in which the entry should be happening. So the order is: first comes the employee ID, second comes the employee name, third comes the salary, fourth comes department ID, and fifth is the hire data. In the same fashion, your entries should also be matched. So first, the employee ID is 1, the name is Alice, the salary is 90,000, department ID is 2, so she belongs to department whose ID is 2, right? If we go back to department here and execute this, so we will be having engineering in the department ID 2. So Alice belongs to engineering department, and then comes the hire date, which is this one, right? So you need to specify the data type. So here I have specifically provided the data type as date for hire date. In the same fashion, rest of the employees, employee ID 2, 3, 4, 5, 6, 7, and 8, 9, and 10 are added, right? And deliberately we're also adding some null values here. So you'll understand why we are adding null values, because in future we will be performing some join operations in the upcoming modules where we will try to filter out the employees whose department is not yet allocated. We are considering these employees are new or fresh hires, so they are on bench period and they are not aligned or assigned to any projects as of now. So they are having their department ID as null. So we'll be performing such operations. For now, just try to, here I think I've marked it, no department, right? So for now, just try to create a table and add data. So now your fundamental job to do is you need to understand how to create a new schema, which I've explained before. Go to the schema table here, create new schema, and write a name to your schema, and then apply it to create a new schema, which happens to be a dimension table, and this will be related to the fact table, which is our employees table, right? And here I'll be having user ID, email of the user, and at what time was the account created at timestamp, right? Now control enter, and we have created this particular users table. And similarly, we will insert the data into users table. So we will be following the same pattern. So we will be inserting into users table, and these are my values. Let me indent it. So proper indentation will help you understand how your tables are organized. So you can follow this. It might take a little time, but in future it will definitely save a lot of your time entering or making mistakes, right? So this is a good practice or best practice. Now I have about 10 users in my database. And then this is the end of the query. So here you can see I've also tagged as duplicate email entry. So this will be another learning experience for us, where we will try to find out duplicate email entries in our database. Now hit Control Enter. I think we selected employees data table. We were supposed to select users data table. Yeah. Okay, we were supposed to create the data table first. Okay, we have successfully entered the elements into the users table. Now comes our fourth table, which is orders table. Similarly, we have order ID, customer ID, and order date. Control Enter, and we have created the orders table. Let's quickly add all the data into the orders table. You can also follow the same indentation, or if you want to have a particular specific format of indentation, you can also follow that. We have the last table, which is sales table, and similarly, let's enter all the data into sales table. Now let's check all the entries or all the tables. The process is simple, like we discussed. Select star from employees. There you go. So these are the employees and their details. And similarly, you can just quickly copy and paste this command and rename this to departments and run a query, and you have all the employees or department details. Similarly, you can copy paste, and then you can use the name of sales, orders, and users. And I'll also have orders, and also I'll have sales. So these are the user details that we have entered, and these are the timestamps when a user account was created, and these are the order details. So these are the orders placed on what detail, on what date, and who was the customer and who was the order ID, and all the details of that. And sales data table, what was the sales ID, on what date was the sale made, and what's the amount they paid, right? So these are the details that we needed. Now let's take a step further and try to extract some details from this particular data set that we have just created. So I'd like to close it here. So far, this is the creation and insert process. Let's comment it. Now let's proceed further, and this would be the querying stage. Now let's try the filtering process. So let's consider we want to filter the details of employees who are earning, let's say 90,000 or more. So how do you extract it? Let's take a moment. So far we have a basic understanding of how to insert data, how to select queries, right? And we also went through a sample where statement where we extracted the marketing ID, right? So the department name where marketing or department ID was equals to 2, right? So following the same approach, can you devise a quick query? Yes, I think you already have a rough template on your mind, but it's okay if you don't have it. So let's get started with it. So as we discussed before, SQL is really simple. All you need to do is just explain SQL in very simple terms. I want to select. Select what I want to select. I want to select employee name, or I want to select everything from employee, where from employee. Let me copy the employee name to save time. This is the table name from employees, where salary is greater than a rough number 90,000. So before that, let's run this query and see. We have Alice, we have Bob, we have David, we have Eve, we have Heidi, and we have, yeah. So there are a few employees who are drawing salary greater than 90,000. Let's say it as greater than or equal to 90,000. So we must be getting a couple of entries here. So let's quickly run the command, control enter, and there you go. So we have about 1, 2, 3, 4, 5 employees, Bob, Alice, David, Eve, and Heidi, who are withdrawing salary which is greater than or equal to 90,000. So this is one of the good filtering examples. Now let's go with a few other queries or filtering queries. So we have HR, we have employees, we have users, we have sales, we have orders. So let's say I want to extract employees who were recruited after February of 2025. So for that, we can use the same query. We can quickly copy and paste it here from employees where join date, right? So I'll execute the select query once again. So I'll copy this particular field name and paste it here is greater than or equal to March. We don't have a March, but we can take the September. We can copy this particular field and paste it here. There you go. So any employee who is hired after September 2025 should be highlighted. Enter, and there you go. We have about a couple of employees who were recruited after this particular date. Or you can also find out less than who are the employees who were recruited before this particular date. There you go. So only David was the one who was, maybe this can be considered as David is one of the senior most employees in this particular organization. Now, let's proceed further and try the next type of query, which is the sorting data. Now, I want to sort the employees table. Let's say now I want to identify employees in terms of salary. Who is the employee who is drawing highest salary and who is the employee who is drawing the least salary? I want to order them in decreasing order. So it's really simple. You can use the same query here. Select star from employees and order by salary DESC. So we have two keywords, DESC and ACSC. So ACSC is ascending order, BESC is descending order. So you just need to run this query and we will have salaries of the employees who have highest salary numbers. So we have Bob, David, Heidi, followed by that we have Eve, Alice, etc. And Ivan is the person, maybe he's a fresher, so he's drawing the least intern level salary or the beginner level salary, which is 50,000. And similarly, you can follow another thing here. you might be assuming, can I give two columns here? Yes, you can give two columns. Order by DEPT. So let's go with department ID. So this even works for character data types as well. Department ID ascending and salary descending. So you need to separate this by a simple comma, and there you go. Enter. Now what happens is, you can organize the department ID in increasing order and organize salary from descending order. So it's just executed for the reason to understand if this particular order by sorting command executes for one or more columns or not. So the reality is it works for one or more columns. So that's the basic understanding. Now we need to understand one more thing, which is filtering out with limits. Let's say I want to find out only one entry which has the highest salary. So in that particular case, what I can do is I can make use of limit command, which limits the number of rows output by one or two, number of, a number, dedicated number. If I just want one entry, I'll have just one entry. In case I want to have top 3 employees, I can provide top 3 as limit 3, and you'll have top 3 rows executed right here for you. So this is where we come across the limit function. And apart from limit, you also have another function which is called as distinct. So the name speaks for itself, unique entries in the row. So for example, let's say I want to find out, let me use the same query, select star from employees, and I'll replace star with distinct department IDs. Copy field name. So what it does is, for understanding what it does, we need to copy this statement and paste it once again, semicolon. Now what's happening is, when you enter this particular query, you have multiple departments. Let's say department number 2, engineering department, is repeated multiple times. But now I don't want to extract all the employee details. I want to just know how many number of unique departments are present in this particular employees table. So in that particular scenario, I need to provide a semicolon to follow the principles or best practices. So here you see we have about, okay, I think for distinct function we might not need semi double quotes. Okay, I think I made a mistake in keyword. Yeah, there you go. We have 1, 2, 3, 4 distinct department IDs and one null. So that is from the employer to which we did not assign any team yet. So that's one thing. And now if we continue ahead, we have aggregate functions, which are basically the average, sum, count, minimum, max, and a few other basic aggregate functions that you use on a daily basis. So for basic aggregate functions, I'll just quickly copy and paste the comments here so that we save time and spend that time for understanding how the query is performing. So here we have the first function, which is counting the number of employees. So basically we'll start with the first aggregate function, which is trying to calculate the total number of count of total employees in this particular data set. So we are using the count function, and here you can provide a dedicated column name, or you can also provide the star logo, which basically calculates the entire rows here. So just enter. Then you have about 10 employees here. Now the next aggregate function is, we will be trying to find out the average salary of an employee from a specific department, which is engineering. So for that, let me expand this again. So for that, first we will be calling the columns from this particular table, which is employees table. And since we are also dealing with a specific department, which is engineering, we need to perform a join operation where we will combine both employees and department tables together based on one keyword or one column, which is department ID. So department ID will be a primary key for department table, and department ID will be a foreign key for employees table. So based on this foreign key, meaning the employees table will be able to get joined or connected with the department table based on this particular department column, department ID column. Now, so our statement is simple. We are selecting average of salary and we are aliasing it as average engineering salary from the table employees, and we are joining the employees table with the departments table on one common column, which is department ID. Departments dot department ID is equals to employees dot department ID. So departments is the name of the table and employees is the name of the table. So in this particular table, I'm referring this particular column and I'm trying to connect to this particular column in the next table where department name is equals to engineering. Now let's execute this particular query. There you go. So on an average basis, the salary of any employee working in engineering department is 1,08,750. So this is the average salary of any employee who's working in engineering department. Could be more or could be less based on the designation. If he's an intern or a beginner, then the salary might be less. If he's a supervisor or in a senior position, the salary might be more. It's basically an average of both. Now, the next aggregate function that we will be dealing with is the maximum and minimum. So for finding out minimum number, you can use a function in SQL which is called min, and for maximum, we can use a function called max in SQL. So it's as simple as that. Minimum of salary as minimum salary, maximum of salary as max salary from employees table. So let's quickly execute this query. There you go. So we found out the minimum salary of any employee in the entire company is 50,000 and the maximum salary in the entire company is 1,20,000. Next comes the last aggregate function in this particular domain, which is count function. So we will be selecting a department ID and we will be counting the total number of employees per department, and we will also name it as employee count from the table employees, and we will be grouping it by department ID. Let's enter. There you go. So we have one employee who has no department assigned, maybe he's an intern, and department ID 1 has 2 employees, department ID 2 has 4 employees, department ID 3 has 1 employee, and department ID 4 has 2 employees in it. And with that, we have come to an end of this module, and we have understood the basic functionalities on how to create a table, how to insert a table, how to select or extract data entries from a table, how to filter data using where clause and having clause, and we also learned grouping, aggregate functions, basically all the fundamentals to proceed with the upcoming modules. And with that, we transition to the next module. So now we enter module number 3, which is about understanding SQL data types and operators. This particular module will help you set the stage for all the basics. In this module, we will be diving into something absolutely fundamental, something every single SQL developer, data analyst, and database engineer uses every single day: data types and operators. Now, I know what you're thinking. Data types? Operators? Isn't that basic stuff? Yes, it is basic. But it is also the reason behind almost 70% of SQL mistakes that beginners make. Wrong data type breaks queries, slows down performance, and causes corrupted results, and even sometimes crash the entire production system. I've seen senior developers accidentally storing dates as text and then wonder why the database can't sort December properly. So in today's chapter, it's not just theory, it's how not to break your job interview or your database. Let's dive into this section. The first step is understanding SQL data types. Before we even start to write a single query, SQL forces us to follow this one golden rule. Every piece of data must have a type. Why? Think of a database as a massive warehouse. Data types are the labels on the boxes. Without labels, the warehouse becomes chaos. With accurate labels, everything is fast, searchable, optimized. SQL databases rely heavily on the data types for storage, indexing, comparison, sorting, and performance tuning. Imagine a library where books have no categories. SQL without data types feels exactly like that. Now let's break them down. First one, numeric data types. We have integer, or it is also specified as int, which is used for whole numbers. Great for IDs, counts, quantities. For example, age can be stored as integer. Product ID can also be stored as integer. Quantity, the number of items ordered. Now it's a small story type. In one of my early projects, someone stored product prices as int field. So the price was $99.5 or 99.5 rupees. So the total became 99, ignoring the 50, right? Or the decimal value. Now, what happened because of it? We lost precision and the entire billing report was off by lakhs. Lessons learned: use the right data type. Now, the right data type was numeric type or a decimal one. So, this is the superstar for financial data. P is equals to precision, total of digits, and S is equals to scale, which is digits after decimal. Now, for a simple example, consider this one. Decimal 10, 2, up to 10 digits and 2 digits after decimal. The maximum value is 99 millions dot 99 decimal values, or one decimal value less than 100 million. Now, real world use case: salaries, prices, taxes, rates, weight, percentages, etc. Next comes the float or double data type. It is used when you need very large or very small numbers, but some precision may be lost. Think scientific data sensors, machine learning scores. But don't use float for money unless you want rounding problems or angry accountants calling you. Now the next data type is character data types. We have char function n for fixed length string. Always use the full allocated space. Let's consider country codes where you have some country codes for that. For India, you have IN. For US, you have US, and you can also have gender, which we have M and F. For example, country code, character data type, two values. And the second one is workchar, and it is one of the most commonly used ones. It stores variable length data, and some of the use cases to consider as names, emails, city names, product descriptions, etc. A small story again. Once I saw a table with workchar and the limit was 5,000 for storing the first names. First names alone. Imagine allocating 5,000 characters for storing just a three-letter word like Max or Raj. Now, what are the lessons learned here? Proper sizing matters for performance. If you store 5,000 characters for just three letters, your space is wasted. And this might affect your performance. Now, the next data type is text. Text is used for large bodies of text. Blogs, descriptions, comments are a few examples. But avoid text whenever a reasonable workchar works in place of text. It cannot be indexed efficiently. That's the problem. Now, the next one is date and time data types. SQL is amazing at working with time-based data, but only when the data is stored correctly. For example, dates are stored only in year, month, and date types. You can see on my screen we have YY, YY, MM, and DD as the format. This type of formatting is perfect for birth dates, join dates, attendance logs, and a lot more. Next is time, and time stores only time. And after that, we have date along with time function. This can be represented as date time together or also known as time stamp. This stores date along with the time. Now some of the use cases: timestamps, log entries, attendance tracking, transactions. A mistake I've seen too often is people store date time as varchar, right? A data type change completely. And then sorting goes like 2024 1 or 2023 12 1, 2024 110. Completely messed up, right? Now, this can be solved. You just have to change the data type, and also we'll go through some examples in the real-time use case where these type of issues are addressed. Moving ahead, we have the Boolean data types. So the name stands for itself. It is either true or false. Some of the examples is active, is verified, is published. Never store Booleans as workchar. You might be wondering, why cannot we use workchar? It is just simple yes or no. Reason: if you use workchar, it wastes space and breaks the filtering logic. That's the main problem. Proceeding ahead, we have the next data type, which is binary, and miscellaneous data types, which is blob. This particular data type is used for storing images, PDFs, videos, JSON files, and they store semi-structured data. Modern SQL feature: JSON is a lifesaver when you need flexibility without completely switching to NoSQL. Now let's go to the next section where it will help us to learn the arithmetic operators and other functionalities. Operators help us calculate, compare, and manipulate data. Let's start with the easy ones. The first one is arithmetic operators. Just like math operator, operator meaning example, addition salary plus bonus, subtraction price, discount, multiplication, quantify, and division, modulus, etc. Now let's go through a simple example query. So you can see it on my screen. Select product name, sales, quantity into rate as new sales from Excel data. Now the real-time analogy. Operators like these are calculator inside SQL. Instead of exporting data into SQL, SQL helps you compute right inside the database. Now let's also go through a real-world scenario. Imagine a store wants to compute total revenue, discounts, tax calculations, profits instead of running separate scripts. A single SQL query can handle all of these arithmetic operations. Now, let's dive into section 3, logical operators. Logical operators help SQL make decisions like, should this row be included? Does it match with condition? Is it true or false? Followed by that, we have AND operator. All conditions must be true. For example, where salary is greater than 50,000 and department is engineering. You can see that query right on my screen. Followed by AND, we have OR operator. Any of one condition should be true, where city is equals to Mumbai or city is equals to Delhi. So this selects all the entries from the cities of Mumbai and Delhi. You can see a sample query on my screen. Followed by that, we have NOT operator. This exactly reverses the condition, where not country is equals to India, and this particular query is on my screen. So you can see any other data apart from India. Logical operators like filters on YouTube, language is equals to English, duration less than 10 minutes category is equals to technology. SQL just filters rows instead of videos. Now we land into section 4. So this particular one is based on between, in, and like operators. Sometimes we have another one as well, which is called I like, which is the opposite of like. These are the operators you will use every single day. Now another one is between operator. So this is used for ranges. For example, columns between value 1 and 2. For example, you can see it on my screen. Select everything from Excel data where row ID is between 10 to 20 or 10 and 20. Now, what this query does is it will eliminate any rows before 10 and it will eliminate any rows after 20. Only the rows between 10 and 20 are executed and shown to you. Now, a friendly tip. Between is inclusive. It includes both the boundaries, which means 10 and 20 are included. They are not excluded. Now, let's dive into the next one, which is in operator. Instead of writing many OR conditions, you can just write one in condition and write the set of cities. For example, you might want 3 or 4 cities. So what you can do is where city is in and the function, inside that function, you can write the city names. For example, Mumbai, Delhi, Hyderabad, Bangalore, and many more, right? Whenever a city name matches with the elements present inside the in function, that particular row entity will be selected and displayed for you or filtered and displayed for you. Now, followed by that, we have like operator and pattern matching. So you'll have a modulus sign or wildcard, which represents any number of characters. And the example is right on my screen, where name is equals to or name like modulus A and ends with a where name like modulus sign an modulus sign. So contains an as a wildcard. So any name which has an included in it, and it might have anything in front of it, it might have anything in the right hand side of it or the end of it. So whichever text has an inside it, all those text values will be extracted and displayed for you. Now in the section 5, we will have a small practical story or a real world analogy. To make this chapter sticky to your memory, let's run through a few stories. The first one, date disaster. An HR system stored join date as varchar. So sorting by join date gave Jan 10, Jan 2, Jan 25, Jan 5. Why? String sorting treats 10 as smaller than 2. Solution? Convert varchar to date to fix everything instantly. Moral? Always pick the right data type. Let's also go through story number 2. The like operator that saved a scale, an e-commerce company needed to find all products with Pro in their name. iPhone Pro, MacBook Pro, GoPro. One more simple query where product name like modulus sign Pro modulus sign. It can have anything before Pro, it can have anything right hand side of or the end of the Pro. So basically any text which has Pro included in it will be displayed. So what's the result? Marketing team recovered thousands of lost sales because these products were mistagged. Now comes the section 6 where we will have some demos. Here are some fully explained queries for learning purposes. So we will be diving into MySQL Workbench and start executing commands. So now we are on MySQL Workbench for running all the examples that we discussed previously. So my data is in sample database. So we will be using the use database keyword. Let me expand the screen. And the name of the database is sample. So we are in a sample database right now. And we have to show the tables that we have. Again, the keyword. You can see that MySQL Workbench is showing us some recommendations, but we don't want any recommendations. We should go with what we have. Now, apart from that, we want to see what's inside this particular table. So, yeah, Superstore. So we were supposed to go into Superstore, not a problem. So this is our database name and show tables. We have checkpoint data, we have complex post view, and this is the Excel data we need to work with. So now let's type a command, select star or everything from Excel data so that we have an information on all the rows and columns that we have to deal with in this particular execution. So we have row ID, order ID, date, shipment date, customer ID, and everything that we need to know. So now we will execute some sample queries to understand the functionality. So let me write down the demos that we want to execute. So the first demo is about finding employees earning between 50,000 to 100,000. Right, this is the first query. Let's leave a little space and also write down demo 2. And what's about the demo 2? We need to search city names. So these are the examples that we discussed before on the go, right? So containing PUR. So it can be Nagpur or any city which has the letter PUR in it. So it took an auto recommendation, or instead of PUR, you can also have anything like DEL, right? So now let's go with the third demo, which is show products with price calculation. And demo 4 will be about list users from specific cities. Demo 5 will be about employees not in HR department. Or we can also make some changes to this based on the dataset that we are working with. So we can go ahead with the segment here. We have segment in, we have which are not in segments of consumer or anything apart from consumer and home office. In specific segment, let's go with the consumer. And lastly, demo 6, which is about items with exactly matching some words, like let's say OUR, or let's say instead of exactly matching, we can consider this as text matching. So we have a template or a skeleton of what demos are we trying to execute here. Now let's start with queries. Now I want to find out any employee or any of the products. So we have number of pricing, right? So we should go with the sales here. So let's identify sales which are more than 3,500. So between 3,500 to 4,000, or sales. Find sales between. So this is a requirement. So what we will write is a simple select statement. We will select everything or select a specific product name. So we will go with the product name. So what I'll do is I'll simply copy this field name. I'll paste it over here, comma. I want sales column as well from Excel data. Where sales is between 35 and 4,000. Now we have the list of products that are having this range of sales. So we have about 5 or 6 entries which have the sales in between 3,500 INR or dollars to 4,000 INR or dollars. And now let's go into the demonstration 2 where we wanted to find out city names containing PUR. So if we go back to our Excel data set, we had a column which had the address, right? So we had cities like Leeds and a few other things, Paris, Parla, and all those things. So I want to find out any city name which has some given text. For example, if you go with Munich, so we have MUNICH, right? And we have Naples here. So APL or APL. So any state or any city which has Hamburg, etc., right? So any state which has AMB, I want to extract it, right? So let's write down a query for that. Select city from Excel data where city like, since we're using a keyword, let's have like, and since this is a text related data, we need to encode in between single quotes and we want Hamburg, right? So AMB and anything after AMB, semicolon, enter. So now we have any city which has AMB included in it displayed here. We had Cambridge, we had Hamburg, and all those city names which has AMB included in the text. Now let's go with the demo 2. We wanted to show the price calculations. So we have, let's execute this one more time. So we already have sales data, right? So if we go back here, let me scroll it. So if we go back here, we have the rate of every single product and the number of quantity. So the rate for single unit was $24.4 or rupees, and multiplied by 3 times, you have 79.2 as the final price, right? And now I want to calculate that once again. Let's say we didn't have that sales tag or sales column. If we wanted to calculate it, how would you do that? That's the problem, right? So we can do this by the following application of the formula. So what you can do is write down, select. What we want is product name. So I'll just copy paste this particular field name here instead to avoid any kind of errors. Comma. We also have sales, right? So let's keep sales, comma. We have quantity star. Let me copy that. Quantity into price. We have rate here, so we'll copy this rate name, paste it here, and we'll alias this as new sales from Excel data, semicolon, enter. So now we have all the product names and the sales, and new sales. Remember the one which we discussed, decimal points? So we did not, kind of constraint to, minimize the number of decimal points. So it gave the full potential of decimal points here. So we could, include a new column with mathematical or arithmetic calculations to go ahead with. Now, the next demonstration was about including all the details about a specific segment. So, list users or list products. So what we can do is, again, a simple select statement, star from Excel data, where segment in. So we want the following. So we have segment as corporate, we have consumer, right? So I want, let's say, corporate and consumer, comma, consumer. So since these are text-based data, so we need to include single quotes as well. And a semicolon to close the data. And there you go. So we have also, you can choose to include only a specific segment, but overall we have filtered the data to include only corporate and consumer related data set. Now, if we go into fifth, so data of the not in segment, so all you need to do is a simple change. So you can copy this and paste it over here as it is, and simply replace in with not in, and there you go. Now you'll get all the data which is not from the section of corporate and consumer. Run that, yeah, there you go. Okay, there was a small error mistake, corporate, and we could also include corporate, separate by comma. There you go. Now let's execute this command. And now we only have a home and office depot related data segment. So that's how you can filter. And the last one is nothing but text matching. So where we wanted to find out the products which have this particular, naming convention. So it's similar to this one which we executed before. Select city names which have this following text matching. So instead of AMG, you can go ahead with any of the other city names like MIL or ILA. So you'll have any of the cities which have ILA in that. This is the list of the cities. And now with that, let's close this particular section with pro tips and best practices. So let's wrap it up with some practical wisdom. First, never store dates as vocab. This is the number one beginner's mistake. Use decimal for money, not float. Float introduces rounding errors. Third one, keep vocab length realistic. Avoid vocab 5000 unless necessary. Next one is use in for clearer queries instead of many ors. Fifth one is like with leading wildcard, and it is slow. Avoid it in large tables. Sixth one is Boolean fields, make filtering faster and cleaner. Seventh one is use int for IDs fields, not vocab. Eighth one is understand indexes before using like frequently. And the final summary. In this chapter, you learned why data types matter more than most people think, how numeric, character, date time, Boolean, and advanced types work, how arithmetic and logical operators really behave, how between in like help simplify filtering, real stories that highlight how crucial good data modeling is. Now let's also go through some professional best practices you can use immediately. With this foundation, you are now ready to write cleaner queries, avoid common mistakes, and handle real-world SQL tasks confidently. In the next chapter, we will start leveling up with constraints and advanced filtering logic, which is where SQL begins to feel powerful. Stay tuned and keep practicing. Module 4, Safe Deletion Practices and Best Practices for Data Entry in SQL. Before we talk about writing advanced queries, joins, or analytics dashboards, there's one uncomfortable truth every SQL professional must understand. The most dangerous SQL queries are not the complex ones. They are the simple queries executed without thinking. And among all SQL commands, there's one command that has probably caused more panic, data loss, and late night emergency calls than any other. And that command is delete. In this chapter, we are going to slow down and talk about something that separates beginner from a professional. It basically depends on how you delete data safely, responsibly, and confidently, and how you insert and maintain clean, reliable data from day one. Because in real world, SQL is not about writing queries that work. It's about writing queries that don't break business. So, the part one, why delete statements are the most dangerous ones. So let's start with a very honest question. Why is delete such a scary command? The answer, delete is permanent. Delete does not ask for confirmation. Delete executes immediately. Delete can affect millions of rows within mere seconds. There is no undo button in SQL for delete option. Once data is deleted, reports break, dashboards go blank, finance numbers change, trust is lost. And most importantly, you are accountable. That's why companies don't fear complex joins. They fear one command, that is careless delete statements. Now, with that, we enter into part two, the most common delete mistakes that a beginner makes. So let me share you the most common and most dangerous mistakes beginners often make. Let's look at a sample on my screen. For your information, we are not manipulating this database as of now, because we will be using these tables for our next module, and if we run these commands and delete or truncate the data, then we might lose it and we might have to recreate again. So let's not do that. Let's have a sample query on my screen, and that should be good enough for you to understand what's the flow. So here's the query. Delete from employees. We are deleting from the employees table. That's it. No where clause, no filter, no condition. This query means delete every single record from the employees table. In a production system, this could mean all employees' records are gone, payroll reports destroyed, compliance violations, audit failures, and here's the scary part. SQL will happily execute this query. It won't warn you, it won't ask you, it will just do it. This is why experienced SQL professionals treat delete like handling a loaded weapon. And with that, we transition to the part three, safe deletion principles. So the first one, always preview before delete. The golden rule of safe deletion is simple. If you cannot select it safely, you should never delete it. Before deleting anything, always run a select query using the exact same where condition. Step number one, preview the data. Let's take a look at the simple query on my screen. Select star from table, that is employees table, where department is null. This should show you employees without a department. Now ask yourself, does this data look correct? Are these the records I truly want to remove? Is this count reasonable? Only when you're 100% confident, move to the delete option and delete those records. Now comes the step number two, convert select into delete. Let's look at the sample query right on my screen. Delete from employees where department ID is equals to null or is null. Same condition, same logic, no surprises. This single habit can prevent 90% of data deletion disasters. Now with that, we transition to part number four, safe deletion principle number two. Use transactions. This is professional level practice. In professional environments, delete is rarely executed alone. It is wrapped inside a transaction process. A transaction allows you to preview changes, validate row count, roll back if something looks wrong. For an example, safe deletion using transaction. Let's take a look at this sample code on my screen. Start transaction, semicolon, delete from orders where order date is less than 2025, 1st of January. Now, select row count method and then roll back. What's happening here? SQL prepares the deletion. You check how many number of rows would be affected. If the number looks wrong, you can directly cancel it. When you're confident, then you can commit. This is how real companies delete data. If you mention transactions during your interviews, It instantly signals production level experience. With that, we make a transition to part number 5 of this module. Safe deletion principle number 3. Delete with primary keys when possible. So what do you mean by primary key based deletion? Never delete data using weak conditions if a primary key is already available. So what could be the dangerous part? Let's look at a sample code on my screen. The code will be delete from users where email is equals to alice@example.com, right? Now, how would this be dangerous? Let's say you have orders data and Alice is your company's employee. Alice might have made thousands of sales and she might have entered the same email ID, which is alice@example.com. When you run this query, those thousands of orders records will be vanished in a mere second. Let's say you wanted to just delete the order for a specific number, let's say order 123, and instead of order 123, thousands of all other records based on alice@example.com will be deleted. So now let's understand why this is risky. So in technical terms or SQL terms, email may not be unique. Remember the unique keys that we discussed? You might delete multiple records unintentionally. Now what's the safe process to escape this? Let's look at the sample code on my screen. Delete from users where user ID is equals to 4, right? Or order ID is equals to 4. Now this will be the safest step. It will only eliminate the records of that particular primary key. Now let's go with primary key. Primary keys are unique, they are predictable, they reduce accidental data loss. Professionals think in keys, not names. Now with that, let's make a transition to part number 6 of this module. Safe deletion principle 4. Soft delete. This is again an industry standard. In many real systems, data is never permanently deleted. Instead, companies use something called soft delete. So what is soft delete? Instead of removing the record, you mark it as inactive, you preserve history, you avoid compliance issues. Example, add a status column. Let's look at the sample on my screen. Alter table users, add column, is underscore deleted, boolean default false. So what's happening here? You're trying to make some changes to the table users and you're trying to add a new column which is termed as is deleted. And you're adding a new boolean value which is by default false. So in case if you're trying to delete something, then you will refer to this particular default false value, and anything if you want to hide or delete or filter, you can just use that command and filter out those rows. That's what is happening here, and that's called the soft delete option. Now the soft delete query. Let's look at the sample on my screen. Update users, set is deleted is equals to true where user ID is equals to 4. Now the next one, fetch only active records. So for that, let's look at a sample on my screen. Select star from users where is deleted is equals to false. Now why companies love soft delete? It is audit friendly, reversible, safer, analytics friendly. If you say soft delete strategy in interviews, it shows maturity. Now let's make a transition to part number 7, delete versus truncate. It's an important distinction. Many beginners confuse delete and truncate. So let's discuss this once. Let's start with delete. Delete can use where. It can be rolled back when used with transactions. It triggers logs. It's slower but safer. While truncate, on the other hand, deletes everything. It cannot use where clause. It cannot be rolled back. It's extremely fast and extremely dangerous. So let's have this rule of thumb. If you don't fully understand truncate, don't use it. With that, let's make a transition to part number 8 of this module, which is about best practices for data entry. It's the foundation of trusted analytics. Now, let's shift gears. Safe deletion protects your data. Good data entry prevents problems before they even exist. Bad data is more dangerous than missing data. So, the best practices. Number 1. Always define data types correctly. Every column should reflect real-world meaning. Let's go for an example for bad design. Salary, worker, 50. So you know this is a character data type and it doesn't make any sense. The correct way, salary is integer or salary float. Why this matters? Sorting works correctly aggregations are accurate, performance improves, data validation becomes automatic. SQL data types are your first line of defense. Now, the second best practice, use constraints, not trust. Never trust users, applications, or APIs to send clean data. Use constraints. So the first one, primary key. Primary key is employee ID in our case. A foreign key, department ID, which can reference department ID from the other table. And for safe side, you can also keep another constraint which says not null. So whenever a null value is being trying to insert, it will not take it. It will definitely throw an error. Next one is name, workar 50, and it can also be not null. Unique value, which is email, workar 100, and it should be unique. And another few benefits of using constraints, it prevents duplicates, maintains relationships, stops bad data early. Good SQL developers design defensively. And with that, the next best practice, that is number 3, handle null values intentionally. Null is not bad. Unplanned null is bad. Ask these questions. Is null allowed? What does null mean in business terms? Should there be a default value? For example, department ID data type is int and null, meaning employee may not belong to any department. This is acceptable only if business allows it. Clarity beats assumptions. Now with that, the next best practice, number 4, insert only verified data. Before inserting data, validate the formats, check references, confirm business logic. Let's look at a sample on my screen. Insert into employees, employee ID, name, salary, department ID, hire date. Select 11, Kevin, 80,000, 2, 25, 12, 10. Where exists, select 1 from departments where department ID is equals to 2. This is a sample query on my screen. This ensures two things. Department exists and referential integrity remains intact. Now the best practice number 5. Standardized data formats. Inconsistent data kills analytics. Bad HR, human resources are a good example for that. Now, good version of it. Single standardized value. Solution, use lookup tables, enforce values via foreign keys. Avoid free text whenever possible. Now, clean data is equals to reliable insights. Now, with that, we have best practice number 6, log changes for critical tables. In real systems, every insert, every update, every delete is logged. Why? Because audits, debugging, compliance, accountability. This is why data engineering and SQL governance matters. Now, you might be wondering why this chapter matters. Let's look at the summary. Let's close this with something important. Anyone can write SQL query. Anyone can join tables, but only responsible SQL professionals delete data safely, protect data integrity, design clean schemas, think long term. Companies don't trust databases to beginners. They trust them to people who respect data. If you master safe deletion and data entry best practices, you are no longer just learning SQL. You are learning how real systems survive. In the next module, we will move into joins and relationships using the same database to answer real business questions. Real-world data never lives in a single table. In real companies, employee names are in one table, department names are in another, orders are stored separately, revenue lives somewhere else. If you know how to query one table at a time, you don't know SQL. You know toy SQL. The moment SQL becomes powerful is when you learn joins. Because joins are how HR teams combine employees with different teams, finance teams combine orders with revenue, product teams combine users and behavior, analysts answer business questions, not just technical ones. This chapter is where SQL stops being syntax and starts becoming decision making. Why joins exist is your next question. Let's take a step back and understand why joins even exist. When databases are designed properly, data is normalized, redundancy is avoided, each table has a single responsibility. For example, employees table. Employees table only stores employee details. Department table stores only department names and other details related to department alone. We don't repeat department names inside employees. So, why is this done is your next question again. It is done for few reasons. One is data consistency, easier updates, better performance. But this creates a challenge. If data is split across tables, how do we see the full picture? Right? That's your question now. That's where joins come into the picture. A join tells SQL combine rows from two or more tables based on a relationship. And that relationship is usually a primary key in one table, a foreign key from another. In our database, department ID is the primary key from department, and department ID from employees is the foreign key for employees data table. This is not accidental. This is an intentional design. What's the business analogy behind it? It's very important for learners. Think of joins like VLOOKUPs on steroids. But unlike Excel, joins scale to millions of rows, joins preserve data integrity, joins power dashboards, reports, and even AI systems. If select is asking a question, join is asking a smarter question. Now, let's go to MySQL Workbench to execute some of the queries on joins to understand them even more. So now we have discussed the theory part of module 5. Now we will be proceeding into the demo part. Here we are going to slow down things a little bit because joins are not about memorizing syntax. They're about understanding how rows from different tables come together and work together. Most SQL learners struggle with joins because they imagine tables merging physically, data being copied. That's not what happens. A join is a logical operation, not a physical one. So in this session, we will visualize tables row by row. We will see which row survives, which rows disappear, and why that is happening. By the end of this module, inner join will feel more obvious. Left and right join will stop being so confusing, and full outer join will finally make some sense. And you will understand joins well enough to explain them to someone else. That's a real goal. Now, let's start with first query. Employees with department names. Let's have a look on the query on my screen. So you can see, let me minimize this output window. So you can see we are starting with the demos of module 5 from here. To get access to the data table inside this particular database, we will be executing use interview, which is the schema name. And now we are on the first type of demonstration here, first query. So what is the first type of join are we executing? So the first join we are executing will be an inner join. But before we understand what exactly or technicality of this particular join, let's understand the problem that we are solving. So we have an employees table. We have another table, which is departments table. And we already know what are the columns. We have an employee table and department table. So now what is our end output for this particular query, or what's the business question? Employees store only department ID, not the department name. So the business question here is, show me employees along with their department names. This is a classic relational problem. So let's deal with this in a step-by-step way. Step 1, understanding the join condition. So the join condition here is specifically mentioned. Department ID from employee table with department ID from the department table. This line defines how rows are matched. It tells the database, take department ID from the employees, match it with the department ID of the departments table. Only rows where this condition is true will be joined. Remember, this condition is not filtering after the join. It is defining the join itself. That distinction is critical. Now, let's go into the step number 2. What inner join really means? Inner join means only keep the rows where the match exists on both sides. So, employee with a valid department is kept and employee with null department will be removed. So, remember the employee with no department in the employees table? So, that particular employee will not be considered here. Department with no employees will also be ignored. So, we might be having certain departments in the department table with no employees. So, that will also be ignored. Think of it as give me only the confirmed relationships, not any vague relationships. Row by row visualization. Imagine looping through employees. Alice is equals to department ID is equals to number 2. And engineering exists is equals to keep. Bob from department ID 2, which is engineering exists, so keep it. Charlie from department ID number 1 is from HR and it exists, so keep it. And lastly, Frank, the department ID is equals to null and no matches found, so that will be deleted. Frank completely disappears from the end result. That's how inner join behaves. Now, let's select the entire query and execute. So as we discussed, there are two different ways to execute. So let's go with the shortcut Control Enter to execute the command, or you can also go with this flash logo here. So you can have the output table right here. So the department or employee ID, employee name, his salary, and department name. Second one is Ivan from employee ID 9, salary and department name, which is HR, and so on. We have about a couple of entries here. So overall, where the department is not null and employee is not null, those particular specific columns have a relationship established successfully, and those will be combined or joined together, and we have an end output here. We can also name this as, instead of specific name, ID, salary, department, you can also keep star, where all the columns of both tables will be displayed all together. Let's try that for a homework. Now, from an interviewer's perspective, interview insight, if someone asks you, why is Frank's missing? Your answer should be, because we applied inner join. Inner join only returns rows where the join condition succeeds on both the tables. That shows clarity. Now let's move to the next query. So let me scroll down my query. And here we will be implementing left join. All employees without departments. So let's have a look at the query on my screen. So this is the one which we will be executing for left join. Key mindset that you should be having in your mind is, what exactly is left join? The left join means the left table is mandatory. The right table is optional. Whatever happens, every row from the employees must appear, even if there is no matching from the department table, which happens to be the second table. What changes did you find here compared to inner join? It is only one thing. Rows without a match are not removed here. Instead, missing columns become null. Let's have a visual walkthrough. Let's focus back on Frank again, where Frank did not have any department ID. It was basically null. So no department match. But left join always says keep him anyway. That's the main core difference between the left join and inner join. So now let's see the result. So before executing the query, let's find out how it may look like. So employee ID is equals to Frank's ID, name is equals to Frank, and salary is Frank's salary, and department will be null. It is intentional, null. It's not a bad data. Now, let's execute the query and see the output. So let me select the entire query and hit enter, and there you go. So we have Alice, Bob, Charlie, David, Eve, and here you can see we already have employee ID 6, Frank, Frank's salary, and Frank's department name is null, right? So even if the matches are not accurate, right, in terms of accuracy, even if there is no actual match between both the tables, but whatever the data we have in the left table, which is employees table, everything will be present. That's the major difference between inner join and left join. Now, even if this kind of data is existing, why companies or why professionals prefer left join is your question. Left join is used often when you want to complete coverage, when you want to detect missing relationships, you want to preserve the main data set. When you have these kind of intentions in your mind while executing query, then left join is the most preferable one. So what are the kind of examples you must be thinking when you are dealing with left joins? So all users, if they are never ordered, all products, even if they are not sold, all employees, if they are not even assigned to a dedicated group like Frank here, right? So these are the scenarios where you are forced to use left join. Now a quick interview tip, a powerful phrase. Left join preserves the left table cardinality. That's senior level language. Now, let's go into the next query. So the next query will be based on right join. So let me highlight my query first. And now let's understand the technicality. So this particular query is based on all departments, even if no employees. Let's take a look at the query on my screen. So conceptual identity to the left join. Right join is just the left join from an opposite direction. Previously, we focused solely on the left table. Now we will solely focus on the right table. Now, departments are very mandatory. Employees are optional. In the previous one, employees were mandatory and departments were optional. Now, this is the opposite side. What row survives will be your question. Departments with employees and matched rows will appear. And also, departments with no employees will also appear. But anyways, employees without departments is a little bit irrelevant here. But for the concern of understanding, let's keep it that way. Now, let's execute the query to understand the output. Now, there you go. We have all the departments and their employees together. We have HR and the name of employee is Charlie. We have Ivan from HR, and we have Alice, Bob, and David from engineering, Heidi, Eve from finance, Grace from marketing, and Judy from marketing. Now, let's understand one more thing. Why right join is rarely used? Most developers prefer left join, reorder table instead of using right join. So this query could be written as from departments D, left join, employees E, right? This is also a perfect logic. Same logic actually, more readable. Now, for that, let's have a small teaching insight. Right join is important to understand, but not commonly used in production code. Now, let's dive into the fourth query, which is about a simulated full outer join. So, why simulated, you ask? Because there is nothing called full outer join, but we can still have a simulation of it by including the union in our code. So, you can see I have highlighted the code and we have a union command here where we will combine both the tables together. So now, why are we doing this? Some databases do not support full outer join, or learners want to understand how it works internally. So for that, we have a query highlighted right on my screen. We'll simulate it. But before that, what full outer join means conceptually? Give me everything, right? This particular data extractions include matched rows, left only rows, and right only rows. Basically, what we are trying to do is we are combining inner join, left join, and right join, basically extracting whatever is present inside both the tables. Nothing is lost. And now you might be having a question. Why did we use union here? Left join keeps all the employees from left. Right join keeps all the employees from right. Basically, employees and departments. And what is the purpose of union is union combines both and removes any duplicates present in both the tables. So what's the result? Full coverage from both sides. Now, let's execute this query and see the output. So there you go. We have all the names of the employees and their specific departments, similar to the previous query. So we have Frank without department name and all the other employees with their dedicated department names right here. Now, what's the important learning moment? This query teaches join logic, set operations, result set thinking. This is advanced understanding, not beginner syntax. Now let's move with a few example queries. So first one, I want to identify orders with user email, and we could go with an inner join here. So let me select the entire query. Now let's understand the flow of this particular query. So take a look on my query at my screen. Business story orders store, and we have customer ID, not customer email. User store, and we have email, not every other details on that, right? Now we want to join to enrich the order data. Why inner join? Because inner join makes sense here. An order must belong to a user. So orders without users is invalid. Inner join enforces data integrity logically. So before we move further, let's execute this command and see the output. So we have order ID, email ID, and order date as per our requirement. Now, what's the real world relevance? This is how dashboards, invoices, analytics queries are built. Almost every real system uses this pattern. Now, let's go with the next query where we will try to find out revenue per order date. And we will be using an aggregate function here. So let's take a look at the query on my screen. So shift in thinking. We are no longer looking at rows. We are looking at groups of data. Group by in my query changes everything. How group by works conceptually and everything else. Now, let's look at the database steps. First, we will scan all the rows. Then group by order table, plus we will also be applying an aggregate function per the group. And then we will return one row per group. So let's quickly execute this query and see the output. There you go. We have order date, total number of transactions, and total revenue all in one shot here. So why count and sum work here? Because count of number of rows per date and sum adds revenue per date. This is basically time series analysis and it is extremely common. Now a quick interview insight for you. Group by reduces number of rows. Join expands number of rows. Remember that contrast. Now we have query number 7, which is about employees with highest salaries. And here we will be using two things. First is a join function and next is a filter function. Now let's take a look on the query. So here we have employees with highest salaries and this is my query. So what we are basically trying to do is we are combining both the tables, which is employee table and departments table. And our concern is to find out any employee whose salary is more than 90,000. So that's the overall observation on this particular question or business question. So what's the execution order? Coming to execution order, one of the most important and commonly asked question in SQL interviews is the execution order of the commands. So far, we have seen through all the basic fundamentals of SQL commands, right? The keywords basically select, join, and all those things. So let's consider this as a homework. Let us know in the comment section below what is the execution order of all these keywords in SQL. Now, for a quick clue, let's see the flow of execution for this particular query. So what happens is, first, join is the one which activates. It joins both the tables. Then, where comes into the picture? It filters the rows. And then comes selects, which formats the output. And this order matters. Let's quickly execute this query and see the output. So there you go. We have Bob, David, even Heidi, who have salaries greater than 90,000 and their dedicated departments are engineering, finance. So these three employees are from engineering department, and we already discussed this, right? Engineering department is the one which is paying highest number of salaries. So we have three from engineering itself, and the next one is finance. Now, why where is executing after join? This is your question, right? We are filtering employees, not departments. If we filtered earlier, we might lose the relationship context. Now, let's have a quick practical takeaway. Join defines relationships, where it defines conditions. Never confuse with both of these. Now we have the query number 8, where we will find out departments with no employees at all. Now, let's take a quick look on the query on my screen. So this is my query. I want to select the department name from departments B, and I want to apply left join, and I'm joining this with employees on the category of department ID, and where employee ID is null. This is a classic interview query and it tests deep join understanding. What's happening is, in a step-by-step way, left join keeps all the entries from the departments table where employee ID is equals to null, and it keeps only rows where no employee is matched. So the result, let's execute this to find the result. So there you go. Departments with 0 employees. Why inner join can't solve this? Inner join removes non-matching entries. Left join plus null, check, reveals them. This is powerful logic. Now we move into the 9th query, customers with multiple orders. So let's take a quick look on the query. Now this is a multi-layer query and it combines a lot of things. For example, join, group by, and having. This is real-world SQL. Why having is used instead of where could be one question in your mind, because where filters rows and having filters groups. This you need to understand. This is one golden rule which you always need to keep in your mind. Now let's discuss the execution logic. Join users and orders. Join is used to combine users and orders. Group by to group or categorize email. Count is used to count the number of orders per user. And lastly, having keeps only the users with order numbers greater than 2. Now let's execute this query. So we have the output here. We have Alice and Bob with total orders 4 each. That's the output. Now what's the business meaning? This query finds out the loyal customers, high engagement users, retention targets. Exactly what analytics teams do on a daily basis. Now this is a final wrap up for joins. If you understand this module deeply, joins are no longer scary. Nulls make sense, aggregations feel logical, interview questions become more predictable. You didn't just learn the syntax, you learned how databases combine data, how SQL thinks, how real systems are queried. That's professional level SQL. And with that, we make a transition to the next module. Now, repeat. Now we have reached to the module number 6, which is about grouping and aggregating data in SQL. So here we will be dealing with group by, having, aggregation functions, and filtering group results. Now let's have a quick introduction to this. Why this chapter or this module matters the most. Up until now, everything we have done in SQL has focused on individual rows. We used to select rows, filter rows, sorted rows, and we used to join some rows. But here's the reality of how SQL is used in the real world. Businesses almost never ask that, show me every row in the table. Instead, they ask, how many employees do we have per department? What is the average salary? Which states generate the highest revenue? Who are most active customers or the most loyal customers? These are summary questions. And the moment SQL moves from showing rows to answering summary questions, you made a huge transition. We enter the world of group by and aggregation. So far, you had a basic introduction to these functions. This chapter is where SQL stops being data relevant and starts becoming data analysis. If joins helped us connect data, group by helps us understand patterns inside the data. Now let's go with the part 1. What group by actually does. Let's build the intuition first. SQL looks at each row independently, but when you use group by, SQL changes how it thinks. Instead of processing row by row, SQL tries to process in a different way. It tries to group rows that share the same value, applies calculations to each group, returns one row per group. So you are no longer working at row level, you're working at a group level. Think of group by as a machine that takes many rows, bundles them into logical buckets, and produces summarized information. This is the foundation of reports, dashboards, KPIs, analytics, and business intelligence. Now let's go to the part 2. First, group by, simple and clear. This could be our first query here. Now let's go through the sample query on my screen. So here we have a department ID and we're trying to count the number of employees per department, and we will be aliasing it as total employees, and we are selecting this data from employees and we are trying to group it by department ID. Now what we want to know is the question. So it is basic and simple. We want to know how many employees are there for each department. Instead of listing employees one by one, we try to group them, and once we group them, we will try to count them and then execute the query. So let's execute this query and see the output. So basically we have 5 departments here. One department is not assigned, so that particular one is based on Frank that we earlier executed. So let's take a pause and understand what SQL is doing here. It is scanning the employees table, grouping rows by department ID, counts the total number of employees inside each group. Every department becomes one row in the result. Now, one important observation that you need to have here is employees with null department form a separate group altogether. This is real world behavior. Missing data doesn't disappear. Now let's make a transition to part 3, where we try to group by with join, making output business friendly. IDs are useful for databases, but people don't think in IDs. They think in names. So let's improve this query by using a join function. So let's quickly go to Workbench and see the code on my screen. So previously we had no names to the department, right? Now to make it more sensible, we are trying to combine employees table with the departments table, because departments table has the name of the department, right? The null 1, 2, 3, 4 doesn't make sense. So it could make a lot of sense when we had an actual department name. So for this, let's execute this particular query, and you already know how the left join works and on what basis did this particular employee table establish a join with employees table, right? So here we have department ID from employees table, and here we have department ID from departments table. Based on the match and the type of join that we are using is left join, what it does is it keeps all the entries from the left table, which is the department or employees table, and the matching elements from the right table, which is the departments table, right? So employees is the left and departments is the right. Now we will be grouping by department name. So let's execute this query, and there you go. We have HR, engineering, finance, and the null department, and the total number of employees working in each department. Now we join employees with departments. We grouped by department name. We made the output more readable for leadership. This is how SQL is used in HR reports, management dashboards, workforce planning, and a lot more. Now, one very important learning from this part is joins usually happen before group by. Now let's make a transition to part 4, which is slightly tricky group by, and we will be using multiple columns here. Now let's raise the difficulty slightly. Suppose the business asks you this: how many employees were hired per department per day? This means we group on more than one column. So let's execute the code right on my screen. So if I scroll down, here we have another slightly tricky query. So here we are trying to select the department ID, hire date, and we are counting the number of employees based on the column employee ID, and we are aliasing it as hire count, and we are extracting this data from employees table, and here we are grouping by multiple elements. One is department ID and another is hire date. You might be wondering, will this work? Group by was designed to take multiple entries here, so this totally works. Now let's execute this query and see the output. So we have a department ID and hire date. So based on these dates, we have the total number of recruits that we had on that particular date. Now what's happening here? SQL creates groups using both columns together. Each unique combination becomes one group. This increases the number of results per row. The key rule to emphasize clearly is any column in select that is not aggregated must appear in group by. This rule appears frequently in interviews. Now, let's move to the next part of this module, which is about aggregation functions. So it's a quick deep dive. Now that group by makes sense, let's talk about aggregation functions. These are functions that operate on groups, not individual rows. Now we have a few of them. So let's get started with count function. It is basically used for measuring volume. Let's start with count. You can see a sample query on my screen. So let's go to the workbench once. So here what are we trying to do is we're trying to count the total number of employees from the employees table, right? And we will be aliasing it as the total employees. What this basically does is it counts all the rows. Now with grouping, back to my screen. So let's execute this and we have about total employees. Now about grouping, we have the query right on my screen here. So what we're basically trying to do is we are basically trying to group the total number of employees per each department. So we are adding the department ID and counting the number of employees in there. So let's execute this query. There you go. So count of column ignores all the nulls. Count of star counts total number of rows regardless of how many entries we have. Count answers questions like how many, how frequent, how active. Now with that, we have the next aggregate function, which is a sum function measuring total value. Sum is used for totals. Let's see a code. So here we have select sum of salary as total salary from employees table. Let's execute this and we have about 8,70,000. Now let's make it a little more meaningful. Explain the business context, budget allocation, cost control, department-wise spending, right? These will be the business level questions. If you categorize by departments, then you will have a clear answer on the budget allocated for each department. Next aggregate function is based on average, typically measuring some value such as average salary per department. So let's execute the code. So we also have another query on sum. So let's execute this as well. So once executed, you will have, this is the amount of salary or budget allocated to each department. Now let's go with the average function again as discussed. So here we want to find out the average salary allocated per employee in each department, which is similar to the previous query. So let's execute this and we will have the answer. So the average salary allocated per each department is, for HR we have 60,000, for engineering we have 1,08,750, for finance we have 95,000, and for marketing 80,000. So this is the average salary which we have allocated for each and every department. Now the next aggregate functions are minimum and maximum, and it is finding the extremes. So let's go for an example, and the business use cases are salary bands, compensation gaps, identifying anomalies, and a lot more. So here we have the department name. So minimum salary as lowest salary per department, maximum salary is the highest salary per department, and we're extracting this from employees table. And since we need the department name, we are joining this with departments table D, and based on the column department ID, and we are grouping by department name. So let's quickly execute this query, and there we have the lowest and highest salaries of each department: HR, engineering, finance, and marketing. So the lowest salary in HR is 50, highest is 70, engineering is 90, and 12 or 1,20,000, and 95,000 for finance, and 95 is the highest as well. Marketing, we have 75 as the low and 85 as the highest. Now let's make a transition to the part 6 of this module, aggregations with dates, transaction data. Now let's switch tables and think like analysts, like orders per day. Now let's go through the query here. So this is one query that highlights the number of orders per day. Let's execute this. So we have about so many orders, and a few dates are where we had multiple orders, and we also have few dates where we have about a single order per day. And let's go through the next query that we had, which is revenue per day. So this particular query is based on revenue per day. Let's execute this, and we have 25,12,6 as the highest revenue which we earned, which is December 6th, 2025. So this is how daily KPIs are built. These queries sit behind dashboards. Time-based aggregation is extremely common. Now with that, let's make a transition to part 7 of this module, which is about having clause, filtering groups, and it is really critical. Now we address one of the most misunderstood concepts of SQL, where filters rows, having filters groups. You cannot use aggregation functions inside where. I guess this is the second time I'm repeating this because this is really important, and most of the times we confuse with this. This is why having exists, and basic having examples are the following. Departments with more than 2 employees. And for executing this command, let's take a quick look on the screen. So here we have the query. Select department ID, count the total number of employees as department's employee count from employees table, and group by department ID, having count of employees greater than 2. So let's execute this. And we have that one particular department where we have about 4 employees. I think it is engineering department. Now let's also discuss the execution order once again so that you have a quick understanding of how the execution order really works in SQL, and it could be helpful for your homework that we had in our previous model. Group by runs first, aggregation happens next, having filters the result, and having with join. And for this, let's go with an example. Right here, we will be combining both having with join. So here we are trying to have this particular business question: which departments are highest paying? So here we have a department name, average salary, and employee, and we are trying to find out the employees with paycheck more than the average paycheck of every employee. So engineering and finance are those two teams which are paying more than the average salary. So we have our final answer. So those two departments which are having the highest salary, right? Tricky, having multiple conditions. So is our next repeat. Now moving next is another tricky question, and this particular one is based on having multiple conditions. So let's go back to the MySQL workbench and have a look at the query. So multiple conditions is right here, having count more than 2, and the average salary should be more than 80,000, right? So let's execute this query. The only difference is we are trying to have the average salary should be more than 80. So engineering team is the one which has employee count as 4, and average salary is 1,08,750. So having can use multiple aggregations. This is advanced interview level question from SQL, so you can make a note of it. Now moving further, we have part 8 of this module, filtering grouped results, where we have where along with having together. This is where learners truly level up. Now let's have a small business requirement. Show average salary per department for employees hired after November 2025, but only include departments where the average salary is above 85,000. So let's take a quick look on the code. So this is the code that we will be executing. So we have put the hire date, which is November 1st, 2025. We're trying to group by department, and the same query condition, which is salary should be more than 85,000. So let's quickly execute this query. So we have two departments in that way, engineering and finance, where we recruited employees after November 2025, and the salary is above 85,000. Now let's look at the execution order. From executes first, then join, followed by that we have where, then group by will be executed, followed by that we have having clause, then we will select, and lastly we will order by. This is core analytical SQL thinking. Now let's move to the part 9 of this module, which is a capstone query, and this could be real dashboard logic. Let's end this with a realistic analysis query. Back to the workbench. So here we have the query. So here what we are trying to do is we are trying to group by order date, and we should be having some amount greater than 800, and total revenue should be in descending order. We are trying to find out those particular columns, which is order date, count total sales, sum of total revenue, and average order. So let's execute this query, and we have the output over here. Now let's understand this. Multiple aggregations are done together. Filtering is done using having clause. We have sorted the results, and this query could power a business dashboard. Now let's also discuss some of the common mistakes that learners should be warned about. Now let's discuss some of the common mistakes that learners make and we should be alert about. So the first one is about forgetting group by columns using where instead of having, mixing row level and group level logic, ignoring null behavior, aggregating without the business context. Now, why this chapter was a turning point? At this stage, learners cross an important milestone. If you have understood group by, aggregation functions, having clause, where clause, filtering group data, then you're no longer just querying data, you're analyzing data. This is the skill that powers dashboards, drives decisions, gets tested in interviews, separates beginners from professionals. In the next chapter, we will build on this foundation with advanced analytics concepts, including window functions and ranking. Now we enter the module 7, which is about subqueries and nested queries in SQL. So it could be single row, multi-row, correlated subqueries, plus usage in select, from, and where. Now let's have a quick introduction to why subqueries matter so much. So far in SQL, we've been answering direct questions. Some questions like, show me the roll number of employees, show me departments, show me total revenue per day. But real business questions are rarely simple. Businesses ask questions like employees who can earn more than the company's average, departments with higher than average salaries, customers who place more orders than most of the other users, sales days that outperform the overall trend. Notice something important. These questions depend on the result of another query. And that's exactly why subqueries exist. A subquery allows one SQL query to depend upon the result of another SQL query. This chapter is where SQL becomes logical and layered, not just procedural. Now, part 1 of this particular module, what exactly is a subquery? So, let's define it. Subquery is a query inside another query. It runs first, produces a result, and that result is used by another outer query. Think of subqueries as asking a question, using the answer to ask a better question. In interviews, this is often described as SQL inside SQL. Simple visual example can be understood in this way. Inner query calculates something, and outer query uses that calculation to provide some better answer. SQL reads subqueries inside out, not top to bottom. This mental shift is really critical. Now, let's go through some examples. So this brings us to part 2, single row subqueries. What is a single row subquery, you ask? A single row subquery returns exactly one value used with operations like equals to, greater than, less than, greater than or equals to, less than or equals to. Let's take an example on my screen. So employees earning more than the average salary. So let's find the average salary first. Let's look at the code on my screen. So here we are trying to find out the average salary of the overall employees table. So the average salary is 87,000. Now instead of hard coding this value, we will nest it, right? So here we want to find out the employee ID, name of the employee, and salary from employees table, where salary is more than the average salary. So here we are ingesting this particular subquery that we recently executed, right? So this happens to be the single line subquery that we are discussing as of now. So this particular single line subquery will be ingested inside the outer query. So this happens to be the inner query, and this happens to be the outer query. Now let's run this. There you go. So we have about 1, 2, 3, 4, 5 employees who earn more than the average salary of other employees. So let's take a pause and understand what's happening here. Inner query calculates company's average salary. Outer query performs and filters employees above the average salary range. Important business interpretation to understand here. Who are our top earners compared to the organization? This is a classic interview question. Now, let's take another example. Employees earning more than the maximum salary in a specific department, let's say HR. Now, let's take an example on my screen. So here we have a subquery which is select maximum salary from employees where department ID is equals to 1. So the department ID 1 is none other than the HR department. So we are encapsulating this particular inner subquery onto the outer subquery, which is trying to select the name, salary from the employees table, right? And where salary is greater than a number which is the result of this particular subquery, which is the maximum salary of employees. Now, let's execute this query. Control Enter, and there you go. Now, let's take a pause and understand how is this working. The inner query returns the maximum value of salary from HR department, and the outer query compares every employee against it. This shows targeted comparison logic. Now, let's make a transition to part 3 where we will have multi-row subqueries. So what is a multi-row subquery? A multi-row subquery returns more than one row. It is most commonly used with operators like in, any, all. So for this, to understand in a better way, let's take an example. And the example question is employees in departments with average salary greater than 90,000. So first, let's identify all the departments. For that, let's take a look on my screen. So let me quickly write a small query. Star from departments. So we have 1, 2, 3, 4 departments: engineering, HR, finance, and marketing. Now we need to execute this particular subquery where we are trying to find out department ID and employees and department having salary more than 90,000. Now let's execute this. So we have department IDs 2 and 3 where they have greater higher salary or the average salary. Now we need to use this particular query inside another external query. So this is the outer query, this particular section, and this was the subquery that we just executed. Now we need to encapsulate this particular subquery inside the outer query, and now let's execute this. So we have the name of the employee, their salary, and their department ID. So as discussed in the first subquery, these are the employee or department IDs and their relevant employees. Now let's understand this clearly. Inner query returns multiple department IDs and outer query filters employees belonging to those departments. Now the business question answered here is, which employees work in higher paying departments? So that's what the answer we gave. Now let's take another example. So the example 2 is, we want to find out customers who placed more orders than the average. Now let's execute this particular query. So there you go. These are the customer and their IDs 1 and 2, and their placed orders 3 and 4. These are the most loyal customers. Now let's understand the working of this particular code segment. Customers who placed more orders than average. Now let's understand this carefully. Inner subquery calculates order counts per customer. Next level calculates average order count. Outer query filters high activity customers. This is advanced analytical SQL, not beginner stuff. Now let's make a transition to part 4, which is about correlated subqueries and most important concept. Now, what is a correlated subquery? A correlated subquery depends on the outer query and it executes once per row and cannot run independently. Think of it as, for each row, run a subquery that depends on that particular row. This is where SQL starts to feel like programming. For that, let's take an example. So this is the particular example we are going to execute. The question here was employees earning more than their department's average. Now let's understand this particular example. Outer query processes each employee. Inner query recalculates average salary for that particular employee's department. Now the comparison happens row by row. Now the business interpretation. Who are the top performers inside each department? This is one of the most frequently asked SQL interview questions. Now, let's consider another example. Orders that occurred after customer's first order. For that, let's take a quick look on the code on my screen. So here it is. We are using two different queries, the outer query and the inner query. So the inner query is where we selected minimum orders and customer ID is equals to customer ID from orders table. And we are joining, or we are applying self join here, basically combining the orders table with itself. Now let's execute this query. There you go. Now let's understand this. For each order, we find the customer's first order. We keep only the later orders. This helps to analyze repeated behavior. Now what is used here? We use this in retention analysis, funnel tracking, behavioral analytics. Now with that, let's make a transition to part 5. Part 5 is about subqueries in where clause. So it is a basic recap plus best use. This is the most common place where subqueries are used. Let's take an example. So here the business query is sales on high revenue days. Let's understand this. Inner query identifies high revenue days. Outer query fetches detailed sale rows. This pattern is used constantly in analytics. Now let's execute this query. So there you go. We have the answer. So we have two different entries, sale ID 8 and 9, and the amount was 400, 50 and 600. Now let's make a transition to part 6 of this module. So part 6 is about subqueries in SQL clause and will have calculated columns. Subqueries can act like dynamic columns. So let's take an example. So this is our example here. Let's execute this. So we have the output. We have a name of the employee, salary, company's average salary, and difference from average. Now let's understand what did we execute here. Salary compared to company's average. The inner query runs once, adds context to every row, makes reports more meaningful. Now it's great for dashboards and exports. So here what we did is we find out the salary of the employee and company's average and what's the difference, right? The difference amount that they are earning more than the average salary. Now this drives us to part number 7 of this module, which is about subqueries in from clause, or also known as the derived tables. Subqueries from act like temporary tables. For example, department-wise salary summary. Let's take a look at the example on my screen. So this is the code that we will be executing, and here we have the output. Now let's understand what is the logic that we implemented here. The inner query creates a derived table, outer query filters it, and this improves readability for complex logic. This is a stepping stone to CTEs and window functions. Now let's move to part 8. So part 8 is about when to use subqueries versus joins. Now one important discussion. Now with that, we make a transition to module 8, which is about the difference, right? When to use subqueries and when to use joins. Use subqueries when logic is layered. Aggregation is needed first. Readability improves. And when to use joins? Joins are used when data relationships are direct, performance matters most, data volume is really large, and professionals choose clarity and performance. Now let's also go through some of the common mistakes to warn learners about. So using equals to instead of in, expecting multi-row subqueries to return one value, forgetting correlation logic, overusing subqueries where joins are better, and the last one, ignoring performance implications. Now why this chapter was a milestone? If joins taught SQL how tables relate, subqueries teach SQL how logics relate. Once you understand single row subqueries, multi-row subqueries, correlated subqueries, subqueries in SQL, from and where clauses, you can answer almost any analytical question in SQL. This chapter is a bridge from intermediate SQL to advanced SQL to interviews to real production analytics. In the next chapter, we will take this logic and supercharge it using window functions and ranking, which solve many problems more efficiently. Now we transition into module 8, which is about data modeling and relationships. So primary keys, foreign keys, relationships, ER diagrams, and normalization are the topics discussed in this particular module. Now let's have a quick introduction. Why this module defines your SQL maturity. Before we begin this chapter, I want you to pause for a moment. Up to this point in the course, you've been learning how to talk to a database, how to select data, how to filter it, how to join tables, how to aggregate results. That's important. Okay, this chapter answers a deeper question. Why does a database look the way it does in the first place? This chapter is not about writing queries. This chapter is about thinking like a database designer. And here's a reality check that most tutorials won't tell you. In real world, SQL queries are easy to learn. Poor data modeling destroys companies. Most production bugs are data design bugs. Most analytical errors come from bad relationships. If data modeling is weak, joins become confusing. Data becomes inconsistent. Reports contradict each other, performance drops, and most importantly, trust in data disappears. This is why senior designers, architects, and analytical leaders care deeply about data modeling. This chapter will help you understand how professional systems are designed, read any database schema with confidence, answer system design interview questions, avoid beginner level modeling mistakes, build databases that scale logically, not just technically. Think of this chapter as the architecture class of SQL. Now, let's start with part 1. What is data modeling? Now, thinking before coding is nothing but data modeling. Let's start with the foundation. So, what do you mean by data modeling? Data modeling is the process of identifying entities, defining their attributes, establishing relationships, enforcing rules and constraints. In plain language, data modeling is deciding how information is structured, stored, and connected before data even exists. A good data model answers what are core subjects of the system, what information belongs to each object, how do objects relate to each other, what rules should never be broken. Now let's go through a real world analogy to understand this better. Imagine you're designing a hospital data system. You don't start by randomly creating tables. First, you think. You think about patient's data table, doctor's data table, appointments table, departments table, prescriptions table, bills table. Then you start asking questions. Can a patient have multiple doctors? Can a doctor treat multiple patients? Does an appointment exist without a patient? This type of thinking is nothing but data modeling. SQL syntax comes later in the picture. Why data modeling comes first is because of some reasons. First, many beginners jump directly into creating tables. Start inserting data, worry about queries later. Now, let's discuss this in terms of professionals. Professionals design the data model first, validate relationships next, anticipate growth in the future, and prevent any type of inconsistency. Data modeling is about future-proofing your dataset. Now, this makes our transition to the part 2 of this module, primary keys, the primary identity of any data. Let's talk about the most fundamental concept in relational databases. What is a primary key, you ask? A primary key is a combination or a column of columns that uniquely identifies each row in a table. Every record must have one identity, one unambiguous reference. In simple terms, a primary key answers one question. How do I uniquely point to this exact row? Now, why primary keys exist? This is one particular and critical insight. Imagine a table without a primary key. You have two customers with the same name, same city, and same phone number as well. Now you ask yourself, which row do I update? Which one do I delete? Which one does a specific order belong to? Now your answer. Without a primary key, data becomes unreliable. That's the answer. That's why we do have a primary key. It's like an identity for your data entry. Let's understand through a real world analogy. For example, government identity. Your name can change, your address can change, your phone number can change. But the passport number, the Aadhaar number, social security number, which will not change. This uniquely identifies you. That's exactly what a primary key does for a row. Now, let's discuss the characteristics of a strong primary key. A good primary key should be unique, no duplicates ever, it should not be null, its identity cannot be missing. Third one is it should be stable, should not change over time. And next one is it should be minimal, prefer single column keys. Now, let's understand one difference between natural keys and surrogate keys is very important. Natural key comes from business data. Example, email, username, PAN number, etc. Now, what are the problems here? So the problems are this can change, this can be duplicated, it can be tied to business rules. Now, let's understand the surrogate key. Surrogate keys are artificially generated ones. For example, auto increment ID. What are the benefits of using surrogate? They are simple, stable, and efficient for joins. Most modern systems use surrogate keys to enforce uniqueness separately. Now, a quick interview tip. Should email be a primary key? A most mature answer is email can be unique, but emails can change. Better as a unique constraint, not as a primary key. Now, we make transition to the part 3 of this module. Foreign keys, which are connecting the data world. Now comes the concept that makes SQL relational. So what is a foreign key? Foreign key is a column in one table that references the primary key of another table. In simple terms, a foreign key relates a relationship between tables. Why foreign keys exist? Now the next question is, why foreign keys exist? Instead of duplicating data, department name, customer details, product information, we store it once. Reference it everywhere. This ensures consistency, reduced storage, cleaner updates. Now, let's understand through a real world analogy. Booking a flight. A ticket references to passenger ID, flight ID. The ticket does not store passenger name repeatedly, aircraft details repeatedly. Foreign keys keep systems normalized and scalable. Now, let's go through referential integrity, a non-negotiable rule. Foreign keys enforce you cannot reference a record that doesn't exist. You cannot delete a parent if children depend on it. This protects the database from orphan records, broken relationships, logical corruption. The next one is on delete and on update. These are business decisions. When a parent row changes, should child rows get deleted? Should they get updated? Should the action be blocked? Now to understand this, consider these examples. Deleting a customer with orders, usually it is restricted. Deleting a draft record, cascade is allowed. These are domain decisions, not just SQL syntax. Now let's make a transition to part 4 of this module, relationship types, how data connects. Understanding relationships is the heart of modeling. We have a wide variety of relationship types. Let's start with one-to-one relationship. One record in table A maps to another record in table B. For example, user data table to profile data table, employee data table to ID card data table, person data table to passport data table. Now the next question is, when should you use one-to-one relationship? It is rarely but intentionally used when sensitive data needs separation, optional data exists, performance optimization is required. Now let's consider an example. Authentication data separated from user profile. Now the next type of relationship is one to many or one to n. This kind of relationship is most common. One record in table A maps to many records in table B. Examples: customer table to orders table, department table to employees table, user table to post table. This is the default relationship in relational databases. What's the implementation rule? The foreign key always sits on the many side. This rule alone clears 70% of beginner confusion. The next one is many to many relationship or M is to N relationship. Many records in table A relate to many records in table B. Some of the examples are students table to courses table, products table to orders table, movies table to actors table. Now, junction table concept. Relational databases resolve M to N using a third-party table, two foreign keys, optional extra attributes. This table often stores timestamps, quantities, status, grades, etc. With that, we make a transition to part 5, which is about ER diagrams. It is basically about thinking visually. An ER diagram is a visual blueprint of a database. It shows tables, columns, primary keys, foreign keys, and relationships. Now, why ER diagrams matter in the real world? Before code, architects use or draw ER diagrams. Teams review them. Business rules are validated. ER diagrams prevent rework, confusion, costly redesigns. How interviewers use ER diagrams could be a question. So they want to see logical thinking, relationship clarity, normalization awareness. You don't need fancy symbols. Clarity matters more. With that, we make a transition to part 6 of this module. Normalization, which is about keeping the data clean. Now with that, we make a transition to part 6 of this module, which is about normalization and keeping the data clean. Now, let's talk about one of the most misunderstood topics. What is normalization? Normalization is organizing data to minimize redundancy and dependency. In simple words, avoid duplicate data, avoid inconsistent updates, protect data integrity. Now, why normalization exists? Without normalization, same data stored in multiple places, updates miss same rows, reports contradict each other, and the data trust collapses. Now we have a few different types of normalizations. So the first one is 1F or the first normal. It is about atomic values and no repeating groups. Now a bad format will be phone 1, phone 2, and phone 3, and a good separate phone table is the best example for this. Now we have this second normal form, which is 2NF, and the rules are in 1NF, no partial dependency, and it applies mainly to composite primary keys. Now we have the third normal form, which is also known as the 3NF, and the rules are in 2NF, no transitive dependency, meaning non-key attributes depend only on the primary key. Now let's understand the difference between normalization versus denormalization, which is a real-world trade-off. OLTP systems, highly normalized, write consistency matters. Analytics systems, often denormalized, read performance matters, and professionals choose intentionally, not blindly. And with that, we make a transition to part 7 of this module, which is about real-world case study on e-commerce modeling. Let's design a simple e-commerce system verbally. So we have the following entities. We will be having users, products, orders, order items, and payments. Now let's discuss the relationships. Users are connected to orders in 1 to n, and orders are connected to order items, which is also 1 to n. And the last one is product to order items, which is also 1 to n. No direct order to product, which is m to n, resolved via order items. This is real world modeling in action. Now let's make a transition to part 8, which is about common beginner mistakes. Let's quickly cover some mistakes professionals avoid. So some of the mistakes are using names as primary keys, storing repeated values, missing foreign keys, over-normalizing early, ignoring future growth. Avoid these mistakes and you already think like a pro. Now we enter the part 9 of this module, which is about interview mindset and how to answer design questions. Interviewers want thought process, trade-off awareness, business understanding. Always explain why you choose a structure, why you rejected alternatives, how it scales. Now, a simple summary. Why this chapter changes everything. This chapter transforms how you see databases. You no longer memorize syntax, fear joins, or guess relationships. You now understand structure, design confidently, think long term. This is the difference between a SQL user and a data professional. So now we have entered module 9, which is about indexing and performance tuning. This module will help us understand why indexes matter, creating and using indexes, and query optimization tips. Now, let's have a quick introduction. Why performance is a career skill. Before we talk about indexes, let me tell you something very important. Most SQL learners stop at select, where, join, group by commands. But professionals are judged on performance. In real companies, no one praises a query that works. They praise a query that works fast. They praise a query that works at a scale. And here's the truth. Performance problems don't show up in small datasets. They show up in production. This chapter is all about why some queries are fast, why others slow down as data grows, and how databases search data internally, how indexes change the game completely. If you understand this module, you'll write scalable queries, you'll pass performance-based interviews, you'll avoid production outages, you'll sound like someone with real experience. This is not about memorization. This is about how databases link. Now the part 1 of this module. Why indexes matter, how databases find data. So let's start with a simple question. How does a database find data? Imagine a table with 10 rows. It could be fast. And if you have 10,000 rows, maybe your query is manageable. 10 million rows, already you might be thinking your query could be slower. And in case if you had a billion rows, it's a complete disaster. So without indexes, this could become a reality. Now, without an index, the database performs a full table scan, meaning it checks every row one by one until it finds what you asked for. That's like searching for a name in a phone book without an index, reading every page from start to the end. Now, a real-world analogy. Book index versus page-by-page reading. Think of a textbook. If you want to find out a normalization topic, you don't have to read every page. You go through the index, find the page number, jump directly, and that's exactly what a database index does. Now, what is an index? An index is a separate data structure that stores column values in sorted order without pointers to the actual rows. In simple terms, an index is a shortcut for finding data quickly. Why indexes improve performance is your question, right? Indexes reduce disk input-output operations, CPU usage, query execution time. It is especially for where conditions, join conditions, order by conditions, or clauses and group by clauses. Now, important reality check indexes. They speed up reads, slow down writes. Every insert, update, delete commands must also update indexes. So indexes are not free. This is why indexing is a design decision, not a default action. Now, with that, we make a transition to the part 2 of this module, which is about how indexes work internally. Now, you don't need to be a database engineer, but you must understand the intuition. Most databases use B tree or B plus tree structures. Conceptually, data is stored in sorted blocks. Each block points to a child block. Searches are logarithmic, not linear. This means searching 1 million rows is almost equal to a few steps. Searching 1 billion rows is also still manageable. Without indexes, search time grows linearly, performance collapses at a scale. Now, let's understand the difference between clustered and non-clustered index. First, clustered index. It defines physical order of data. Table can have only one and it is often a primary key. Now, non-clustered index. It's separate structure. Multiple clustered indexes are allowed. Points back to table rows. You don't need to memorize this just now. You just understand. Some indexes control how data is stored. Others act as lookup maps. And with that, we make a transition to part 3 of this module, which is about creating and using indexes. Now, let's talk about practical usage. Basic index creation. Indexes are created on columns that are frequently searched, frequently joined, frequently filtered. Now, some of the examples are like user ID, order ID, email address, and other foreign keys. When should you create an index could be your next question. You should create indexes when table size is large, queries use where on that column, and joins happen frequently, and sorting is very common. And the next topic is about selectivity, which is a key performance concept. High selectivity column has many unique values. For example, email, user ID, and low selectivity are few unique values. For example, gender, status, active or inactive. Now, indexes work best on high selectivity columns. Composite indexes sometimes queries filter on multiple columns as well. For example, a department ID is equals to 2 and salary is greater than 90,000. A composite index on department ID and salary can significantly improve performance, but order matters. Department ID comma salary is not equals to salary comma department ID. Indexes follow left to right rules. Indexes and joins, very important part. Indexes on primary keys, foreign keys make join operations faster, more predictable. This is why foreign keys are often indexed. Now, we make a transition to part 4. Query optimization is not magic. It's about reducing work, reducing data scanned, helping the optimizer. Now, the rule 1. Avoid select star. Select star fetches unnecessary columns, increases input-output operations, slows network transfer. Always select only required columns. Rule number 2. Filter early. Use where conditions as early as possible. Filtering early reduces rows, improves joins, and improves aggregations. Now comes rule number 3. Index where and join columns. If a column appears often in where, join, order by, it's a candidate for indexing. Rule 4. Avoid functions on indexed columns. Now let's go through an example which is bad, where year of order date function is equals to 2025. Now let's also go through a good example, where order date is between 2025 1st of January and 2025 December 31st. Functions can prevent index usage. Now the rule number 5. Use explain. Most databases provide explain and explain analyze. These show query plan, index usage, and scan type. Professionals always check execution plan before optimizing blindly. Now comes the part 5 of this module, which is about common performance anti-patterns. Let's talk about mistakes that kill performance. First anti-pattern, over-indexing. Too many indexes, slow inserts, slow updates, and increases storage. Indexes should be intentional, justified, and reviewed. Second anti-pattern is indexing everything. Not every column needs an index. Indexing low selectivity columns rarely helps and often hurts. Now, third anti-pattern, ignoring data growth. A query that works today may fail at a scale or may time out later. Always ask, what happens when this table has 1,000,000 rows or 100 million rows, right? Now, the fourth anti-pattern is blind optimization. Never optimize without measuring, without understanding the plan. Premature optimization is often dangerous. Now comes the part 6 of this module, which is about real world scenarios. Now the first scenario, slow dashboard query. Millions of orders filtered by date range, grouped by customer. Now the solution for this problem, index on order date, composite index if needed, and avoid select star. Now the second scenario, slow join query. Orders joined with customers, foreign key is not. Now the quick fix for this problem is index foreign key, reduce join columns, and check execution plan. Now comes the scenario number 3, which is about reporting versus transaction systems. OLTP, normalized index for writes plus reads. Analytics, denormalized index for reads, sometimes materialized views. Now comes the part 7, which is about interview perspective, how to talk about performance. Interviewers don't expect perfect tuning, deep engine internals. They expect awareness, trade-off thinking, real-world mindset. Good answers mention indexes, execution plans, data volume, and query patterns. Now, some of the bad answers that you should avoid are add indexes everywhere, use faster hardware. A little summary of this module. Why this module makes you professional. Anyone can write SQL that works, but a very few can write SQL that scales, performs, survives growth. This module moves you from beginner level SQL thinking to production ready SQL thinking. From here on, you won't fear slow queries. You will reason about performance, you will design smarter schemas, and you will earn trust in real teams. And with that, we make a transition to the next module. Now we enter module number 10, which is about views, functions, and stored procedures. Up until now, we've been writing queries directly on tables using select, join, and group by, subqueries, and even some window functions. That's great for learning SQL fundamentals. But in real-world organizations, analysts and applications do not write raw queries every time. Instead, SQL logic is abstracted, reused, and secured using database objects. This is where views, functions, and stored procedures come into the picture. Think of it like software development. Views are reusable layers, functions are calculation utilities, stored procedures are like back-end APIs running inside the database. Mastering these concepts separates someone who knows SQL from someone who works with SQL in production systems. Now, SQL views. What is a view? A SQL view is a virtual table created with a select query. It doesn't store any data by itself, but it stores the logic. Whenever you query a view, SQL runs the underlying select query. It fetches fresh data from the base tables. So remember, tables store data and views store business logic. Why views exist in real systems is the question you ask. There are four main reasons companies use views. First one, simplification. Analysts don't want to write complex joins every time. So the next reason is consistency. Everyone should calculate metrics in same way. The third reason, security. Views hide sensitive columns from certain users. The fourth and most important reason is maintainability. Change logic in one place and it updates everyone. And those were the four reasons why views really matter in real-world data analytics. Now, let's go through some examples. View example number 1, right on my screen, which is about employee details view. Right, we are creating a view on the employee details. Now, let's imagine you are an HR and you want employee details along with department names without writing joins repeatedly. Now, for that, let's create a view. So here, we are creating a view using the word or the keyword create and the keyword view. And this is the customized name that you are providing to your view, VW employee details. And inside this view, you will have this particular query where you are selecting employee ID, employee name, employee salary, hire date, and you're also using department, right? So here you can see the D letter. So this means you are using a different data table, which is department's data table and from employees, and you're joining that particular department's table based on the foreign key department ID and the keyword, the primary key in department table, which is department ID. Right, this is the query, and this is totally a join, and this is your view. Now, let's execute this so that your view is successfully created. So I have executed this query previously. So here you can see VW employees details already exist, right? If you want to extract the details from this particular view, all you need to do is select star from view, which is this one, and you'll have view here, right? Let's have a quick understanding. So when you execute this particular query, you create a reusable virtual table. You'll have a left join here, which ensures that employees without departments are still visible. For example, contractors or new hires, the Frank, which we have in our table, he doesn't have a department here, right? In our previous section, we have discussed about that intentional missing of department for Frank. And this view hides the complexity of joins. Now, so we have already used the view to extract the details, right? Now the key point, SQL executes the join behind the scenes. The user sees clean results. This is exactly how dashboards and BI tools work. Let's go through another example in view, which is department salary summaries. And what's the business question here? The business question is, what is the average and total salary per department? Now, let's go through the query. So here we have the second view, which says department salary summary. And we are creating this particular view using create and view keywords. And here we have department name, counting the total number of employees in each department. And we are aliasing this as employee count, and average aggregate function, and we are aliasing it as average salary. Sum aggregate function as the total salary alias from department's team. Left shown the employees on department ID from department's table with a department ID from employees table and group by department name. We already created this view. Let's say if we try to execute this, we'll get an error which says A view department salary summary already exists. Now, how do we use it? So you can just use the same select function. You can copy and paste it here and replace this particular view employee details with this particular view name, salary department, and enter to use this view. And there you go. So we have the department name, employee count, average salary, and the total salary, right? Now we enter a state where we should understand why views matter. So views matter when you're creating monthly reports, leadership dashboards, financial analysis. Without views, you would write the same query multiple times, risking inconsistent results and creating a maintenance headache. Now, a quick interview insight. Now, if someone asks you to explain what is a view, then you should not answer use store data. As we discussed in the beginning section, views never store any data, but they store only the logic. So the correct question would be, views store query logic. They abstract the complexity and keep the data dynamic. Now we transition to the next part, which is the SQL functions. Now let's understand what exactly is a function. A SQL function is a reusable block of logic that accepts input, returns a single value. It can be reused inside a select, where, order by condition, and you can think of it like an Excel formula that works directly on your data table. Why functions matter? Functions avoid repeating case statements in multiple queries, centralize business rules, improve readability, reduce errors. Now, let's also go through some examples. Now, the first example is salary category. Now, what is the business need here? The business need is we can classify employees as high, medium, or low salaries, right? Now, let's go through the query. So here we have the delimiter, and we are creating a function which is function salary category, which returns worker type of data 20 and deterministic begin here. So declare category, and the categories are high for employees having greater than 1 lakh salary, medium for employees having greater than or equal to 70,000 salary, and the other category is set to low. Now this function is already created. Now how to use the function? Now we are using the function here, select name, salary, and the function name as salary band from employees. Now let's quickly hit enter, and we have all the details right here. Now we have the second example for function, which is experience calculation. Now before that, let's see how the output works. So basically this particular query returns worker type of output, and deterministic, which is same output, always returns the same output, and helps the optimizer if or else if function, and encodes the business rules using the function. Now this approach keeps your queries clean, readable, and maintainable. Now as we discussed, the second function, which is experience calculation. What this does is it basically calculates how many years of experience does each employee have. Now, where is this being used? So for that, let's go to the workbench. So we have already created this particular function, which is function experience in years. Now we have deterministic, returns int type of data type, and we will use this particular function here and execute the query. So Alice, I think this particular industry was created recently, so none of the employees have crossed 1 year of experience. So that's great, not a big deal. Now we enter the next part, which is about stored procedures. And before that, let's understand the difference between function and a view. When comparing views and functions, there are few points to note. First, their purpose. A view is designed to be reusable query. It encapsulates the logic of one or more tables so that anyone can access it without writing or rewriting joins and aggregation. A function, on the other hand, is reusable calculation. It is meant to perform specific logic or transformations on data. Second, what they return. A view returns a result set, essentially behaving like a virtual table that you can query just like a regular table. A function, on the other hand, returns a single value which can be used directly in calculations or conditions. Finally, where they are used. Views are referenced in the from clause of a query, just like any other table. Functions, on the other hand, are used in select statements, where conditions, or even order by clauses whenever a value needs to be computed. In short, think of views as query containers and functions as calculation helpers that make your SQL cleaner and more reusable. Now, a quick interview insight. A good explanation is functions encapsulate calculations while views encapsulate data relationships. Now we enter into the stored procedures. Now what is a stored procedure? A stored procedure is a named set of SQL statements stored in the database. It can accept parameters, execute multiple queries, return result sets, enforce business workflows. Think of it as a backend logic running inside the database. Now, why stored procedures exist? They reduce application database traffic, improve performance, improve security, standardize business logic, and a lot more. Now, let's go through an example. Now, the example is about employees by department. And what's the business requirement? They return all employees for a given department. For that, let's go through a sample query on my screen. So here's a procedure that we recently created, and the procedure name is SP get employees by department. Now, it's already created and we cannot create this procedure once again. So let's simply call it. So there you go. So all the employees from engineering department are being called here. Now, why it matters? Applications call the procedure. Users never see the underlying tables. Logic is centralized. And now let's go through the next example on procedures, which is department salary summary. Now let's go through the procedure name, which is department salary summary. And since this is already created, we can just call it and execute it. So this is what we have. So we have engineering, HR, finance, marketing, and their employee count, average salary, and the total salary. Proceeding ahead, we have another example in procedures, which is in and out parameters. So here we have in and out parameters. So we are providing customer ID, and out will be the order count. Now this particular procedure is created. Now we can call this particular procedure and then select the total orders. And here we have the output, which is a total of 4 orders. Now, what was the business use case? They return total orders from a dedicated customer. Now calling it will give you the results. Now let's have a quick understanding between the stored procedures versus the function. When we compare functions and stored procedures, there are 3 differences to keep in mind. First, what they return. A function always returns a single value, making it perfect for calculations or deriving a specific result. A stored procedure, on the other hand, can return full result sets and even use out parameters, which makes it ideal for handling workflows or multiple operations at once. Second one, how they are being used. Functions can be called directly inside a select statement, so you can embed them in queries whenever you need a calculated value. Stored procedures, on the other hand, cannot be used inside a select. They are executed independently. Finally, their primary use case differs. Functions are primarily used for calculations like categorizing salaries or computing experience. Stored procedures, on the other hand, are better suited for workflows like fetching all employees for a department, updating multiple tables, or encapsulating business logic. In short, think of functions as a calculation tool and stored procedures as a workflow engine inside the database. Now, a final summary. Views improve readability and consistency. Functions improve reusability of logic. Stored procedures improve performance and control. Mastering these concepts prepare you for data analyst job roles, business analyst interviews working with production level databases, and backend and business intelligence systems. Now this finishes the module 10, and with that we transition to the next module. Now we have entered module 11, which is about transactions and error handling in SQL. Before we talk about SQL transactions, error handling, or even asset properties, let's take a moment to understand why this chapter matters so much. Until now, we've been writing SQL queries that read data, filter rows, and analyze information. But in real systems, SQL is not just about reading data. SQL is also responsible for changing data, and once data changes, the consequences become serious. In production systems, a single SQL mistake can lead to incorrect salaries being paid orders being duplicated, money being deducted twice, customer records becoming inconsistent, or the worst case, complete data corruption. This is where transactions come into play. Think of transactions as the safety net of SQL. They ensure that when multiple changes happen together, they either all succeed or nothing happens at all. This chapter will help you understand what SQL transactions really are and how databases protect data integrity, why asset properties are critical in enterprise systems, and how databases deal with errors gracefully. This is one of those chapters that separates beginners from professionals. Interviewers love this topic. Architects expect you to understand it, and production systems depend on it every single day. What is a transaction is our first question in this chapter. At a very simple level, a transaction in SQL represents a group of database operations that are treated as one single logical unit of work. Instead of executing each SQL statement independently and immediately making its changes permanent, the database deliberately groups multiple statements together and evaluates them as a whole. In practical terms, a database makes a promise. That promise is simple but powerful. It says either every change inside this group must succeed together or none of the changes should be applied at all. There is no middle ground and no partial success. To understand why this concept exists, let's step outside the world of databases for a moment and think about real world scenarios that almost everyone can relate to. Imagine you're transferring money from one bank account to another. This process always involves at least two steps. First one, money is deducted from account A. Second, the same amount of money is added to account B. These two steps are logically connected. One step cannot exist without the other. Now pause and ask an uncomfortable but important question. What happens if the system crashes after the money is deducted from account A but before it is added to account B? From a user's perspective, that situation is completely unacceptable. Money has vanished without reaching its destination. Trust in the system is broken. Databases face the exact same challenges. In SQL, real-world operations rarely involve a single statement. A business process might require updating one table, inserting records into another table, and deleting rows from a third table. Each of these statements may succeed individually, but from a business perspective, they are not independent. They are a part of a single operation. If one of these steps fail, allowing the others to remain would leave the database in an inconsistent and unreliable state. That is why these actions must behave like one combined operation, not three separate ones. This logical grouping of multiple SQL statements into one indivisible unit is what we call a transaction. Now, why transactions are needed is your next question. Without transactions, databases would behave like a collection of isolated commands that execute independently without awareness of each other. While this might sound simple, it quickly becomes dangerous in real systems. Imagine a database that executes every SQL statement immediately and permanently without any ability to reverse or group changes. In such system, failures would create chaos. Partial updates would become common. Data mismatches would appear across tables. Relationships defined through foreign keys would break silently. Reports and analytics would start showing numbers that do not align with reality. Let's take a very common example from an e-commerce system. An order is created in the orders table. Payment processing begins. The payment fails due to a network issue or insufficient balance. However, the inventory system has already reduced the stock count for that product. Now the database shows an order that was never paid for or inventory that no longer exists. This is not a rare edge case. It is exactly the kind of scenario that happens in real systems every day if the transactions are not used correctly. Without transactions, SQL would simply execute each statement in sequence and move on, completely unaware that something went wrong midway. The database would not automatically understand that these operations were connected logically. Transactions introduce control and intent into this process. They allow us to clearly tell the database when to start tracking changes, when to confirm and permanently save those changes, and when to cancel everything and revert back to the original state as if nothing ever happened. This level of control is not optional in modern systems. It is essential. Banking platforms rely on transactions to protect financial accuracy. E-commerce systems use them to ensure orders, payments, and inventory always remain in sync. ERP systems depend on transactions to maintain consistency across complex business workflows. Payroll systems cannot afford partial salary updates. Analytics pipelines and data warehouses rely on transactions to ensure reporting data is trustworthy and complete. In short, transactions exist because real systems fail, networks break, users make mistakes, and databases must be prepared for all of it without compromising data integrity. Now, we land into the next part, which is begin, commit, and rollback. It is the core of SQL transactions. Now that we understand what a transaction is and why transactions are necessary, it is time to focus on the three most important commands that make transactions actually work in SQL. These commands form the backbone of transactional control in every major database system used in the industry today. Those three commands are begin, commit, and rollback. You will encounter them in MySQL, PostgreSQL, SQL Server, Oracle, and almost every enterprise-grade relational database. While syntax variations may exist, the underlying concepts are universal. If you understand these three commands deeply, you understand how databases protect data from mistakes, failures, and unexpected crashes. Let's take them one by one and truly understand what each command does, not just at a syntax level, but at a conceptual level. Now, let's start with begin, or also known as a start transaction. The begin statement marks the starting point of any transaction. Conceptually, begin tells the database something very specific and very important. It tells the database, from this moment onward, do not permanently save any changes yet. Before begin is executed, every SQL statement typically operates in what is known as auto commit mode. That means each individual statement is immediately finalized and written permanently to the database. Once executed, there is no easy way to undo it. Begin changes this behavior. When you execute begin, the database switches into a controlled state. From this point forward, every insert, update, or delete statement is tracked internally by the database engine. The changes are applied in memory or in temporary structures, but they are not yet committed to the permanent storage. This distinction is extremely important. At this stage, the database remembers what has changed. The original data is preserved internally. Other users do not see the changes. The system is effectively waiting for your final decision. A very helpful way to think about begin is, imagine opening a draft document. You start editing the document, but nothing is published yet. You can add text, remove sections, or rewrite entire paragraphs. But until you click save or publish, the changes are private. Begin creates the same draft-like environment for database operations. This is why begin is often described as the moment when the database starts recording intent rather than finalizing the action. Now, visibility of changes after begin. One subtle but critical aspect of begin is visibility. Once a transaction has started, the changes made inside that transaction are usually not visible to other users or sessions. This means you may update a salary inside transaction. Imagine multiple analysts running reports while data is half updated. Without isolation, reports would show unpredictable results. Begin creates a protected workspace where changes can be reviewed, validated, and finalized safely. Now let's dive into commit. Once you have executed all the necessary SQL statements inside a transaction and you are confident that everything is correct, you use the commit command. Commit tells the database that everything that has happened since begin is correct. Make it permanent. This is the point of no return. When commit is executed, the database takes all the track changes and writes them permanently into the disk. At this moment, the transaction ends. The database is updated. Other users can now see the changes. The old data is replaced by the new data. From a conceptual perspective, commit is equivalent to clicking save or publish. Until this moment, everything was reversible. After this moment, the changes become a part of the official database history. It is very important to understand that There is no undo after you use commit. Once the database confirms a commit, the transaction is complete. If a mistake is discovered later, it must be corrected with a new SQL statement, not by reversing the commit itself. This is why commit should only be executed when all statements have run successfully, all constraints are satisfied, the data makes logical sense, the business rule has been fully applied. Professional developers and database administrators treat commit with respect because it represents finality. Now we have durability and commit. Another important idea connected to commit is durability. When a database confirms a commit, it ensures that the changes are safely returned to persistent storage. Even if the server crashes immediately after, the committed data will still exist when the database restarts. This guarantee is one of the reasons relational databases are trusted for critical systems. Commit is not just a logical confirmation. It is a promise that the data will survive failures. Now we have rollback. While commit represents success, rollback represents recovery. Rollback tells the database something went wrong. Cancel everything that happened since begin. This could be due to a constraint violation, a failed business rule, an unexpected error, a manual decision by the user, or even a system failure handled gracefully. When rollback is executed, the database discards all track changes from the current transaction. Every insert, update, or delete is undone, and the database returns to its exact previous stable state. It is as if the transaction never happened. This behavior is what makes transactions so powerful. Instead of leaving behind partial updates or corrupted data, the database cleans up everything and restores order automatically. This is why rollback is often called the panic button of SQL transactions. When something feels wrong, rollback ensures safety. Now we deal with rollback and data integrity. Rollback protects data integrity in situations where partial success would be dangerous. Consider again the banking example. Money deducted from one account, errors occur before adding money to another account. Rollback ensures that the deduction never truly happened. The system goes back to a consistent state where balances still make sense. Without rollback, errors would permanently damage data trust. Mental model for transactions. A very effective way to remember how these commands work together is to use a simple mental model. Think of it like this. Begin means start recording changes. Commit means accept and save changes. Rollback means forget all changes. And this mental model is powerful because it works across databases, tools, and even interview discussions. Whether you're working with MySQL, PostgreSQL, SQL Server, Oracle, or any other enterprise database, the behavior remains conceptually the same. The syntax may differ slightly, but the intention never changes. Transaction lifecycle is our next concept. Every transaction follows a clear and predictable lifecycle, even though the most users never see it happening. The lifecycle begins when a transaction starts. This may happen explicitly using begin or implicitly when auto commit is disabled. At this point, the database prepares itself to track changes rather than finalizing them. Next, SQL statements execute one by one. Insert, add rows, update, modifies values, and delete, removes records. Each change is carefully tracked internally by the database engine. During this phase, the database maintains enough information to undo everything if required. This is where transaction logs and internal buffers come into the play. Although those mechanisms usually remain hidden from the users, after all statements are executed, the transaction reaches a decision point. One of the two outcomes must occur. If everything is correct, commit is executed. The database permanently saves the changes and ends the transaction. If something goes wrong, rollback is executed. The database discards all the changes and returns to the previous stage. What is crucial here is that there is no third option. A transaction can never end in half-completed state. The database guarantees that it will either fully succeed or fully fail. This all or nothing behavior is what makes transactions more reliable. Why this lifecycle matters? Although this lifecycle is invisible to most users, it is absolutely critical behind the scenes. Every time you place an order, receive a salary, update customer information, generate financial reports, you are relying on this lifecycle to behave correctly. Understanding this flow not only helps you write safer SQL, but also helps you think like a system designer. It teaches you to anticipate failure, plan recovery, and respect data integrity. Now, with that, we make a transition to the asset property. Now, a quick introduction to asset properties and error handling in SQL. Now that we have built a strong understanding of transactions and we clearly know how begin, commit, and rollback work together, it's time we move into one of the most important theoretical foundations of SQL and database systems as a whole. This section is not just theory for the sake of theory. It explains why databases are trusted, why transactions work reliably, and why SQL systems can safely power critical business operations across the world. Every reliable transaction database follows a set of guarantees known as ACID or asset properties. Asset is not a buzzword. It is not any academic concept that exists only in textbooks. Asset is the reason why banks do not lose money, airlines do not double book seats, and enterprise can run large-scale systems with confidence. The word asset is an acronym, and each letter represents a functional fundamental property that a transaction must satisfy. A stands for atomicity, C stands for consistency, I stands for isolation, and D stands for durability. If you truly understand these four properties, you understand why databases are considered reliable systems rather than simple storage tools. Let's explore each one of them carefully, one at a time. First one is atomicity, all or nothing. Atomicity is often the earliest asset property to understand conceptually, but it is also one of the most powerful. Atomicity means that a transaction is treated as a single indivisible unit of work. In simple terms, a transaction must either complete entirely or not happen at all. There is no such thing as partial success. When a transaction contains multiple steps, the database does not allow some of them to succeed while others fail. Either all steps are applied successfully or every single change is undone. Imagine a transaction that contains 10 SQL statements. According to atomicity, the database guarantees one of the two outcomes. Either all 10 statements succeed or none of them are applied. There is no scenario where 5 succeed and 5 fail. This guarantee becomes especially important when systems fail unexpectedly. Consider what happens if a transaction is executing and the system crashes during the ninth step. From the user's perspective, this crash is unpredictable and unavoidable. However, the database still guarantees safety. It detects that the transaction did not complete fully and automatically rolls back all the changes made by that transaction. This is atomicity in action. Atomicity prevents half-written records from entering the database. It prevents partial updates that could break reports, analytics, or business workflows. It ensures that relationships between tables remain intact and logical. Without atomicity, databases would be extremely fragile systems. Every unexpected shutdown or error could leave the data in a corrupted or unusable state. Atomicity is one of the primary reasons databases are trusted in financial systems, healthcare platforms, airline booking engines, and other mission-critical applications. When money, lives, or legal obligations are involved, almost correct is not acceptable. Atomicity ensures correctness or nothing at all. Now, the next one, C for consistency. From one valid state to another, while atomicity focuses on all or nothing, consistency focuses on correctness. Consistency means that a transaction must move the database from one valid state to another valid state. A valid state is defined by the rules of the database and the rules of the business. These rules include technical constraints such as primary keys, foreign keys, unique constraints, and not null conditions. They also include business rules such as salary limits, account balances, or workflow conditions. For example, if a table requires that every employee must have a unique employee ID, consistency ensures that a transaction cannot insert duplicate IDs. If an order must reference a valid customer, consistency ensures that orders cannot exist without customers. When a transaction violates any of these rules, the database does not allow it to succeed. Instead, the transaction fails and is rolled back. Consistency ensures that invalid data never enters the system. It guarantees that every committed transaction leaves the database in a state that makes sense according to the defined rules. It's important to understand that consistency does not mean the database automatically knows what is right for your business. Instead, it enforces the rules that you as a designer or developer define. Once those rules are defined, consistency becomes the database's responsibility. This is why well-designed schemas matter. The stronger your constraints and rules, the stronger the consistency guarantees your database can provide. Consistency is what allows analytical teams to trust reports, auditors trust financial records, and engineers to trust system behavior. Now we have the next one, I for isolation, protection in a multi-user world. Modern databases are multi-user systems by design. At any given moment, hundreds or even thousands of transactions may be executing at the same time. Isolation answers a very important question. What happens when multiple transactions interact with the same data simultaneously? Isolation means that transactions should not interfere with each other in a way that causes incorrect or unpredictable results. In simple terms, isolation ensures that one user's incomplete transaction does not affect another user's transaction. Imagine one transaction is updating employee salaries, but it has not yet committed. At the same time, another user is running a report that calculates average salaries. Without isolation, the report might see half updated data, leading to incorrect results. Isolation prevents such scenarios. It ensures that uncommitted changes are not visible to other transactions. Dirty reads are avoided, data remains predictable and stable. Different databases implement isolation at different levels, allowing trade-offs between performance and strictness. These are known as isolation levels. While the strictness may vary, the core principle remains unchanged. Isolation exists to ensure that concurrency does not break correctness. Without isolation, databases would become chaotic under load. Reports would fluctuate unpredictably, updates would conflict, and debugging would become nearly impossible. Isolation is the silent guardian that allows multiple users to safely share the same database. Now comes the last one, D for durability. Once committed, always committed. Durability is the final asset property and it focuses on permanence. Durability means that once a transaction is committed, it will remain committed, even in the face of system failures. Once commit is executed successfully, the database guarantees that the data is safely stored. Even if the power goes out, the server crashes or the database restarts, the committed data will not be lost. This guarantee is achieved through internal mechanisms such as transaction logs, write-ahead logging, and persistent storage strategies. Before a transaction is considered committed, the database ensures that enough information has been written to disk to recover the changes if necessary. Durability is the reason databases can recover safely after crashes. When a database restarts, it replays committed transactions and discards incomplete ones. Without durability, a database crash could result in data loss, broken trust, and catastrophic failures. Durability transforms databases from temporary data stores into reliable systems of record. Why asset matters in real systems? At this point, it should be clear that asset properties are not abstract ideas meant only for exams or interviews. They are the foundation upon which real systems are built. Banks rely on asset to ensure financial accuracy. Airlines rely on asset to manage reservations without conflicts. E-commerce platforms rely on asset to synchronize orders, payments, and inventory. Enterprises rely on asset to run payroll, compliance systems, and analytics pipelines. When interviewers ask about asset properties, they are not testing memorization. They are testing whether you understand why databases can be trusted or not. A candidate who understands asset demonstrates system-level thinking, not just SQL syntax knowledge. Now we make a transition into error handling in SQL transactions. Now, let's move on from guarantee to reality. In the real world, errors are inevitable. Networks fail, constraints are violated, input is incorrect, applications contain bugs, systems crash unexpectedly, and the key question is not whether errors will happen. The key question is how databases handle these errors without compromising data integrity. The transactional system's error handling is deeply connected to asset properties. When an error occurs inside a transaction, the database does not panic or partially commit changes. Instead, it ensures safety. Errors typically trigger rollbacks. This means the database cancels all changes made by the transaction and returns to a stable state. Some databases automatically roll back when a fatal error occurs. Others require explicit rollback commands regardless of the implementation. The principle remains the same. Errors must never leave the database in an inconsistent state. This principle is non-negotiable in reliable systems. Now, the conceptual workflow of error handling. The conceptual workflow of error handling in transaction is simple and elegant. First, a transaction begins. Next, the SQL statements execute one by one. The database continuously monitors for errors. If an error occurs at any point, the transaction is rolled back. If all statements succeed, the transaction is committed. This flow is deeply embedded into enterprise systems, even if the developers are not consciously aware of it. It is this flow that allows databases to gracefully handle failures instead of amplifying it. This is why this chapter is career critical, and this chapter may feel theoretical, but it is one of the most practical chapters in SQL. Understanding transactions, asset properties, and error handling improves system design thinking. It prepares you for production environments. It helps you answer senior level interview questions with confidence. It builds credibility as a data professional. Many people know how to write SQL queries. A very few truly understand how databases behave under failure, load, or concurrency. This chapter closes that gap. Now, let's summarize everything that we have covered so far. Transactions group multiple SQL operations into a single logical unit of work. Begin starts tracking changes. Commit saves changes permanently. Rollback cancels all changes. Asset properties guarantee reliability, error handling protects data integrity. Transactions form the backbone of enterprise systems. If SQL were a building, transaction could be its foundation. Without them, everything collapses. And that brings us to the end of this chapter. And now we transition to the next one. Let's imagine you just joined a company as a data analyst or a business analyst, and your manager gives you one of these CSV file and say, we sell products across multiple regions. We run marketing campaigns. We generate traffic, leads, and orders. And I want you to find the insights that can drive revenue and reduce losses. That's exactly what this project is all about. In this module, we will build a complete SQL sales analytics project using real-world sales data. We will move step by step, just like the actual analytics rule does. By the end of this project, you will know how to analyze sales data performance using SQL, how to convert raw data into business insights, how to write interview-ready SQL queries, how to explain your analysis like a professional data analyst. Now, before we get started with data understanding and everything, let me show you a quick way to understand how to import data. So this particular data is from an Excel workbook, just as we discussed. So it can be either an Excel workbook or it can be an Excel CSV file. So this is my data. So we'll be having order ID, order date, delivery date, order status, and all those things. So if you observe closely, on each and every column ID, I have not left any spaces. You can either go with an underscore or don't leave any space, because in real world data analysis, if you're having spaces in between the column header names, then you might face issues while writing the queries. So for safe side, just understand one thing: no spaces in between the column header names. Okay. And then make sure you save this as .csv, because in SQL workbook, we import data in the form of .csv files. So that's one major thing. Now, let me show you my data location. So we have data in the download section. Here we have the file. So if you save the same file in the form of .csv, this is how it's going to look like. There you go. And also you need to remember the files, the date files should be saved in the form of date, and the specific format should be year, month, and date, right? So let me go through the workbook and check if my data is according to my request. So here we have the data already. Let me also show you how to load it, not a worry. So there you go, we have the data in form of year, month, and date. So this is how you basically have the date files. So what I'm basically telling you is, before you load the data onto SQL workbook, when you have the opportunity to work on it on Excel, then why don't you use it, right? So most of the times, before you load the data, in on any of the platforms, it can be a MySQL Workbench, or it can be a data visualization tools like Tableau, Power BI. Make sure you clean the data and data is ready for analysis, right? So we've already gone through how to, change the data type of the column, how to change some elements, how to replace filter and all those things, right? So based on that analysis, or based on that approach, you might have to work on the data cleaning first. And once you're satisfied with it, you can close and load the data. So now back to MySQL Workbench. So this is the location. And now if you come back to the MySQL Workbench, now here you can see the databases. You can select any of the schemas. So this is my schema. So here what I'll do is I'll go for an option which says data import or visit, right? From here, I have already given my location, or else if your location is in a different location, then you can just browse and go to the location and then just select the file, and here you go to the next option, and here you have the next, right? So you already have the table. So in case if you don't want to delete the table and import a new one, you can just cancel it. But in case if you want, you are exploring, don't worry, this particular data set will also be provided with to you in the description box below. And if you want to just load the data, you can just proceed with it. And I'll use the existing, so I don't want to delete the data table. So this is how you basically load the data table. And in case if you want a little bit more clarity, I'll also drop a tutorial link in the description box below, which will explain you how to load data from Excel files. So that's the approach. Just right click, and here you go to the table data import wizard and just select the location where you have it and then load the data. That's basically it. And once you are loaded the data, what you can do is select the database. I'll just use interview database, and then here show tables. So these are the tables you have, and this is our data set, which is sales data, and you have an overview. And once you load this data, you might be having a few errors on the column names, sometimes, very rarely, 1 out of 100 cases. So I had an issue due to some spacing issue on the name. So I quickly changed this, but let me expand this. Yeah, I quickly expanded or selected the column name. What I did is I just copy the field name and paste it over here. So this was the initial field name, and I changed it to my requirement, which is order ID. And once you do it, the column header name from this got changed to the expected name, which is order ID. And now we start with the business analysis and questions and queries, right? So this is how you quickly load the data to the MySQL Workbench platform, and then you start with the business queries. So this was a basic understanding of how to load the data and understand what's present in our data. Now let's proceed to deep dive into the data set. So now comes the data understanding. Before writing even a single SQL query, the first thing an analyst does is understand the data. Our dataset contains the following key information. We have order level data, which includes order ID, order date, and delivery date, order status, such as it is delivered or cancelled. We also have customer information, which includes customer ID, first name, and the last name, which state or region he or she belongs to. Then comes the product and sales metrics, which includes product name, product category, product subcategory, the quantity of the product sold, cost to the company to make it, and the revenue details which we made out. And also we can have the profit column, and finally the marketing funnel metrics, which include the traffic number on the website or the store's site, and the total number of leads we had, total number of orders we received, and all those things. This tells us something very important. This is not just sales data. This is sales plus marketing plus operations data all combined together, right? So we have the sales data, which has product price, cost of the company, revenue, and all those details. And we also have marketing data, which is about leads, revenue, and traffic, and all those orders, and the product data as well. So this is a combination of all three of the data sets together. And most of the times what happens is these three different data tables will be stored in three different data modules altogether. So we also had data modeling part in this particular full course. So you can go through that once again to get a full detail on this particular aspect, right? So most of the times the data will be stored in different tables so that we maintain a schema of data sets. Most importantly, we follow the star schema, and all the other tables are related to one another through a foreign key, right? Using foreign key, we can combine different tables to the fact table. So here the fact table will be the orders data table or the CS data table, and product data, marketing data, and all those things will be the dimension tables. But now to eliminate the confusion and keep the project more simplistic, we have combined all this together in one single data table, and we have it in one table here itself. So this means we can analyze revenue, profitability, conversion funnel, regional performance, product performance, order cancellation, and all those aspects in one single go. That's exactly what companies expect from SQL analysts today. Now, the project problem statement. Let's clearly define our project goal. So the problem statement is analyze sales, performance, profitability, and marketing efficiency across different regions, products, and customers to identify revenue drivers and business bottlenecks using SQL. It is simple, clear, and business focused. Now, let's get started with the questions and their answers. So the first question. So I have already added the questions here to save time and also the queries, and you can have this code documentation readily available for you in the description box below. So to follow up with me, make sure you copy the dataset and the queries document with you and be ready with your SQL workbench so that I will explain you on the go what's happening here, and you can also follow along with me and run the query with me and get the output. And if you're getting anything different or if you are facing any difficulty, please feel free to drop them in the comment section below and we will address that as soon as possible. Now, the first question is, what is the total revenue, total cost, and total profit? Let's understand this a little bit more detail before we start with the solution approach. So now what we are doing is we are understanding total revenue, cost, and profit, which is fundamental for any business. This analysis provides a snapshot of overall financial health of the company. Revenue indicates the total income generated from sales alone. Cost shows total expenses incurred while manufacturing that particular product. And profit reflects the net gain. Now, monitoring these metrics helps decision makers evaluate the business performance and identify whether operational strategies are generating the desired financial outcomes or not. Now, let's go through the approach design, right? The query aggregates the values of revenue, cost to company, and profit across all records using a sum function. Each aggregation is labeled with an alias for clarity. For example, we have total revenue, total cost, and total profit. This approach ensures we get a single summary row representing the company's overall performance. Now, let's go through the query. So, as discussed, we have the sum of revenue and we have aliased it as total revenue. And total cost to company is aliased as total cost, and total profit is aliased as total profit as here, right? And you already know what is the meaning of aliases. It's just an alternate name or the user defined name for your column names or the output, right? So this was the indentation followed. But in case if you are someone like me who likes to have all the columns in one line and the table name and then get ahead with the indentation when you actually deep dive into queries, then this approach is fine for you. But in case if you are someone who is comfortable with naming the columns line by line, then you can follow the line by line approach. So this is the query that we will be executing now. So let's quickly execute this. And there you go. So you have all the details. So this is your total revenue, which is around 533 million. And the total cost is about 101 million. Or is it 10 million? I think, yeah. And then we have total profit. So this was the total cost we invested, and this is the total revenue we generated, and this is the total profit that we made. So this is how you go ahead with the first question. And now we come across the second analysis for the day. So the second analysis or the second question of the day is, what is the monthly revenue trend? Now, let's understand this question. So this question is basically about tracking monthly revenue trends that help businesses understand seasonality, sales growth, and revenue fluctuations over time. By visualizing these trends, organizations can identify peak periods, forecast future revenue, and make informed marketing or operational decisions. So it's basically like if you're going through a Diwali festival or Dasara or Christmas or any of the Eid or any of the special days like Independence, Republic, right? So you can take out the seasonality of that special occasion and then boost up the sales so that making those offers look more lucrative and make some more sale out of it. So that's the overall business perspective of this particular query. So it helps in evaluating the effectiveness of promotions and campaigns across different months. Now let's go through the approach. So this is the query. Now let's understand or deep dive into this particular query. The query uses date format function to extract year and month from order date and then groups the data by this formatted month. The sum of revenue function calculates the total revenue per month. Ordering by month ensures that the result set follows a chronological trend, making it easier to interpret temporal changes in revenue. Now, let's quickly execute this query and see the output. So here you have the date format, which extracts the year and month as provided here. So you have the percentage Y for year and percentage M for month, and it is aliased as month. And here you have sum of revenue, and we have aliased it as monthly revenue from the table, which is sales data. So this is another approach where you write the query. So here the column headers or the column names are mentioned in line by line. So you can also follow this one, this kind of indentation or this kind of indentation. Both are good enough based on your comfort, right? And then we are grouping by date format and ordering by month. Now let's quickly execute this query, and we will be using the shortcut method, which is Control Enter, and there you go. So we have date and month wise analysis. So here we have 2021 data starting and we are ending data with 2024. So this is the overall sales data, and here we have monthly revenue numbers. Now let's proceed with the next question, which is about which product categories generate the highest revenue. Now let's understand this question before getting started with the query. Now the third question is about which product categories generate the highest revenue. Now let's go through the explanation. Knowing which product categories contribute to the most revenue allows businesses to focus on high performing segments and optimize their product mix. It also helps in inventory planning, promotional strategies, and prioritizing resources towards categories with maximum financial impact. Now that was the backstory behind this particular query. Now let's go through the approach and query design. This query groups data by category, column, and calculates total revenue for each category using the sum of revenue function. The results are sorted in descending order to immediately highlight the top earning categories. This aggregation approach provides a clear ranking of categories based on their revenue contribution. Now, let's go through the query and understand what's happening here. So here, as discussed before, we have the following columns: category, sum of revenue, which is aliased as total revenue from sales database. And here we have category. We are grouping them by category and we are ordering in descending order so that highest revenue numbers comes on the top and the lowest revenue numbers comes below, right? Now let's quickly execute this particular query. We've also been through the group by and order by filters. So you can go through that in the previous chapters. And now let's execute this. And there you go. So the category FMCG, furniture, home appliances, clothing and electronics are the top revenue generators. And out of all those, FMCG is the highest revenue generator, almost next to the furniture. So you can next time, so you can focus on these two categories so that you can earn maximum benefits. Now, let's go through the next question, which is about the top 10 products by profit. So the fourth question is about top 10 products by profit. Now, what's the explanation for this particular approach? So identifying the most profitable products is crucial for maximizing business margins. While revenue indicates sales, volume, profit, it provides insight to the financial efficiency of the products. Highlighting top products by profit helps prioritize marketing, production, and strategic investment decisions. Now, this was the backstory for this particular question. Now, let's understand how the query design and approach is for this particular question. The query first groups the records by product and calculates the total profit using sum of profit. Then we use order by to total profit in descending order and the products from the highest to lowest order. The limit 10, right? So we wanted to identify the highest number of products or the highest selling products, but we didn't have a limit here. So small improvement here. We want to find out the top 10 products, right? So if you want to find out the top n number of products, you can use limit clause and provide the n number. Let's say if you want top 5, then you can use limit 5, and in our case, we are using the limit 10 because we wanted to find out the top 10 products, right? So the limit 10 clause ensures only top 10 products are retrieved, giving a focused view of the most lucrative offerings. Now, let's go through the query and execute it. So here we have a product and sum of profit as total profit. And from sales data, we are grouping by product and order by total profit in descending order. And it is top 10, right? So limit 10, enter, and there you go. So we have a washing machine, air conditioner, soap, headphones, and all the other top 10 products which are highest selling. So the next time in the marketing aspect, you can share this data with the marketing team so that they can run a couple of more ads and campaigns on washing machine, air conditioner, and soap, so that by the end of the year, you'll have more profits in the upcoming sales analysis. Now, proceeding further, we have section B, which is about the customer analytics. And here, the first question or the overall fifth question that we are facing is, how many unique customers do we have? Now, let's go through the question a little bit more. So to deep dive how many unique customers we have, we are basically here trying to understand the size of customer base, and it is very vital for any business. It is vital for assessing marketing research and growth potential as well. Knowing the number of unique customers helps you segmenting audiences, target retention campaigns, and estimating lifetime value per customer. It also serves as a foundation for analyzing repeat business and customer loyalty. Now that we have a briefing on why this particular question is placed, let's go through the query approach and design. The query uses count of distinct of customer ID. So this is a part. So basically we have two aggregate functions here, the count function as well as the distinct function here to calculate the number of unique customers. This ensures that even if a customer has placed multiple orders, they are only counted once. This approach provides an accurate representation of the business actual customer base. Now, let's go through the explanation. So here, as discussed, we have distinct. First, we are filtering out the customer so that the customer ID is unique. There are multiple possibilities where one customer ID could have placed multiple orders, right? So multiple entries in rows. So what we're doing here is basically you're finding one repetition of each customer, and then we are counting the total number of customers and aliasing them as total customers. And then we are selecting this from sales data. So let's quickly run this query, and there you go. We have about 3,216 unique customers in our data set, and these might have place multiple orders. So the overall count of rows could be a little different. Now, let's proceed with the next question in our customer related queries. So the next question is, which states contribute to the most revenue? So let's deep dive into this question a little bit more. So identifying revenue contribution by state helps businesses understand the geographical performance. It highlights high performing regions that can be targeted for growth and underperforming states that may need marketing support or operational improvements. This analysis is crucial for regional strategy, distribution planning, and resource allocation. Now that we have a brief understanding of why this question was asked, let's go through the query approach and query design. So this is our query. Let's understand this a little bit. The query groups sales records by the state column and sums the revenue of each state using the sum of revenue function. Results are ordered in descending order of revenue to immediately identify top performing states. This aggregation approach provides a clear picture of geographical revenue distribution. Now let's quickly run the query and see the output. So as discussed, we have state here and sum of revenue as total revenue alias and people name. So we are here trying to perform a group by function and we are ordering revenue in descending order. And in case if you are having that question, can we find out the top 5 performing states? Yes, we can just limit them by 5 and we will have top 5 states here: Telangana, Odisha, Delhi, Maharashtra, and Kerala. And if you remove this particular limit function, you will have the entire states list right here, right? So all the states and their performance. Now with that, let's go to the next question, which is the seventh question and third question in customer analytics. So here we are trying to find out average revenue per customer. Before we execute this query, let's go through a little bit more deep dive into this particular question and why this was being asked from an interview perspective. So, average revenue per customer. Why this question is asked? Average revenue per customer, or in short, ARPC, measures the value each customer brings to the business. It is an essential metric for evaluating customer profitability and effectiveness of sales or marketing strategies. Higher ARPC indicates better monetization on the customer base and helps in targeting premium customers. Now that we have an understanding why this question is being asked, let's go through the approach in solving this question and the query design. The query groups data by customer ID and calculates the average revenue using average revenue function. This approach ensures that we get per customer data view of revenue and highlighting differences in spending patterns across the customer base. Now, let's go through the query and execute this. So, as discussed, we have customer ID, average revenue as average revenue per customer aliases, and we are grouping by customer ID. Now, let's execute this query and see the output. So, here, based on their revenue, here we have the highest spending or the average spending of each customer. Right? So, there are a few customers who have been registered onto the website, but so far they haven't made any sale or purchase from our website. And apart from that, we also have a few customers which have already placed some orders, and there are a few customers who are repeated, and there are a few premium customers as well with the highest number of sales from the website. Now, we enter into the next section of this particular project, which is about regional performance analysis. So, in the regional performance analysis, we have the eighth question or the first question in this particular part, which is about revenue contribution by region. So, let me scroll this a little. This is our question and the query. Now, let's go through the question and understand a little more detail why this question is being asked. Now, revenue contribution by region is very important. Regional revenue analysis provides insight into which areas generate the most income. This helps in strategic planning for expansion, marketing campaigns, and allocation of sales resources. It also identifies strong and weak regions to improve operational efficiency. Now that we have a briefing on why this question is being asked, let's go through the approach on what basis this question can be solved and the query design. The query groups the dataset by region and sums the revenue column. This aggregation ensures each region total revenue is calculated, providing a concise overview of regional performance. Now, let's go through the query and execute this. So, as discussed, we will be having region and summation of revenue and alias as total revenue from sales data, and we are grouping by region. Now, let's execute this query, and there you go. So, we have overall country wise East region sales revenue, West region, Central region, South, as well as North. So, region wise, these are the sales numbers. Now, let's dive into the next question, which is about profit margin by region. So, this is our question and query. Before we execute the query, let's understand what is the meaning of this question or what's the reason behind this question and understand the query approach and design. So, profit margin by region is really important. Understanding profit margins at the regional level helps businesses assess operational efficiency and pricing effectiveness. A region might have high revenue but low profit margins. This indicates cost ineffectiveness or discounts impacting profitability. Now, this was the reason behind why this question was asked. Now, let's discuss the approach to solve this question and what is the query design. The query calculates profit margin using the formula, which is sum of total profit divided by sum of total revenue into 100, which is named as profit margin or alias as profit margin from sales data. And we will also be using a filter function here where revenue should be greater than 0, which ensures division by 0 is avoided. Now, along with that, we will be using a round function, which enhances the readability of percentages. Now, let's go through the query and execute this. So here we have it. So we are selecting the region column, and then here is the function or the mathematical calculation, and we are aliasing it as profit margin percentage from sales data. This is the filter that we were talking about. Revenue should be at least greater than 0, right? And you can have at least 1% revenue, but it shouldn't be 0. That's why we have using this filter, and we are grouping by region. Now let's execute this query and see the output. There you go. So we have East region profit percentage margin, South, North, West, Central, so on. So these are the profit margins here. Now we dive into the next section, which is marketing funnel analytics. Let me point this out. This is very strong analytical section and great for interviews. And in this, the first question we have is traffic to lead conversion. Most of the times, if you are a business analyst aspirant or a data analyst aspirant, or you're already working in business analytics or data analytics, then these are the most common figures that you will be listening or saying in your meetings. Traffic to lead conversion, lead to order conversion, right? So these are some important things that you go through in interviews or in a business analyst day-to-day life, right? So this is one such question, traffic to lead conversion rate. Now, let's understand the business aspect behind this particular question. And along with that, we'll also see why this question was being asked and what's the solution to this particular question and what's the design of the query. So traffic to lead conversion is critical. Conversion from website or store traffic to leads show how effectively marketing channels are capturing potential customers. This metric helps evaluate campaign efficiency and the quality of the visitor engagement, forming a critical part of marketing analytics. Now, let's go through the approach to solving this question and also the query design. The query sums the total leads and traffic across all records and calculates the conversion rate as leads divided by traffic into 100. And we also use a round function to format the percentage. Aggregation across the dataset provides an overall conversion insight. Now, let's go through the query and execute this. So, as discussed, we will have the function sum of leads divided by sum of traffic into 100, and we are giving a round function as well. So we are rounding up the decimal values to 2 decimal values, right? So this is the total function here, and we are aliasing it as traffic to leads conversion percentage, and we are selecting this data from sales data, right? So let's execute the query, and here we have the output. So traffic to lead conversion is 10%, which is pretty decent. Now, along with that, let's go to the second question, which is about lead to order conversion, right? So the traffic will be on your website, and if your marketing is really good, then they convert into a lead which show interest in your product, right? And we want that lead to convert into an order. That's the critical point, right? So this is the intention behind asking this question. Anyways, let's deep dive, right? And after that, we'll also go through the approach. Lead to order conversion indicates the effectiveness of sales process. It measures how potential customers, basically leads, are successfully converted into paying customers which place an actual order. This is basically done for highlighting areas for sales optimization. Now let's understand the approach to solve this question and the query design. The query sums orders and leads where leads exist and calculate them as orders divided by leads into 100. We also use a where clause as a filter where it filters down the leads having number greater than 0, and this condition avoids division by 0 errors and ensures the calculation is meaningful for relevant data points. Now, let's go through the query and see the output. So this is where we had the total orders divided by total leads into 100. And we also have the round function here where we will have the decimal values limited to 2 numbers, and we are aliasing it as lead to order conversion. And leads filter here, it should be greater than 0. Now, let's execute this query and see the output. So lead to order conversion is somewhere around 0.9%. Now, with that, let's move into the next question, which is about overall funnel conversion. So traffic to order is this particular aspect. Now, let's go through the intention behind asking this question. Traffic to order is also one of the important aspects. The overall funnel conversion rate reflects the efficiency of the entire marketing and sales process. From attracting traffic to closing orders, it's crucial for evaluating end to end performance and return on investment of campaigns. Now, let's go through the approach to solve this question and query design. The query aggregates total orders and traffic and calculates orders divided by traffic into 100. This approach summarizes the overall funnel efficiency, giving leadership a clear metric of conversion effectiveness. Now, let's go through the query. So here we have it. So we will be dividing total orders divided by total traffic and into and 100, and here we have a round function as well to limit the decimal values to 2, and we are aliasing it as overall conversion rate from sales data. So let's quickly execute this query to see the output. So overall conversion rate is somewhere around 0.09%. So this is some serious issue, so we need to focus more on sales and marketing. Don't worry, this is not a real sales data. This is an actual data which we created for learning purposes, right? So this particular, the real business data might vary a lot, but it could be also a reality where the conversion rate is really falling and you need to focus on improving, right? In the initial stages, any business might have weak performances, but down the line, if you are someone who's really good with analytics, then you can help the company to grow, right? That's the overall perspective. Now, let's dive into the next question, which is about funnel performance by category. So, why this particular question is being asked? Now, let's go through that. Analyzing conversion by product category helps identify which product lines convert visitors into buyers most effectively. This insight guides marketing focus, inventory allocation, and promotional strategies. Now that we understand why this question is being asked, let's go through the approach to solving this question and the query design. The query groups data by category and calculates conversion as total orders divided by total traffic into 100. Using grouped aggregation allows comparing performance across categories and identifying high and low performing segments. Now, let's execute the query. So as discussed, we have the category and the function of total orders divided by total traffic into 100. And we are rounding this particular number as two decimal values using the round function. And we are aliasing it as conversion rate. And we're extracting this data from sales data and we're grouping by category. Now, let's quickly execute this query. So we have electronics, clothing, home appliances, FMCG, furniture. So far we have furniture and FMCG as the highest performing categories, and the conversion here is really good. Now, rest of them needs a little more attention. And with that, we enter the fifth segment of this particular analytics, which is order and operations analysis. In that, we have the 14th question as our first question, and it is about order status distribution. Now, let's deep dive what's the meaning of this question, and along with it, we'll also go through the solution approach and the query design for this question. So, order status distribution is really important as well. Understanding the distribution of order statuses, which is delivered, pending, cancelled, etc., provides visibility into operation performance and customer satisfaction. It highlights bottlenecks and potential service issues. Now that we have a brief understanding of the question, let's go through the approach in solving this question and the query design. The query here basically groups by order status and counts the number of orders per status using count star function. This gives a simple frequency distribution, making operational insights easy to interpret. Now, let's go through the query and execute it. So as discussed, we have the order status and we are counting the total number of orders and we're aliasing it as total orders from sales data grouped by order status. So we might be having a delivered, cancelled, pending, something like that, right? Based on that, we will be grouping it. So we have 997 delivered, 986 cancelled, and 1013 written and 980 pending. So these are the statuses of our products so far. Now that let's dive into the next question, which is average delivery time for delivered orders. So if you go back to the dataset, you might have seen order date, delivered date, and as well as we have created another column which says time to be delivered, right? So it is basically the time difference between delivered date and ordered date. Let's say we have 5 days of difference between the order date and delivered date. So we are trying to, okay, before we solve this question, let's understand why this question is being asked and what's the query design, right? That is the basic approach before you start to write any query. You need to understand the question. And if only you understand the question, then only you can design a perfect query for that. So let's understand the question. So average delivery time for delivered orders is basically measuring average delivery time that helps evaluate logistics efficiency and customer satisfaction. Faster deliveries usually correlate with better customer experience and retention. Now, let's understand the solution approach and query design. The query calculates the average difference between delivery date and order date using the average date diff function. For orders marked as delivered, filtering ensures only relevant orders which are completed are included and rest are ignored. Now, let's go through that. So here we before the previous question we had cancel, return, and pending, right? So here we are specifically filtering out the delivered products only, right? So once we have the data of delivered orders, and based on that, we can find out the order date and delivery date of that particular product and find the difference. And once the difference is found, we will have multiple rows of number of dates, and that particular rows will be filtered out using an average function, right? Let's consider 10 rows. One product might have taken 5 days to deliver, one might have taken 3 days, one might have taken 2 days, one might have been taken 7 days, right? So out of all those 10 entries, we will find out an average of 10 days, 7 days, 3 days, 6 days, etc. And then we will have a final number. So you can declare that as this is the average time that we are taking to deliver one product to a customer. Now let's execute this query. And there you go. So on an average, we are taking about a 5.99, or we can consider 6 days on an average to deliver any product from the inventory to the customer. So on the application or on the website, you can confidently mention within 6 days, your product will be delivered to you, right? Now that may help you in retention, right? So customer might feel happy that within 6 days, I'll be receiving this product. That's the basic approach behind this question. Now we have the question which says or speaks about cancellation rate, right? Now, why this question is being asked and how do we solve this? Let's understand that. Cancellation rate measures the proportion of orders that did not complete successfully. High cancellation rates indicate potential operational issues, product dissatisfaction, or a pricing problem. Now that we have understood the concern behind this question, let's understand the approach to solve this question and the query design. The query counts cancelled orders using a case statement inside some function and divides by total orders. Next comes the round function, which formats the result as a percentage, giving a clear view of order cancellations. Now that we have a clear understanding of how this question can be solved, let's go through the query and solve this particular question. Here, let's dive with this particular case. So we are using cases here. Now, when case order status is cancelled, then 1, else 0. So in the previous chapters, we've also been through cases. And this gets divided by count of staff into 100. And the decimal value is limited to 2 numbers. And this is aliased as cancelled rate. And now let's execute this query. There you go. So the average cancellation rate we have is 24% as of now, which can be reduced based on improving the product quality and decreasing the days to deliver and basic things that we discussed now, right? Now, let's go ahead with the next question, which is the 17th question. And a new section is also allocated here, which is about profitability analysis. Now, in this particular profitability analysis section, the first question we have is profit margin by product category. Now, let's understand the question. Profit margin by product category is basically about evaluating profit margin by product category, which helps identify high margin product versus a low margin category or product. This informs pricing strategies, product focus, and profitability optimization. Now that we have a briefing on the question, let's go through the approach to solving this question and the query design. The query groups by category and calculates the total profit divided by total revenue into 100. And we will be filtering out by revenue, which should be greater than 0, which avoids invalid calculations. And finally, we'll have a round functions, which ensures clarity in presentation. Now that we have a briefing on the approach, let's go through the query and execute this. Now we are trying to find out the profit margin by dividing the total profit by total revenue. And we have a round function to minimize the decimal values to 2. And we are aliasing it as profit margin. And here you see we are filtering out the revenue should be greater than 0 and we are grouping by category. Now let's quickly execute this query and see the output. So here we have all the categories and their profit margins as well. And you can also add another query which is order by descending. So we have FMCG on top and the rest of them in following in the next, right? We have clothing in the next section, home appliances in the next section, and so on. Now we have the next question, which is the 18th question in this section, which is about loss-making products. Now, let's go through the intention behind asking this question. So, loss-making products is nothing but identifying the products that generate a little or negative profit. This helps businesses optimize their portfolio by removing or repositioning loss-making products, and this can make significant improvement in overall profitability. Now we have understood the intention behind this question. Let's understand the approach to solving this question and the query design. The query basically groups by product and sums profit, and we are using having by clause where the total profit should be less than 10. And this filters the underperforming products. This approach directly highlights the items contributing minimally or negatively to profits. Now that we have a briefing on the approach, let's go to the query and solve the question. Now, as discussed, we have the sum of profit from sales data, and the filter having profit less than 10 is the filter or the query here. And now let's execute the question. So far, there are minimum products which are underperforming. Those, or you can also change to 2 and find out if there are any products which are even now. So it's good enough. Maximum number of products that we have in our inventory are not underperforming, right? So that's a good news. Now, with that, we enter into the next section, which is advanced analytics, and it makes you a little ready for interviews. Now, inside that, we have about 2 questions more, and out of which the first one is top 5 customers by lifetime value. Now, what does this question mean? Now, let's highlight the query and understand what's the intention behind this question. So top 5 customers by lifetime basically means the lifetime value or LTV, which qualifies the total revenue as a customer brings over time. Identifying top customers by LTV helps prioritize retention, loyalty programs, and personalized marketing strategies. Now that we understand the intention behind this question, let's go through the approach and query design to solve this question. The query groups by customer ID, sums revenue per customer, orders the results by lifetime value in descending order, and limits the output to top 5 customers. This highlights the highest value customers most efficiently. Now that we have understood the approach, let's go back to the query and execute this. So here we have minimum customers. Yeah. So these are your high value customers, which gave you about so much revenue. 1,71,000, 140,000, 120,000, 117,000, and 117,000. So these are the top 5 customers which have your highest lifetime value. So here we have the sum of revenue as lifetime value and customer ID. And we are grouping by customer ID and we are ordering lifetime value in descending order. And we have the limit 5, right? So which reduces or filters out the top 5 performing customers. Now we have the last question in this particular project and the second and last question in this particular section of advanced analytics. So this question is about repeat customers versus one-time customers. Now, what do you mean by repeat customers versus one-time customers? So let's understand this question. So repeat customers versus one-time customers differentiates repeat and one-time customers is crucial for retention analysis. Repeat customers indicate loyalty, while one-time or high one-time orders may point to marketing but weak retention. Now, this was the intention behind the question. Now, let's go through the approach in solving this question and the query design. The query first calculates order counts per customer in a subquery. Using a case statement, it classifies customers into repeat or one time, grouping the customer type, and counting provides a clear comparative distribution. Now, let's go through the query and execute it. As discussed, we have case statement here. So if the order count is greater than 1, then it is referred as repeated customer. Else, it is referred as one-time customer. And the case ends here, right? And now we will count the total number of repeated customer and we'll also count the total number of one-time customers. And from there, we will select the customer ID, order count, and then we group by customer ID, right? So this particular query is encapsulated inside an outer query. So this is the inside query and this is the outside query. So if you have any doubts in subqueries, you can go back to the subqueries chapter and go through that once again. Now, finally, we will group by the customer type and then we will have the total number of repeated customers and the total number of one-time customers. So let's quickly execute this query. So there you go. We have 2,574 one-time customers and 642 repeated customers. And that brings us to the end of this session on the SQL data analysis project. And now we will proceed to the next section. Now we enter module 13, which is basically about framing SQL as an analytics tool. Up until now, we have been using SQL primarily to fetch data. But in this chapter, we will shift our focus. We are going to use SQL as a powerful tool for analysis. This is the difference between someone who knows SQL syntax versus someone who can drive business decisions using SQL. So, what does data analysis in SQL really mean? It's about comparing values to identify patterns, creating categories for better insights, ranking records to spot top performers or priorities, tracking change over time to understanding trends, finding patterns directly in SQL without exporting to Excel. This chapter is essential for anyone in analytics roles, including data analysts, business analysts, product analysts, BI developers, writing analytics queries, and a lot more. Now, let's get started with what is an analytical query. An analytical query is more than just fetching data. It is designed to aggregate information, compare results across groups, identify trends and patterns, answer why something is happening, not just what is happening. For example, you might want to ask who are the top performers in my company? Which customers bring the most value? How is revenue changing day by day? Now that we have understood the basic fundamentals of this particular chapter, let's get started with the analytical queries. Now, starting with the first one, salary analysis. And the business question here is, what is the average salary per department? Now, here we will understand the group by, which allows us to define the level at which we want to analyze the data. The aggregation functions like average convert raw rows into meaningful insights. Now that we have the basic understanding, let's go through the query. Now here, this was our first analytical query, which asks one question. What is the average salary per department? Let me expand this particular area. Yeah. So here, what we're trying to do is we are trying to identify the department name and we're using the average aggregate method to identify the average salary and we're aliasing this as average salary. And we're extracting this from the employees table E and we are trying to join with departments table D and we are joining the tables based on the department ID from employees table and departments table and we are grouping by department name, right? So based on this query, we will be getting the department names in the table and their average salaries. Now let's quickly execute this query and see the output. Now based on the query, we are having HR as 60,000 average salary, engineering as 1 lakh 8,000 as average salary, finance as 95,000 and marketing as 80,000. Now, let's go into this second analytical query, which is about how many employees were hired per month. Now, let's understand the question here first. So business question here is how many employees were hired in each month? The real world relevance? This analysis is used in HR planning and workforce forecasting. Now that we have understood why is this particular question is being asked, let's solve this. Now in the query, we have date format. Here, we are extracting percentage %y, which stands for year, and percentage %m, which stands for m. Now based on this, we are hiring employees and we are using count star and we are aliasing this as hires, and here we are aliasing the date format as hire month. And we are grouping by hire month and order by hire month. Now, let's and execute this query. And there you go. And in case you want to, uh, order by, add some more value to this, you can order by descending, and which gives you December and November were the highest hiring months. And this is our answer. And now let's proceed with the next analytical query, which is right here on my screen, customer order frequency. Before we execute this query, let's understand the key aspect, why this is a question here and how do we solve this. So customer order frequency basically gives one business question. How often do our customers place orders? Now, what's the business meaning? This query helps identify repeated customers, which is critical for designing loyalty campaigns. Now, let's go to the query. Here we have the query, and here we have the customer ID count as star as total orders from orders data table, and we are grouping by customer ID and order by total orders in descending order. So once we execute this query, here we have our output. So these are the customers and their total orders. Customer number 2 is a repeated customer and the total orders placed by him or her are 4. Next is customer ID 1 and he or she placed 3 orders and so on. Now we get into another example, which is case example salary banding. Now the business need clarify the employees into salary ranges or classify the employees into salary ranges. Let's select the query. This is our query. Now let's understand the intention behind this query. Using case statements in select. So what is a case in SQL? Think of case as a SQL's version of if-else logic. It allows us to create categories, apply business rules, convert numeric values into readable labels. Now, case example. Salary banding. Now, what is the business need here? We need to classify employees into salary ranges. Why analysts love case? So we have some answers for that. It eliminates the need for pre-processing. You can perform clean categorization directly inside SQL. Now let's go through the code. So here we have the case. So when salary is greater than or equals to 1 lakh, then deem it as high. And when salary is greater than or equals to 70, then deem it as medium, else consider it as low. And the case ends here. So this is our case statement. And we will alias this case as salary band. And we will be extracting name of the employee, salary details of the employee, and the case result of the employee from the employees data table. Now, let's execute this query and see the output. So we have Alice, Bob, Charlie, David, and Eve, and their salary numbers, and their salary band falls in medium, high, so on, as described in the case statement here. So Frank is having low salary, and Ivan is having low salary, or in case of low, you can also tag them as new recruits or freshers or interns, right? Now, with that, let's move into another example for case, which is department-wise salary labels, which is basically a similar approach, right? But still, let's go through the question once again. So the example 2, which we have about department-wise salary labels, which is basically none other than the same question. So let's go through the query here once again. But there are a few differences. In case of salaries, we have the department-wise details here. If department ID is equals to 2, then tech department, department 1 is equals to support department and others, right? So this query is basically designed just so that you understand how case actually works in real time, right? Now let's execute this query and see the output. So here we have the same name of the employee, department ID. And if the department ID is 2, then we have the tech department. If it is 1, then the support department. If it is anything other than the tech and support, like marketing, software engineering, etc., we will deem it as other, right? There you go. Now let's also go through another example in case so that we have a comfortable understanding. So here the example is about customer segmentation. Now, what's the business aspect of finding out this particular answer? Now let's go through that. Let's select or highlight the query first. So what's the business question, right? Which customers are high value and what's the industry usage? It is used in CRM segmentation, marketing, target, and revenue prioritization. Now, let's go through the query. So here we have the case statement. So this particular one is the case statement where count is greater than 4 or greater than or equal to 4, and it is high value customer. Greater than or equal to 2, then medium value customer. If it is greater than or equal to 1 or less, then low value customer. This is aliased as customer segment, and we are counting the total orders here and the customer ID. We're extracting the customer ID from orders table and group by customer ID. Now, let's execute this query. Control enter. And here we have the customer ID and total number of orders they have placed. So if it is greater than or equal to 4, high value, greater than equal to 2, then it is medium value. And the other one is else low value, right? So this is how you execute the customer retention things, right? Now we have the next function, which is a row number. Now out of which one example is rank employees by salary per department. Let's highlight the query first and then understand the intention behind this function and how do we use it. So before we move into the next function, which is row number, I want to quickly deliver one interview tip for you. So if ever someone asks you about to explain about case, then consider two things, right? The bad explanation of case could be this one. Case just replaces if. No. Yeah, I agree that I told if is a replacement for case in SQL, but there is a difference, right? It was given for a quick understanding of the difference. But in interviews, that's the reason why I'm giving this tip to you. In interviews, when someone asks you to explain about case in SQL, then you can go with this strong explanation where instead of just saying it as a replacement for if, you can say case enables rule-based categorization directly in SQL query. If you have gone through our codes here, you can see we have different categories, right? If there is something happening in the dataset, then deem it as or categorize it as under this particular value. And similarly, if something is happening here, category in this particular aspect, and so on, right? So it is just another categorization tool where it compares the values and based on the results, it categorizes. This is the perfect and strong explanation of case in interviews. Remember that. So in the beginning, we said it is just a replacement for if. It is just said so that you have a quick understanding. It's not the final answer. Remember this. Now we enter window functions, which is the core of data analytics. Now, what are window functions? Window functions allow you to perform calculations across related rows without collapsing the data, unlike group by. Why window functions matter is your next question. Now, without window functions, you often need complex subqueries and multiple joins, which hurt performance. With them, your queries get cleaner, faster, and more readable. So, one such window function is row number. Now, what does row number function do? It assigns a unique sequence number within a group. For example, rank employees by salary per department. Now, what's the business usage of this particular question? It identifies top performers duplicating records, picking the latest records. Now, let's go through a sample query here. So here on my screen, you can see a sample query where we are selecting a customer ID. They're counting them as total orders. Okay, this was a previous query. Yeah, here we have the row number. So this was the example, rank employees by salary per department, right? So here we have the employee ID, employee name, department ID, and their salary. And here we have the row number function over partition by department ID, order by salary descending as salary rank from employees. Now let's quickly execute this query, and there you go. So based on salary numbers, we have rank 1 and 2 and 3, 4, and so on, right? Now, we will have a quick comparison between rank function and dense rank function. And we'll also go through an example which says department salary ranking. Now, let's highlight the query and then we will try to understand the business requirement or business behind this particular functions. Department salary ranking, right? Rank skips the numbers if there's a tie. Dense rank, on the other hand, does not skip any numbers. That's the basic difference between rank and dense rank. Now, let's execute this query and see the output. So, there you go. So, there are no rank gaps like we had in the rank, right? Here in the dense rank, we don't have those gaps. Now we have another window function, which is lag function. It assesses previous row data. And we also have a quick example for this here, day over day sales comparison. Let's highlight the query. Now let's understand the business behind this function. Lag method accesses data from a previous row. For example, day over day sales comparison. Now the business insight. Growth analysis trend is one business insight where you can implement the lag method. Now let's go through the example. So here we have the lag amount over the order by date and the previous day sales. Now let's execute this query and see the output. Now the daily changes are written in the last column and the previous day sales are here and the total amount is here. Now the next function is lead, which is assesses next row data. Now let's highlight the query. Now, what is lead method? It assesses data from the next row. What's the use case? It is used in predictive comparisons, performance tracking, and much more. Now, here we have a query for quick understanding. And let's execute this. And there we have the output. Now, the last one in this particular segment is the running total. So, running total window function, which is basically from advanced analytics. Let's highlight the query and now understand the business insight of this particular window function. So this particular window function is used in financial dashboards, KPI tracking, investor reporting, and a lot more. Let's quickly execute this query and see the output. There you go. So we have the outputs over here. Now, let's have a quick follow-up of all the window functions. Case statements, window functions, analytical thinking in SQL. You are no longer a beginner. This chapter prepares you for data analyst interviews, building business dashboards, solving real world analytics problems, and a lot more. With that, we have come to an end of this module, and now we transition to the next module. So, the first question is, what is the difference between SQL and DBMS? To understand this question at a professional level, learners must internalize that SQL and DBMS serve two completely different roles, yet they work together tightly. SQL, or structured query language, is a standard communication language. It is the vocabulary and grammar we use to talk to a database. We can write select star from customers. We are simply sending a request. We don't actually store data using SQL. We don't manage files using SQL. We don't enforce security using SQL. All of that is the job of DBMS. A DBMS, or database management system, is a fully fledged software that handles how data is stored internally, how it is indexed, how users access it, how security rules are applied, how concurrency is handled, how backups and recovery work. So SQL is just the language, while DBMS is the system that understands and executes that language. So a helpful analogy: SQL is the remote control and DBMS is the TV that responds to the button presses. Without TV, the remote accomplishes nothing. Without remote, the TV cannot receive instructions. Now let's go through some examples to strengthen the understanding of SQL Server. SQL Server uses eSQL, Oracle uses PL/SQL, PostgreSQL uses PostgreSQL, Dialect MySQL uses its own SQL variant. So SQL sits inside a DBMS the same way a steering wheel sits inside the car. It's necessary, but not enough to make the car move. Now, the second question: explain primary key versus unique key. This question helps interviewers assess whether you understand how relational databases maintain identity and prevent duplicate records. A primary key is the central identifier for a row. It is the official identity card of each record. Before that, a primary key must meet two conditions. The first condition is uniqueness. No two rows can share the same ID. Second one, not null or non-null. Every record must have an identity. A unique key, on the other hand, enforces uniqueness but does not define the identity. It's more of a constraint that ensures no duplicates are allowed here. So the key difference is primary key is equals to strict, no duplicates, no nulls, only one per table. On the other hand, unique key is equals to flexible, no duplicates, allows a single, multiple allowed tables analogy. On the other hand, unique key, which is equals to flexible, no duplicates allowed, a single null, multiple allowed. Now let's go through a table analogy. Imagine a table analogy. Imagine a table called employees. Primary key is employee ID, unique keys are email, phone number, and every employee must have an ID. But emails simply must be unique to avoid any conflicts. This distinction keeps data clean, consistent, and logically structured. With that, we move into the next question. What is a foreign key and why is it important? A foreign key is the glue that holds relation databases together. It connects tables exactly the way real-world relationships links entities. A foreign key in one table refers to primary key in another. This enforces referential integrity, meaning you cannot insert an order for a non-existing customer. You cannot delete a customer still referenced by others. You cannot break relationship chains accidentally. Now let's go through a real-world analogy. An order referencing a customer is a passport referencing a citizen. The relation must be valid. Without foreign keys, datasets become chaotic. Broken relationships, missing references, incorrect reports, often records, foreign keys keep the database accurate, safe, and logically consistent. Now, the fourth question, difference between where and having. Now, this is one of the most commonly tested SQL concepts because it checks your understanding of query execution order. Let's start with where. Where clause filters rows and applies before the group by function. It cannot use any aggregate functions. For example, where salary is greater than 50,000. Having clause, on the other hand, filters groups after group by function is applied. It can go with aggregate functions. For example, having count greater than 3. Now, let's have a mental model mapping. Imagine organizing employees by department. Where clause filters individual employees before grouping. On the other hand, group by forms the groups. Next is having clause. Having filters the groups themselves. This conceptual clarity helps avoid mistakes in analytical SQL. With that, we jump into the question number 5. The question number 5 is about the difference between inner join versus the left join. Joins reveal how well someone understands relational thinking. Inner join returns rows only when both tables have matching values. Left join returns all rows from the left table and matching rows from the right table. Missing matches become null. Now, let's have a mental visualization. Let's have a Venn diagram. Inner join is equals to intersection. Left join is equals to entire left circle with intersection. Now, let's go through a practical example. For inner join, let's consider customers who made some purchase. For left join, all customers, including those with zero purchase. This distinction is essential for building BI dashboards, performing retention analysis, or generating financial summaries. Now, let's dive into the question number 6. What is normalization? Normalization is the process of structuring data to reduce redundancy and improve consistency. So, we have a few types of normalization. So, the first one is 1NF, no repeating groups. So, atomic only values are stored here. The second one is 2NF. It must be in 1NF, removes practical dependencies. The third one is 3NF, must be in 2NF and removes transitive dependencies. Why normalization matters? Normalized data avoids duplicate information, updates anomalies, inserts anomalies, deletes anomalies. So the database remains scalable, clean, and reliable. Now let's enter into the question number 7. What is denormalization? While normalization focuses on structure, denormalization focuses on performance. It intentionally introduces redundancy to reduce joins, lookups, computation time. And now comes the question where it is used. It is used in data warehouses, BI reporting, OLAP, star schemas, etc. Now let's consider a small analogy. Normalized is equals to highly organized data library. Denormalized is equals to popular books placed at the entrance for quick access. You trade structure for speed. Now we have the 8th question. What is a subquery? The answer, a subquery is simply a query inside another query. It is used to answer more complex questions. Where subqueries help is your next question. It helps in dynamic filtering, ranking, and comparisons. Apart from that, it is also used in conditional validation, nested logic, and a lot more. A few examples to consider: finding second highest salary, checking if a value exists in another table or not,
filtering based on aggregated criteria, subqueries increase the expressive power of SQL dramatically. And with that, we dive into the question number 9. What is an index and why is it used? Indexes are crucial for database performance. Let's go through an analogy. Think of an index page in a book. It helps you jump directly into the right content instead of flipping every page. What indexes do? Indexes accelerate select queries, improve filtering and joins, enable fast ordering and grouping, but they come with a cost. Slower inserts, updates, because index must be updated. Increased storage usage. Indexes are one of the first performance optimization tools. Every SQL developer must understand them. Now, with that, let's dive into the question number 10. Question number 10 is, what is ACID compliance? ACID, or simply called as atomicity, consistency, isolation, and durability for the full form. It ensures reliability and predictable transaction processing. Atomicity is the first one. All steps succeed or none do. Second one, consistency. The database remains valid after each and every transaction. Next is I for isolation. It stays concurrent transactions do not interfere. Last is D for durability. It changes, survive, crashes. These principles make transactional systems trustworthy, especially in banking, e-commerce, ticketing, and ERP systems. With that, let's dive into the 11th question, delete versus truncate versus drop. Now, these commands all do the same thing. They remove the data, but with crucial differences. Delete is row level removal, logged slower, can use where, and can be rolled back. Truncate does not use where clause and mostly it is irreversible. The third type is drop. It removes the entire table definition and data and it is completely irreversible. This distinction is extremely important for safe database operations and disaster recovery. Now let's move into the 12th question. So the 12th question is, what is a view? A view is a virtual table based on a query. Why views are used? It is used to hide complex joins, improve security, simplify repeated logic, provide abstraction layers. Views are heavily used to enterprise applications and BI too. Now, with that, let's dive into the 13th question. What is a stored procedure? Stored procedure is a pre-compiled blocks of SQL that sits inside the database. Benefits: reusability, security, consistency, reduced network load, better performance, and many more. They allow complex business logic to run close with the data. Now we have the 14th question. What is the difference between char versus varchar? Character has fixed length storage. On the other hand, varchar has variable length storage. Char is ideal for country codes, gender, etc., which has mostly the fixed identifiers. Varchar is ideal for emails, names, addresses. Understanding this distinction leads to better storage optimization. Now, the last question in the theory section. What are window functions? Window functions allow you to perform calculations across rows while preserving individual records like group by, which collapses rows. Most common window functions are row number, rank, dense rank, lag, and lead, sum, over, average, over, and a lot more. Where they are used is your next question. We can use them in running totals, moving averages, trend analysis, time-based comparisons, leaderboards, cohort analysis, and a lot more. Modern SQL exams and interviews test window functions heavily because they reflect practical analytical skills. Now comes the next part of these interview questions where we will be dealing with practical query-based or scenario-based questions and answers. So now we are in the scenario-based or practical query-based interview questions and answers. So let's go through the questions and answers quickly because we will be creating a new table, entering the data. After that, run the queries. So let's go through the questions and answers quickly. So first we have the fetch the second highest salary from the employee data table and we have the answer here. It uses a subquery to exclude the highest salary and extract the next one. Now the second question is retrieve employees who have no department assigned. So this is the answer for it. It uses left join to identify unmatched rows. So what we are currently doing is we have a list of 10 interview questions and answers. So we'll quickly run the PowerPoint presentation and have a quick analysis on what we are going to face and how are we going to answer the question. And you can see the last line, right? This particular last line gives you a small hint of the logic we are going to implement. So once we are happy with all the overview of all the questions and answers, and then we will create new data tables. And inside the new data tables, we will add new data entries and then start question by question and run our queries and extract the outputs that we are looking to. Now, the next question in the list is find duplicate email IDs in the table. And after that, we have display the top 3 highest paid employees. So here we have order plus limit, where we will limit the output to only 3 rows. And then we have count orders per customer. We will be using a count function here. Then get employees whose salary is above the department average. So first we will be calculating the average of salary, and then we will include that inside the subquery and find the employee who has salary greater than that particular value. Next, we have display employees hired in last 30 days. So this is related to our time date function. So we will use the current date and then subtract the interval of 30 days. Then we have get all customers who placed more than 5 orders. So we have to use group by and having functions here. Then retrieve the running total of all the sales, use a window function for cumulative logic. Then we have to remove the rows while keeping only the latest records. So it keeps only latest records per unique email. So we will be using unique function here. So this is the overall overview of all the 10 scenario based or demo based questions that we will be facing today. Now, let's quickly jump onto the MySQL workbench and try to create the new tables, add the entries, and then run each and every single query for each and every questions that we have listed here. So now we are on the MySQL workbench. So this is the SQL training interview questions that we are facing. So let me also check the data table first real quick. So I have a doubt that I've already created a table on interview questions. So for better clarity, yeah, we have created a database, but there is no table inside this. But yeah, we do have tables. So let's open a new query prompt quickly and see, or we can use the same prompt. Let's check it. Use, let me expand, database interview. We are in interview and then show tables. Yeah, we do have created all the department employees order sales data. So let's quickly run the select commands star from departments. But if you are worrying about the queries to create the data sets, don't worry. So here you can see on my screen, we have the entire code documentation done for us, the SQL training documentation. So here you have the, commands for creating the table, inserting the table data, and then selecting the employees and all those things. And apart from that, if you scroll a little bit down, here are the places where we start with interview questions and their answers. This is the section. So this is the first question, right? So no worry, all the tables are created for saving time. And also this particular document is listed in the description box below. You can go through that and start running the queries along with me, right? So now let's go to the table here. Select staff from department. So we have about 4 departments, and the fifth one deliberately left as null because one of the questions was also listed as find the employees where a department is not assigned yet, right? Something like that. And we have a second select. Let's copy and paste quickly so that we save time. And instead of departments, we have employees. This is the employees table. And we have the employees here. Department is equals to null. So Frank is one of the employees where department is not assigned. So we will be extracting them in the runtime. And the third one was about orders. And we have the following orders along with the date time. And next table is sales. So we have the sales here, sales table. And lastly, users. Let's run. And there you go. So now we have a briefing on all the data table entries and the elements. Now let's go back to SQL file number 8. I think we do not need to create any tables so far, so I'll eliminate this particular part. And that brings us to the first question. Fetch the second highest salary from the employee table. Now, we need to understand subqueries here. So we've already been through subqueries tutorial. So I have highlighted a small part of the single query, which states select maximum salary column. So we have a salary column. Inside that, we need to find out the maximum value inside the salary column. So that becomes a subquery. And that particular subquery is encapsulated inside an outer query. So outer query is this one. So we need to select maximum of salary from employees where salary is less than the maximum salary of employees. So basically, it gives you a list of all the salaries which are less than the maximum salary, but we want the second highest one only. So for that, you can also add limit one. If you don't add limit, what you will have is all the entire list of rows. But if we have limit, you'll just get one entry. So let's quickly run this. So we have this particular salary, which is second highest. You can also include employee name, right? So what was the name given for employees? So if we run the employee table here, we have name, right? So we can copy this field name, go back to file number 8, paste it here, comma. Okay. Right now, if you run this, you'll get the name of the employee. Okay. So what we need to do is employees dot name. This should resolve our problem. I think it's not working. Basically, this is how we run and we get the second highest salary. And there you go. Now, the second question is retrieve employees who have no department assigned. So here we need to perform join operations. So we are doing a join operation of left join on departments as well as employees table. And based on that, we will find a location where employee department ID is equals to null. And according to that, we will find out the employee's name. So let's run this query quickly. Left join departments D on employees department ID. So based on these IDs, we are finding or creating a join and then finding the employee. Enter, and there you go. So Frank with employee ID 6 and his salary is 60,000, but department is not entered, so it's on null. Now, proceeding ahead, we have the next question. Let me expand this. So the next question is find duplicate email IDs in a table. So here we will find a simple select query with email and count from users table, and we are grouping by email, and we are grouping by having count star is greater than 1. So what this basically does is if one email ID, right, is counted for multiple times more than one, then that particular email ID is been duplicated. So we need to execute this query here, and there you go. Alice at example.com is one particular email ID which has two entries there. It is repeated for 2 times. So we have a duplicate entry there. Now the next question is display top 3 highest paid employees. Remember the first query? It is completely similar to that one. So here what we are doing is we are ordering by salary and descending by salary, order by salary in descending order, and we are limiting to 3 entries. So we will have 3 entries. It is similar to the previous question. So quickly control enter. And we have 3 employee IDs, 2, 4, and 8. So these earn top highest salaries. Now next is count orders per customer. So we have customer ID and we are counting their order IDs as total orders from table orders, and we are grouping by customer ID. You can also do an order by thing here. So we can order by descending so that we can find out the highest orders. Let's try that. Well, let's execute this first and then try to plan out the order by query. So there you go. So we have customer ID and the total number of or total orders. Now let's get going with the next question. Get employees whose salary is above the department average. So we have already discussed this particular question. So what we are basically doing is we are encapsulating the query here. So let's format that. So here is our subquery. We are basically finding the average salary from employees where department ID is equals to this one. So we are finding the average salary and then we are comparing the salary with the average salary, and it should be greater than the average salary. Now let's execute this particular query, and there you go. So we have about 1, 2, 3, 4 employees who have salaries more than the average salary paid to overall employees. They must be in good roles. Now the next one is display employees hired in the last 30 days. So here we need to use the date and time function. Select star from employees. Interval is 30 days. I think interval is 30 is enough, or there must be a small query error here. So let's go to the next question. Get all customers. So let us consider this particular query as your homework. You can let me know the answer for this particular question. Display employees hired in the last 30 days. Go ahead with the time date function and find out the answer for this. And please do let us know in the comment section below. Now, the next question is get all customers who placed more than 5 orders. So we are selecting customer IDs from orders table. We are grouping by order ID and having. So we are going with an aggregate function here. So we cannot use the other function, but having. So having is the only function we'll go with the aggregation functions. So enter, and we are having the details here. So I think nobody is having more than 5 orders. Let's go with another number, 2. So we have 2 customers, customer ID 1 and 2, which have more than 2 orders placed. That's the answer. And next one is retrieve running total of sales. So for extracting running totals, we need to have aggregates over date as running total from sales. Now let's run this query. And there you go. Now we have reached the last question of this particular session. Remove duplicates rows while keeping only the latest record. So what we are doing here is select maximum creators subquery and users U2, and we need to find out the unique email. And if that particular email is repeated twice, then we need to delete that, and we need to keep only the latest entry of that particular email. So we are also using a delete command here. Enter. So I think there are no duplicate emails entered, so we already removed them so far. So that's how you remove the duplicate entry so far. And with that, we have finished the top 25 most frequently asked theory-based interview questions and answers, as well as scenario-based or query-based interview questions and answers on SQL. Now, let's proceed with the important tips for SQL certification exams. Now that we have decoded the theory questions and walked into some most commonly asked interview patterns, it's time to shift gears and boost your exam performance. Interviews sharpen your fundamentals, but certifications validate them formally. Recruiters, hiring managers, and even senior architects look at certifications not just as badges, but as proof that you understand SQL at a systems level. So, in this section, I'm going to walk you through high value strategies and by top performing candidates. These are not generic tips, these are insights sharp by real exam patterns, real failure stories, and success paths. Now, the first one. Master SQL fundamentals deeply. Every SQL exam, whether it's Oracle, Microsoft SQL Server, PostgreSQL, or any cloud-based SQL assessment, it's fundamentally built on the same backbone. SQL fundamentals. The exam creators know that if you truly understand these foundations, you can handle any advanced question with confidence. Now, when I say fundamentals, I don't mean memorizing definitions. I mean truly understanding why and when something works. For example, joins are not just about combining tables. They test how well you understand relationships between entities. Subqueries check whether you can break down data problems into layered logic steps or not. A key skill in real analytics. Transactions ensure that you know how databases maintain consistency even under failures. Indexes test whether you understand performance, not just correctness. Certification exams love focusing on those areas because they expose whether you're simply writing SQL mechanically or whether you can actually reason with SQL. You'll notice that nearly 60 to 70% of exam questions revolve around these fundamentals, sometimes directly and sometimes hidden inside complex analytical questions. So before you jump into mock tests or dumps, invest time in mastering the foundations deeply. Once you have this clarity, the rest of the exam becomes significantly easier. The second one is practice SQL on actual exam engine. One of the biggest mistakes candidates make is preparing on generic platforms like SQL Zoo, HackerRank, LeetCode, or any online-based examples, but not practicing on the actual exam environment. Each certification vendor, whether Oracle, Microsoft, PostgreSQL, or even cloud vendors like Google BigQuery, it has its own flavor of SQL. That means the syntax, the built-in functions, the error patterns, and the way the system responds to your mistakes can all vary slightly. For example, SQL Server uses TOP for row limiting. Oracle uses row number or fetch first. PostgreSQL uses limit. These small changes or differences can completely change the behavior of a query. The advantage of practicing on the real exam engine is that it reduces the exam time surprises. You're already familiar with the UI, the formatting rules, the syntax behavior, and how strict the evaluator is. You also get comfortable writing queries without relying on the autocorrect, autoformat, or syntax highlight. This is exactly why top scorers insist on simulating the exam environment early. The more you replicate real conditions, the more confident and stable you will be under pressure. The third one is learn vendor specific features. Now, let's talk about a very underrated area, vendor specific functionality. Every SQL database implements the SQL standard slightly differently, and certification bodies intentionally test these unique features. Let's break down some examples. Oracle SQL, row number. It is used heavily for pagination and row limiting queries. NVL, Oracle's versioning of handle null values equivalent to is null or coalesce in other engines. If you don't know these features, you will misinterpret these questions and lose marks. For example, SQL Server uses top n function, a very common row limiting clause. The other one is try convert, a safe conversion function that avoids throwing errors when conversions fail. Again, Microsoft exams love to test these. Another example is PostgreSQL's JSON-B. PostgreSQL's powerful binary JSON format is heavily tested because it's a core strength. Rich window functions like PostgreSQL is known for analytical SQL, so expect questions on ranking, partitioning, and frame clauses. When you learn vendor-specific features, you're not just memorizing functions. You're understanding the identity of each database. This gives you an edge because you can decode what the question writer is expecting. The next one is fourth one, understand execution plans. Execution plans are game changers. Modern SQL certification exams are not satisfied with candidates who can simply produce the correct output. They want you to understand how efficiently the database retrieves that output. Execution plans reveal whether an index is being used, whether a full table scan is happening, how joins are processed, which query operations are most expensive. When you understand execution plans, you understand the internal mechanics of SQL engines. This helps you answer exam questions that revolve around cost optimization, indexing strategy, and query rewriting. For example, an exam may show two queries with the same logic, but ask you which performs faster. Without knowledge of execution plans, you are guessing. With understanding, you're simply decoding the behavior systematically. This is why high scores always study execution plans. It's a direct way to align your reasoning with how the database actually operates. Now, the fifth one, learn to interpret SQL errors. SQL certifications don't always give you perfect queries. Sometimes they intentionally include incorrect code and ask you to identify the issue. If you're not comfortable reading SQL error messages, you will struggle. Common exam patterns involve foreign key violations. These test your knowledge of referential integrity. Null violations is the next one. These test check constraints, default values, and null handling logic. The next one is type mismatch errors. These enforce you to understand data types rather than relying on generic casting. Even experienced candidates get stuck because they expect perfect queries. Remember, the exam is not just testing your ability to write SQL, it is testing your ability to debug SQL. Now we have the sixth tip, master join combinations. Joins are one of the most commonly or frequently tested topics in SQL certifications. But not just simple inner joins. The real complexity is in combinations and edge cases. You need to be comfortable with cross joins, self joins, and right outer joins, full outer joins, anti joins. Not exist right now, but in exams it may be there. Exams often place these joins in the context of tricky dataset structures, missing values, duplicate records, circular relationships, and asymmetric data. The goal is to test whether you can visualize table interactions mentally. When you master joins at this level, you can handle any data retrieval question under pressure. The seventh tip is focus heavily on window functions. Now, let's talk about one of the most important areas in modern SQL exams, window functions. These include row number function, rank function, dense rank function, lead function, and lag function, sum function, over function, average function, and a lot more. Partitioning and framing clauses are also important. Why are window functions heavily tested might be your next question. Because they represent analytical SQL, the core of modern data engineering, business intelligence, and analytics workloads. Window functions allow row by row analysis without collapsing the dataset. This means you can perform ranking, running totals, and trend analysis and change direction, all with elegant syntax. In certification exams, these questions are often look complex, but if you understand partitioning and ordering deeply, you can decode them instantly. So, allocate special timing for mastering window functions. They are high marks, high value, and high impact. Now, let's go with the eighth tip. The eighth tip is about use official learning paths plus practice tests. Another strong recommendation, stick to official learning paths. These are curated by same teams that design the certification exam. That means the content is aligned with the exam blueprint terminology and difficulty level. For example, Oracle University's learning path, Microsoft Learning modules for SQL Server, and Azure SQL, PostgreSQL official docs, and tutorial guides. These official resources also contain free practice tests. Use these to gauge your readiness. Consistent scoring above 85% is good indicator that you're ready to book the exam. Remember, random online sources like blog posts may be good for learning, but they rarely follow the exact same pattern. Trust official sources when preparing seriously. Now, the next tip. The next one is our ninth one, build at least 2 real-world mini projects. Certifications are not just theoretical. Practical experience massively boosts your retention and intuition. Building real-world mini projects help you develop muscle memory. Some ideas include a sales dashboard with aggregations and window functions, a user engagement analysis with session-level SQL, a logistics or inventory dataset involving joins, subqueries, and transactions. These projects strengthen your ability to handle multi-table analysis, a core exam requirement. The more you practice data challenges, the faster you'll decode certification exam questions. The 10th and the last tip, build a time management strategy. This one area many candidates underestimate. In SQL exams, the time pressure is real. Even if you know the answer, poor pacing can cost you the certification. Here's a simple but extremely effective strategy. Attempt all easy questions first. Mark medium questions for revisit. Leave complex analytic questions, multi step queries, and optimization based problems for the last 25 to 30 minutes. This ensures that you maximize your score early and avoid getting stuck. Remember, exams do not reward you for solving hard questions first, they reward strategic thinking. And with that, we conclude this model, a complete roadmap to succeeding in your SQL interviews and certification exam. In this session, you learn how to articulate SQL concepts with clarity, precision, and confidence. We've reviewed the most common interview question patterns, logic behind real world SQL scenarios, and how certification bodies test both your fundamentals and your analytical mindset. The entire goal of this module was to help you think like a professional, not just write SQL queries mechanically, but develop a deeper reasoning style. And once you start thinking this way, SQL stops being just a query language. It becomes a tool for structured analysis, pattern recognition, and business decision making. With these fundamentals, you will walk into interviews and exams with not just knowledge, but confidence, speed, and strategic clarity. Now, take these insights, put them into practice, and start preparing for your next step in SQL journey. You got this. As we come to the end of the SQL full course, take a moment to pause, not just to finish a course, but to recognize how much ground you've covered. When you first started, SQL may have felt like a new language filled with unfamiliar keywords, syntax rules, and database concepts. But now, SQL should feel less like a tool you're memorizing and more like a language you understand, a language that allows you to ask meaningful questions of data and receive precise, reliable answers. This course was designed with one clear objective, not just to teach you SQL commands, but help you think in SQL. Because in this real world, successful professionals are not those who remember every syntax keyword, but those who understand how data behaves, how databases are structured, and how to extract insights logically and efficiently. Over the last few hours, you didn't just learn SQL. You built a foundation that is used daily by data analysts, backend engineers, data engineers, business analysts, and even AI professionals across industries. From startups to Fortune 500 companies, SQL remains one of the most trusted and widely used skills in data ecosystem. Now let's take a structured walkthrough of everything you have learned and even more importantly, why it matters. So, recap chapter by chapter learning journey. So, the first chapter, Introduction to SQL and Database Basics. You began by understanding what SQL is and why it is still dominating in 2026 and beyond. You learned that SQL is not just a programming language, it's the standard way humans communicate with relational databases. You explored how SQL powers everyday systems, banking, e commerce, flight bookings, healthcare, telecom, and analytics platforms. This chapter grounded SQL in reality, helping you see it's not just a theoretical concept, but as an invisible engine behind the modern digital systems. You also learn the difference between relational and non relational databases, understanding when structure matters and when flexibility matters. This comparison laid the foundation for architectural decision making later in your career. Finally, you set up your own SQL environment, an often underestimated but critical step. By installing MySQL or PostgreSQL and running your first query, you crossed an important milestone from observer to practitioner. Now comes chapter 2, Basic SQL Queries. This chapter marked your transition into hands-on SQL. You learned how to retrieve data using select statement, filter it using where, sort it using order by, and control result size using limit and distinct. These are not beginner concepts. They are most frequently used SQL commands in production systems. You also learn how aggregation functions like count, sum, average, minimum, and maximum help transform raw data into meaningful metrics. This is where SQL starts becoming analytical, where you stop looking at individual rows and start identifying patterns. By end of this chapter, you had the core skills required to answer real business questions using data. Now we dive into chapter 3, understanding data types and operators. In this chapter, you learn something many learners overlook. Data types matter. You explore numeric, string, date, and Boolean data types and how choosing the right data type impacts storage, performance, and accuracy. You also learned how arithmetic and logical operators allow SQL to perform calculations and comparisons. Operators like between, in, and like taught you how to filter data intelligently, skills that directly translate to writing clean, efficient queries in real systems. This chapter helped you move from writing queries that work to writing queries that work correctly. With that, let's make a transition to chapter number 4, inserting, updating, and deleting data. Here's where you learn SQL isn't just about reading data, it is also about responsibly modifying it. You practice insert, update, and delete operations while understanding why careless data manipulation can cause serious issue in production environments. You learn safe deletion practices, conditional updates, and the importance of verifying data before making any changes. This chapter introduces you to the mindset of a professional, someone who understands that data integrity is as important as data access. Now comes chapter number 5, mastering SQL joins. This is where SQL truly starts to show its power. You learn why joins matter and how real world data is almost never stored in a single table. Through inner join, left join, right join, and full outer join, you learn how to combine data meaningfully across many tables. You practice multi table joins and saw how business insights emerge when data relationships are used correctly. This chapter is often a turning point where learners realize SQL is not just about tables, but also it's about relationships. If you understand joins well, you already stand ahead of many beginners. Now comes chapter 6, grouping and aggregating data. This chapter focuses on summarization and insight generation. You learn how group by transforms detailed records into aggregated summaries and how having allows you to filter aggregated results. This distinction, where versus having, is subtle but very crucial. Here, SQL starts behaving like an analytical engine. You move from row level data to trend level thinking, which is exactly how data is used in dashboards, reports, and decision making systems. Now comes chapter number 7, which is about subqueries and nested queries. In this chapter, you learned how to write queries inside queries. Subqueries taught you how to break complex problems into smaller, logical steps, just like solving real world analytical problems. You explored single row, multi row, and correlated subqueries and saw how they can be used in select, from, and where clauses. This chapter sharpened your problem solving skills and introduced a more modular, logical way of thinking in SQL. And now comes chapter number 8, which is about data modeling and relationships. Here, you step back from writing queries and look at how databases are designed. You learn the difference between primary keys and foreign keys. You explored one-to-one, one-to-many, and many-to-many relationships and understood why normalization exists. This chapter helps you communicate better with data architects, backend engineers, and system designers. It also explains why well-designed databases make SQL queries simpler and faster. And with that, we come to chapter number 9, indexing and performance tuning. In this chapter, you learn that performance is not accidental, it is designed. You explored how indexes work, when to use them, and how they speed up query execution. You also learned basic optimization principles that help queries scale with large datasets. This knowledge separates casual SQL users from professionals who work with real production systems. Now we make a transition to chapter number 10, which is about views, functions, and stored procedures. This chapter introduces you to reusability and abstraction in SQL. You learn how views simplify complex queries and functions encapsulate logic and how stored procedures allow SQL to behave more like a programming environment. These concepts are widely used in enterprise systems and play a major role in reporting, automation, and backend workflows. Now comes chapter number 11, transactions and error handling. Here, you learn how SQL ensures reliability and consistency. You explored begin, commit, and rollback and understood the importance of asset properties. This chapter showed you how databases protect data even when systems fail. This knowledge is critical for finance systems, inventory systems, and any application where data accuracy is non negotiable. Now, chapter number 12, real world SQL projects. This was where theory met practice. You applied everything you learned by building a mini e commerce database, writing sales reports, and analyzing customer behavior. These projects mirror real world workplace tasks and help bridge the gap between learning and doing. Now, the chapter 13, SQL for data analysis. Here, SQL became a true analytical tool. You learn case statements and window functions like rank, row number, lag, and leak. These are powerful features and are used in advanced reporting and analytics platforms. This chapter aligns SQL with modern data analytics rules. Now comes chapter number 14, integrating SQL with Python. You learn how SQL fits into larger ecosystems. By connecting SQL with Python and Pandas, you saw how data flows from databases into analytical and machine learning workflows. This integration is essential for data scientists and engineers. Now, with that, we come into chapter number 15, which is SQL interview and certification preparation. You'll learn how SQL is evaluated in interviews and certifications. You explored common interview questions, best practice answers, and how to demonstrate SQL knowledge practically. This chapter prepares you not just to know SQL, but to prove it. Now let's go through a roadmap which explains you what to learn next. Now that you have a strong SQL foundation, here's what you can go with next. Advanced query optimization and execution plans, advanced window functions and analytical SQL, database internals and indexing strategies, SQL for big data platforms like Snowflake, BigQuery, and Redshift, SQL in real-time analytics systems, SQL for data engineering pipelines, SQL certifications from Oracle, Microsoft, and cloud platforms. Think of SQL not as a destination, but as a core skill that grows with you. SQL is one of the rare skills that ages well. Technologies change, tools evolve, but SQL remains relevant because data remains relevant. Every decision, every product, every AI model begins with data, and SQL is how we access it. If you have completed this course sincerely, you are no longer a beginner. You have the confidence to explore data, ask questions, and solve problems. The real learning begins now when you apply SQL daily, break queries, fix them, optimize them, and use them to create value. Thank you for committing your time and effort to this journey. Keep practicing, keep questioning, keep building. And remember, those who control data shape decisions, and SQL gives you that control. And with that, we have reached to the end of this session on SQL Full Course for beginners. Should you need any assistance or any other resources used in this session, or if you have any queries regarding any of the topics covered in this session, then please feel free to let us know in the comment section below, and our team of experts will be happy to assist you at the earliest. Until next time, thank you for watching and stay tuned for more from Simply Learn.